Can you see the screen, Sylvia? Okay, great. So I'll start then. So warmly welcome everyone for the Explainable Agency in Artificial Intelligence workshop, co-located with the AAAI conference. And we are funded by JP Morgan Research. So this workshop's idea came through a discussion with Sylvia and David and Rosina, because so far we didn't have a workshop that addresses the explainability and interpretability subjects in AAAI. Right, there were many workshops at HCI and AMAS and ICAPS, but we couldn't find a workshop in AAAI, so that's what we thought of doing one ourselves. And yeah, so again, a small message from our sponsor. Thanks very much for JP Morgan for sponsoring the registration fees of our speakers and panelists. For more information about their research, please visit this link. So a little bit about organizers. I'm Prashant Madhumar. I'm a PhD student at University of Melbourne, and I mainly work in reinforcement learning and how to develop explainability methods for reinforcement learning, and also a bit in causality and causal learning. And Sylvia pretty much works in the same kind of direction. We actually met in the last doctoral consortium, and we had a lot of overlap in our research. And actually, I met David in the last doctoral consortium as well. And he was actually my mentor in the doctoral consortium. So we had a discussion about the XAI workshops. And that is where we started the kind of inception of this workshop. And Rosina also works in machine learning, interpretability, and case-based reasoning interpretability. And she's from Drexel University, and David is from Naval Research Laboratory in USA. And I want to thank all my co-organizers for their effort so far. And so these are some related prior events among the main conferences. So we had the workshop on explanation in case-based reasoning in ICCPR, and we, of course, XAI workshop in HCI running from 2017 to up to now. And also there has been workshops, explainability workshops in AMAS, extra mass workshop, and ICAPS as well, explainable planning workshops. And there's also like big conferences now starting to emerge, the FACT conference, Fairness, Accountability, and Transparency. And also there's many workshops in interpretability in ICML. And so last year, we also had a explainable AI tutorial in last year's AAAI. But yeah, so as I said before, we didn't have any workshops specifically tailored to explainability in AAAI so far. So I want to thank the amazing work our program committee did. So we had we had 46 committee members and from all over the world. So to ensure the quality of our contributed talks and selected papers, so every paper received at least three reviews, and some papers even got like 5 reviews, and also a meta review. And we had a very diverse program committee from all over the world, from many disciplines, like even from cognitive science and HCI as well. More program committee members. So at the end, we had 46 submissions in total, and we accepted 26 papers. And these are either would be contributor talks or short talks, which I'll explain later. So when we talk about explainable agency, I'd like to present this diagram. This is kind of a diagram that shows, okay, explainable AI is just like this group effort from different disciplines, from HCI to cognitive science. And as you most of you are familiar with, explainable AI tries to address the concerns with transparency, trust, and ethics in AI to make them more accountable, interpretable, and explainable to humans. But this requires a range of expertise, ranging from artificial intelligence and human-computer interaction and cognitive sciences. So I think this diagram kind of encapsulate this multidisciplinary approach we need for explainability. Okay, let me. So Sylvia, I'll hand over to Sylvia to continue. So let me know if when to move the slide.
Okay, go ahead. So thanks, Prashant, for starting with the introduction. You can move to the next slide where I will give you an overview of the workshop. So even though the topic of explainable AI received the attention of the research community, the definition of what explainable AI is in machine learning and intelligence agents is still an open problem and varies a lot across research domains. So this leads also to inconsistency in the way the explainable AI part of the system is implemented and evaluated. And we try, as Prashant was saying before, to discuss this among researchers that comes from different areas in order to find a shared definition of explainable agency. And so with this workshop, we want to promote cross-pollination of ideas among practitioners of these research areas. You can move to the next slide. So we invited 4 speakers, and today we will have Ofra Amir and Timothy Miller from Technion and from the University of Melbourne. Tomorrow we will introduce Margaret Barnett and Pat Langley that comes from Oregon State University and University of Auckland. Next, we will also have 2 panels, and our panel discussion will involve researchers from both industry and academia, and we want to look at explainable agency from 2 perspectives, the industrial application perspective and more cognitive science research perspective. And so in the first panel, we will have Freddy Lecu, Vera Liao, and Bing Kim. And for tomorrow panel, we will have Eric Worm, Bertrand Malle, and Denise Agosto. Next. We will also have 15 oral presentation in those 2 days. And each presentation will have a Q&A session at the end. We will also have more longer contributed talks distributed between today and tomorrow. You can go. And this is the general schedule of our workshop. If you, for further information, like for more information, you can find the more detailed program in the website. We will have in each day 2 invited talks, as we said. So one at the beginning of each day and one in the afternoon after the lunch break. We will have 2 presentation sessions where we will have short paper presentations and 3 contributed talks session. We will also try to create some space for virtual networking and for discussion at the end of each day with the 2 panels that we mentioned before. So thank you everyone for participating and enjoy the workshop. And thank you again to our sponsor, JP Morgan.
Yes, so we'll be using Zoom chat for communication. So after if you have any questions for the presenters, you can just type in the Zoom chat and we'll moderate it and ask.
If you want,
yes.
If you prefer, you can also use the Rocket chat. I'm sending you again the link, but yeah, you can use both depending on what you prefer. We will check both of them.
Does Rosina or David want to say a few words, or can we move to the next?
I'm good. Thanks very much.
Thank you. Let's move.
Yeah. Okay. So I'll stop sharing, and I think next up is Ofra's talk. So Sylvia will introduce Ofra. I'll stop sharing.
Okay. So I don't know if you want to share your slides. I also created a slide with you only, but if you...
So I see I can't share my screen. You might need to make me co-host or something.
Oh. Let me check. I think Rosina has to.
Rosina has to make her.
Yeah.
I guess that will be true for all the speakers.
I will say a few words about you before you start, and then I give you.
Okay.
What is it that you saying that you're not being able to share?
Oh wait, no. Oh, sorry, my bad. I can't share. Sorry, I was minimized. Can you see?
Yes.
Yes.
Great. Sorry.
Okay. So Ofra Amir is our first speaker, and thanks Ofra for accepting to be part of the workshop and to give a talk today. She is a professor at the Faculty of Industrial Engineering and Management at Technion, and she leads the group of AI and people, and her interests lie in the intersection between artificial intelligence and human-computer interaction. She did a PhD at Harvard, supervised by Barbara Gross, and her thesis focused on the developing agents that support information sharing in human teams. So our contribution to AI include research in agent policy summarization, as we can see from the title of her presentation, and user computational models. So I give the word to you, Ofra. Thanks.
Thanks. Thanks very much, Sylvia, and thanks for inviting me. So I'll talk today about kind of recent work that we started doing about agent policy summarization, which has the goal of describing agent behavior to people, and hopefully it will be clearer in a couple of minutes. So in general, I guess for this audience, I don't need to motivate a lot, but there are many agents, both autonomous and semi-autonomous agents, that are becoming involved in our lives. And these could be both physical agents like robots or self-driving cars. It could also be virtual agents like agents recommending medical treatment or various other settings. And what we'd like to do in this work is improve people's knowledge of agents' expected behavior. And there may be several reasons for why we may want to do that. For example, if you need to choose between alternative agents, or if you need to decide how much autonomy to grant to an agent, then you might need to know something about the agent's capabilities and limitation. So our goal is to support users in gaining better understanding of the agent's behavior. And in general, this is a hard problem, as I guess, again, people here who work on explainable AI know, because it's actually hard for people to form correct mental models of how agents behave. And this is not something new. So in human-computer interaction, people have talked about how people's mental models of even simpler computer systems, like think about Word or Google Docs. So we form some mental model of how they work. But research has shown that the mental models that people form are typically incomplete, inaccurate, and unstable. So we'd somehow like to create better mental models for people with respect to how the agents behave. And in more specifically in our case, we're going to focus on sequential decision-making settings. So typically these will be reinforcement learning agents. And there's some prior work, mainly in recent years, some of it from Prashant and other people here maybe, on how to explain decisions in this sequential decision-making settings. And most of them focused on what's referred to as local explanations. So I'm in a particular state of the world, and I want to explain why did I choose a particular action. And there are various approaches to doing this. Some of them look at saliency maps and try to show where the attention of the agent is. Some of them, like Prashant's work, look at more causal models. But in general, these works explain particular decisions. And so they don't give a global description of what the agent will do in different states. Okay, so what we're doing is trying to work on a complementary problem, which is how to give this more global view of the agent's policy. Okay, and by the way, feel free to stop me if you have questions along the way. So our approach to providing some global information is what we call agent policy summarization or agent strategy summarization. And in a high level, the key idea is that we want to describe the behavior of the agent in a range of scenarios. So a kind of naive solution, if I want to describe how an agent behaves, I can just show you what the agent does in every state of the world. So as an analogy, say that my agent is Michael Jordan, and I want you, the basketball player, for those who don't know him, not the machine learning researcher. So I can just tell you, okay, watch an NBA season and see all the games, but that's not very efficient. So what we're going to try to do is sort of create these summaries that show highlights, that show kind of interesting states that the agent encounters, and try to illustrate the capabilities of the particular agent in a more efficient way. So instead of watching 80 games in a basketball season, maybe you can watch a short summary that shows kind of the main skills of your agent, in this case, Michael Jordan. Okay, so this is sort of the analogy. And more formally, if we're going to look at a Markov decision process setting, so we're going to assume that the agent has some representation of states, and there are actions that the agent can take, and there's a transition function that determines how the actions move the agent from one state to another, and the agent is rewarded according to some reward function, right? And so in reinforcement learning, typically our goal is to learn a policy, right, that maps from states to actions. And in this case, we're going to assume that we already have a policy, so someone else is solving that problem, and now we want to describe this policy to a person. So our input is going to be a policy of the agent that maps from states to actions, and the budget, which is going to tell us how much information are we allowed to show in our summary. Okay, this is sort of the time limitation of the user. And our output is going to be a set of state action pairs that demonstrate what the agent does in some selected set of the world states. Okay, so the key question then will be, what should we optimize when we choose these states? So imagine that the state space is very large, right? So Michael Jordan can do many things, or a self-driving car can encounter many different situations. And now I want to sort of show you highlights of this behavior. And now I need to think about which states to choose, what makes a good summary, okay? And what I'm gonna talk about in the remainder of the talk is two approaches for creating summaries. And then I'll also talk about more recent work where we try to combine summaries with saliency maps to provide both the global and the local perspective. Questions about the problem formalization or the motivation? All right, great. And so what information should we show? So the first thing we try to do, and this is joint work with Dan Amir, who wasn't a student in my group, but is my younger brother, so I can get him to do stuff. And our first attempt was to try to show important or interesting states. And what do I mean when I say important states? What would make a state important? So our intuition is that the state is important if the action that we choose has a substantial effect on our expected utility in the long run. So for example, this picture shows Michael Jordan making a shot 6 seconds to the end of the game, and they were down 1 point and then they won. Okay, so it has a lot of impact on the expected reward that we get. And if we go back to the MDT setting, so we're going to assume that we have access to the agent's policy, like I said, and also a simulator of the domain. And we're going to try to quantify this importance using Q values. So what do I mean by that? So the Q values, for people who are not familiar with that, when you train a reinforcement learning agent, you can think about quantifying the expected future rewards from taking a particular action and then following your policy later on. Okay, so if I look at the difference between the Q values of different actions in a particular state, okay, for example, the best action and the worst action, and then I'm going to say that the state is more important if there's a large gap between them. So sort of the intuition is that if there's no difference between the Q values, it doesn't matter, I'm going to turn right, I'm going to turn left, then I don't care about this state. But if there is a big difference, then I do care. So just to illustrate with an example from Pacman domain, which is what we used in our user studies in this case. So this state is important because Pacman here is very close to a ghost. And if Pacman will turn right, the ghost will eat it and it will die. And if not, it can keep accumulating score. Whereas this state is not very important because even though maybe going left is slightly better because Pacman will get some immediate reward, in the long run, it doesn't really matter. It can turn right and then turn back left. Okay, so there will be a smaller gap in the Q values, and I will consider this state much less important. Okay. Hopefully it's clear. It's hard when you don't see the audience, but I see some of it. All right, so this was our first algorithm for creating summaries. We called it highlights, and it used this importance score. So the idea again is the input is the agent's policy and the budget for how many states do I want to extract for the summary. And then the output is this set of state action pairs for the summary. And how the algorithm works is simply running simulations of the agent in the domain. So I let Pacman play, and in each state, I look at the Q values, and I just choose the states with the highest importance value. So the states where there's a high gap between the different actions Q values. So what does this end up looking like? So if you think of the sort of Pacman Michael Jordan example, so you can see Pacman eating ghosts and escaping ghosts. And that's going to be a summary that we're going to present to a user. Okay, all right. And then a second consideration that we looked at to slightly improve this, if you notice in this summary, all of the states are quite similar. So you see what happens kind of in the corners for the most part. So another criteria we added was diversity. And this is more a criteria not for a particular state, but for the summary as a whole. So I won't get into the technical details here, but the idea is that we will add important states that are sufficiently different from each other. So if there are two important states that are very similar to each other, we won't care as much about them. So then finally, we have this algorithm that chooses important and diverse states. And now the question is, does it work? And what does it mean for the algorithm for a summary to be a good summary? So in our first empirical evaluation, we used an agent selection task. So the idea was, again, we wanted to see if summaries help people understand the capabilities and the limitations of agents. So what we did is show them summaries of two different agents, and I'll describe it in more detail in a second. And they had to choose which agent they think is better. The way we phrased it is which agent they want that will play on their behalf. And they get rewarded with the bonus payment if they choose the better agent. And the way this worked is that we trained 3 different agents simply by varying their training time. So we had a low quality agent, a medium quality agent, and a high quality agent. And then for the summaries, we had 3 conditions. We had our and then we had 2 different baselines. One was just creating random summaries. And when I say random, it's really kind of showing frequent states more often because we're running the simulation. So if a state is encountered more often, it has higher likelihood of being included in the summary. And the second baseline was just showing the first trajectories in the game. So this is kind of like saying, you go and you watch Michael Jordan play until you run out of time. And all of the summaries were, of course, of the same length, the same budget. And then we had the 40 participants on Amazon Mechanical Turk within subject design. So everybody participated in all conditions. So this means that people did 9 agent comparisons. So they had, for example, low quality agent versus medium quality agents with the highlight summaries, low versus medium with random summaries, and so on. And the ordering was counterbalanced. So what we wanted to see is whether highlight summaries improve people's ability to identify the better agent. So what I'm going to show you in this results plot is on the y-axis, you're going to see the correctness rate. So did people get the right agent? So a random guess will just give me 50%. And I'll separate it to the 3 different comparisons because some of them are harder than others. So for example, the low quality agent versus high quality agent is the easiest comparison because there is a huge difference in their actual performance. And then the colors will be for the different conditions. And what you see is that with highlights, the green bars, people were able to more frequently identify the better agent. And random summaries were usually better than random guess, but not always. And then just looking at the first trajectories was actually very misleading. So one interesting thing that we saw is that for the easiest comparison, so if you look at this bar, people were, when seeing just the first trajectories of the game, they were really bad at identifying the better agent. Actually, if they would just flip their answer, they would do very well. And we asked them to write textual descriptions of why they chose a particular agent. And what they wrote is that the high quality agent seemed to be taking risks. And because they only saw the beginning of the games, they couldn't really see that it's succeeding. So it just looked like it was getting too close to the ghosts or something, but they never got to see its capabilities. So this is just to say that a bad summary can be very misleading, actually. Okay, so far, what I showed you was how by taking important or interesting states and optimizing also for diversity in the summary, we could improve people's ability to assess the capabilities of agents. Any questions about that before I move to the second approach? All right, thanks. So the second thing, and this is a very recent work, like the results are from last week or something, is to look at agent comparison. So we had this task in the empirical evaluation that I just told you about, and that made us think, but if we really want to support users' ability to compare different policies and contrast them, is this summary approach really a good way? And we think that it might actually not be ideal because if you think about it, highlights generates a summary for each agent independently. So say that I want to compare Michael Jordan with LeBron James, I can create summaries of each of them, but that might fail to demonstrate where their policies actually diverge. And this could happen for at least 2 different reasons. One is that if both agents are fairly good, then the states they consider important might also be fairly similar, and they might actually behave similarly in those states, even if their policies are very different in other parts of the state space. So that's one thing, we might end up with very similar behaviors. And the second problem is that even if the 2 summaries do show behaviors in kind of different states, then we wouldn't know still, if I show you Michael Jordan in a particular situation, you wouldn't know what LeBron James would have done in that situation. Okay, so it might be kind of comparing apples to oranges. And this led us to think about what information should appear if we have a summary of multiple agents, because again, the naive solution is to just, this video will show a bit of LeBron James and a bit of Michael Jordan, but it doesn't really tell us what each of them would do in situations encountered by the other agents. And so in very recent work, and this is work with Yotam Amitai, who's a PhD student in my group, he tried to develop disagreement-based summaries. So the kind of key idea here is that instead of creating summaries for the two agents independently, I'm going to show users where the agents disagree, okay, where they actually make different decisions. And I'm going to use, in this case, we use the Frogger domain, which I'll get into in a second, but the idea will be to show what the agents do when they disagree. So how does this work? It's kind of similar to the highlights approach, but with slight differences. So again, we're going to run simulation of the agent, but this time I have two agents. So one of them is going to be what we'll call the leader agent. So we're going to follow the leader's policy. We're going to ask the leader what it does. And then the other agent, we're going to also ask it what it does in this state that the leader brought it to. But once they disagree, then we're going to let the agent that disagreed kind of diverge and go to its own route. And I'll show an example in a second. And we sort of record this disagreement trajectory. So again, the idea is that as long as they make the same action, we just keep following the leader. But once the other agent disagrees with the leader, we're going to let them diverge for a couple of states, and we're going to record that and save it as a sort of disagreement trajectory. Then we do that for a couple of states, and then we sort of bring back this agent that disagreed to where the leader is, and we do that again. Okay, so we try to identify states where they make different decisions and then see how they behave differently from these states and keep doing that over and over again. And then we'll need also a way, kind of similarly to the way we rank the importance of a state for a single agent, we're going to somehow want to rank the importance of a disagreement. And again, you can think of different ways to do that. For example, you can think of, if, for example, I disagree with Sylvia, you can ask, what do I think is the Q value for Sylvia's action? Right? And if the gap is large between how I evaluate, like how poor do I think Sylvia's decision is, then that's maybe an important disagreement. Or you can look at things like where these disagreement trajectories led us. Like, did we end up in totally different places in the state space, or what are the values of these states? So we just uploaded this to archive today, so you can look at the details there, but these are sort of some ideas on how to do that. And then finally, what we're going to do is reverse the roles. So we had the leader agent and the other agent that we queried, and now we're going to let the other agent lead, because the idea of doing that is that maybe, for example, Sylvia might go to different places in the state space that I wouldn't go to, and now I want to see what I would have done there, right? So I wouldn't get it if I just let myself lead, but now I need to also let Sylvia lead and see where I disagree with Sylvia. And so that's kind of the idea. And then we store all these disagreements. And again, we rank them and we show them to the user. And this time, what it ends up looking like is, I'm going to show you it here. So we're going to have a summary where as long as the two agents take the same action, so I have one frog here, so this is Frogger, it tries to cross the road and then cross the river. So as long as the two agents make the same decision, I'm only going to see one frog. And then once they disagree, once the other agent disagrees with the action and takes some other action, then I'm going to split them off. So now one agent is highlighted in red and the other in black. And I'm going to see what each of them does, okay? And follow them for a little bit longer. And now it's going to fade out. And then there will be another trajectory where, again, at the beginning, they take the same actions. And at some point, they're going to split off and go in different directions. Okay, so I end up with a summary that more directly shows where the agents disagree with each other. And again, to evaluate this, we took the agent selection task again, and here we used agents trained from a paper of Pedro Sicoria, I'm probably mispronouncing his name, where they used Frogger, and they created different agents already that have kind of different qualitative behaviors. And it's the same type of task that I talked about before. And this time we compare highlights with disagreements. And before we did that, we actually checked that highlights does work in this domain. So if we have agents that have a pretty significant gap in their capabilities, people recognize it with highlights. But if we have agents that have small gap in their capabilities, then they start having a hard time. And we wanted to see if disagreements summaries solve that. And what we see is that it did work. So what you see here in the green bars is the people who are shown disagreement algorithms and their success rate. And in red is the highlight success rate. So you see that with highlights, people kind of failed here. They did worse than random guess or kind of similar to random guess. And the direct comparisons in the disagreement summaries led them to better performance. And we tried to see what caused the better performance. And we saw that people were talking, so we asked them again why they chose a particular agent, and they did refer to this direct comparison. So they said, I prefer the path that some agent was taking, or I felt that agent E, which is the expert agent, was making slightly stronger moves and pushing ahead. So it does seem that having this sort of contrastive information, which is also in line with what we know from social science and how people do explanations, that this information of kind of what would the other agent would do actually helped people compare the agents in a better way. All right, so to kind of recap this part, so we saw highlights that created a summary by choosing states based on importance, and then this idea of disagreements, which is aimed to support the comparison of different agents. And I'll say that there are many other criteria that you might use for comparing agents. So in some other work with Ike Lage and Daphne Lifshitz and Finale Doshi-Velez, we looked at the ability to reconstruct an agent's policy. And again, in recent work from a different group, they looked at various interestingness elements, that's how they refer to it, things like the global or local minima or global maxima. So kind of the nice thing is that you can think of different heuristics for what you might want to highlight in the summary, and you can tailor that to the task, the user task that you're trying to support. Any questions so far? All right. So the last thing I want to talk about is, again, fairly recent work where we try to combine global and local information about agent behavior. And this work was led by Toby Huber. And the idea is to combine these global summaries that I just described with some local information. And in particular, in this case, we used saliency maps using an approach called the layer-wise relevance propagation. Won't get into the technical details of that here, but the high-level idea is that saliency maps are good for helping users understand what information the agent pays attention to in specific states, right? They show me where the agent is looking at in a particular state. And summaries hopefully are good for getting an overall view of the policy. So why not integrate both of them and try to gain the benefits of both approaches? And this led us to integrate them into what we call highlights LRP. So these are again summaries, but this time the summary also shows a saliency map that highlights the information that the agent pays attention to when it's making a decision. Okay. And again, we did an empirical evaluation to try to see what are the complementary, hopefully, benefits of the two approaches. And in this study, we had 4 conditions. So one thing I want to note here is that you can't directly compare the contribution of saliency map and the contribution of a summary, because if you show a saliency map, you need to decide for which state to show that. And that's already a major decision. So the way we try to evaluate the two things is to vary the two dimensions. So for the global information, we have either random summaries or these highlight summaries. And for the local information, we have with or without saliency maps. So we're going to have random summaries without saliency maps, highlight summaries without saliency maps, and then random summaries with saliency maps and highlight summaries with saliency maps. And again, the setup is fairly similar to what I showed you in the previous two works. So we had 3 agents that were different because of having different reward functions. So one was sort of a regular Pacman agent. The other was kind of overly optimizing for eating power pills. And the other one was extremely afraid of ghosts. So it got extra negative reward for getting close to ghosts. And then we had a between subject design. So about 35, 40 people in each of these conditions. And for the evaluation metrics, we will see the agent selection task again. And here I'm showing the diagram from Hoffman's work on how to evaluate XAI. And so you can think of the agent comparison task as sort of an appropriate trust task, because it shows whether you're correctly trusting or mistrusting a particular agent. And we also ask them a kind of mental model comprehension questions. And then we also had explanation satisfaction questions. So the agent selection task I've shown you already 2 times, so you know it. The retrospection task, this is a more mental model kind of task, is a task where we asked people to describe in text the behavior of the agent. And then we also asked them to select the objects, that the agent was considering most important. And then we also ask them for their confidence and to explain their decisions. Okay, so what did we find? So the good news is that we got more support for the benefits of summaries. So we did see that the summaries, the highlight summaries, resulted in improved performance in both tasks. So this is the retrospection task where they need to describe the agent behavior, and wherever you have plus S is with the saliency map, H is highlights, and R is random. So if you see highlights versus random, highlights led to a lot of improvement, and similarly highlights versus random here. And this is also true in the agent comparison task. So that's nice. So in 3 of the 4 cases, we get an improvement with highlights. The kind of more disappointing news is that adding the saliency maps didn't really lead to significant improvement. So if I compare this H bar to H plus S, right, don't really see a difference. The only place where there was a difference that was marginally significant was adding saliency maps to the random summaries. But it seemed like the saliency maps didn't really help much here, and I'll say a word about that in a minute. Where we did see an improvement thanks to saliency maps is in participants' textual strategy descriptions. So here we had independent coders that actually looked over the responses, and we saw an improvement for highlights plus saliency versus highlights that was, again, not statistically significant, but getting close. So that's more encouraging. And then when we look at the satisfaction, we again see an improvement for highlights versus random for the retrospection task, but no effect for the saliency maps, and also no effect in this case for agent comparison. So what did we learn overall? So again, the good news was that these results supported that highlight summaries were helpful. Like I said, the saliency maps didn't add that much, but we have some hypotheses as to why that was the case. So first, it might be hard to just view it in a video. You might need to pause it. But more importantly, when we look at participants' textual comments, we saw that they often misinterpreted the saliency maps. So for example, if someone saw that the agent was looking at many different places, they thought it was a good thing because they said, oh, great, the agent is taking into account a lot of information. What it really said is that the agent just didn't learn enough to kind of figure out what's important and what's not. And so it seems like there's both kind of a conceptual level here of do people understand what these saliency maps mean, and also more of an interface question of maybe how to show it. So we think there is potential because we think of it as sort of complementary. If the summaries show more about the intentions, like what the agent wants to do, then the saliency maps say more about the attention, but seems like needs more work to get it to work better together. Okay, so to summarize, and then I'll try to leave some time for questions. So again, this kind of high-level idea was to show the behavior of agents in a range of scenarios. And again, I said I'll get back to it. So when I talked about not being able to directly compare this to saliency maps, what I mean is that there are a lot of works about local explanations that then ask people to predict what the agent will do in some other state. And it seems from our studies that it's very important for which states you show the local information. So that's something that might be useful to consider. And kind of looking forward into next steps. So like I said, we still haven't really figured out how to combine this local and global information, and maybe we need to look at different local explanation types to integrate with, or maybe do saliency maps better. As I said, this idea of comparing agents, this was kind of from the last couple of weeks, the results. But I think the more high-level question is optimizing summaries for a real user task. So thinking about what the goal of the user is, and then try to tailor the explanation for that. And another newer direction that I think is interesting, and we're just starting to look at, is having something more interactive. So far, we only created these explanations that are sort of automatically generated, and we show them to the user. But what if we give the user an opportunity to sort of interview the agent? So we're currently running kind of initial exploratory studies to understand what people want to ask, what types of questions, and try to think about how we can enable that. So that's it. Thanks to all the collaborators, and thank you. And if there are questions, then I'm happy to answer.
Thank you very much, Afra. It's a very good talk. I enjoyed the talk. I think we have a couple of questions in the. So the first one is from Anna Lukina. Did you notice that the agents learn to pay more attention to places where they should not go? So that's the question.
So we didn't really, I guess in this case, we didn't try to really analyze, I assume she's referring to the saliency maps and the agent's attention. So our goal here was not really to check what the agent learned, but to see if it helps people. So we actually haven't looked at it sufficiently. We did see that the agents that were not trained in a good way were kind of more spread out in their attention.
Okay, so next question is from David Smith. So another way of summarizing a policy is to abstract the policy by removing variables, which results in coalescing states. One strategy is to remove variables that reduce the expected reward of the policy the least. Have you considered an approach like this?
So we haven't actually, but that's an interesting idea. So what we did try to do in another work is to try to use machine teaching approaches and to see what states, if I give them to an inverse reinforcement learning algorithm or an imitation learning algorithm, enable to reconstruct the policy. So that was sort of a more computational criteria than a heuristic, but we haven't tried that, the removing states and that's, or removing features, but that seems like an interesting direction to try. And I guess in general, when I use the word summary, we're sort of, it's kind of in in NLP, they have two types of summaries. One where you just extract important sentences, and this is more like this kind of summary. So we don't really give a, I don't know, conceptual description of a summary. We just show kind of a subset of states. So a different approach might be to try to generalize a bit more and not necessarily just show what the agent does.
I think we can open the questions to ask directly. Maybe I think Margaret also has a question, so she can ask directly.
Hi, yeah, thank you for this interesting talk. Ofer, this was wonderful. One thing I wanted to mention is that we've gotten so much mileage out of some work that Brian Lim and his colleagues did a while back called intelligibility types.
Yeah.
Okay, good. I see that you're familiar with it. And so you've done a lot of thinking about saliency, which would classify as an input type under the LIMS categories. So, and now you're thinking about adding other types. Are you thinking about it in the limb types terms? In other words, are you thinking about adding output types, model types, those kinds of things?
So yeah, we looked at this work recently, and when I talked about at the end about this interviewing agents ID, so the first thing we're trying to do is actually try to see if this intelligibility types framework, how does it extend to sequential decision making? Because I think it was mostly used for supervised model, and now you have other questions about the reward function, about the transition function. So we are thinking about it. It's super preliminary, but yeah, we're definitely looking into it. And I think we're trying to pay more attention. To be honest, I think when we started, it was just like, this seems like a cool idea to describe the behavior, and we weren't really user-centered in our thinking. But since then, we've done more reading and thinking, and hopefully yeah.
Nice. We have used it in a sequential domain, the game playing set of actions. So yeah, I'll post a link to a paper or two along the way. Yeah.
We have time for one more question, maybe.
There is David that wanted to ask a question.
So thanks, Ofer. This is a terrific talk. Really enjoyed it. And it was really cool to see how you've adopted the paradigm for evaluation that came out of the DARPA program that Robert Hoffman and friends put together. So I'd love to talk more about that. But I found myself thinking about narrowing in the right information. So for example, and I may have missed this, two agents' decisions, their actions may differ and thus divergence occurs, but might not have had much impact on the reward. Or it may be that the reward function isn't quite capturing everything, and we really want to look at, say, landmarks. So for example, something that takes place in the middle of a basketball game that doesn't impact the score immediately may be really important, like somebody getting injured or something like that. And I was wondering what your thoughts are on that.
Yeah, so we were debating that, and we have some ideas. We haven't tried all of them yet, but so one problem is that I think in many interesting cases, the reason that the policies will be different will be maybe because the reward function is different, especially in domains where it's not clear. For example, in healthcare, right, you might want to have a more aggressive treatment or a more conservative treatment, and then kind of assessing how important it is might also be different for the different agents. So currently, the things we tried was this thing I mentioned about how do I evaluate your action and how do you evaluate my action? And the other thing that we ended up using in the user study is if we kind of diverge for several states, and this relates to what you said about the impact, then where do we end up? Because if you turn right and up and I went up and right, then it doesn't really matter. So we tried to say, what's the value of the final states they reached if we integrate both our value functions? So I sort of average how you think about it, but I'd be happy to hear more ideas on how to do it better.
Another time, maybe. Thank you.
Yeah.
So thank you, Afra. So any other questions? I think we can have them in the Rocco chat or even in the Zoom.
Sure.
Or maybe Afra can later answer.
Yeah.
Afra's research is very interesting. It's very much related to my own research as well, and I also have some questions.
Great.
Yeah. So
yeah.
Sylvia, do you want to?
No, I suggest I will share with everyone again the link to the chat so that we can continue ask question remotely and go ahead with the session. Thanks a lot for the presentation. It was really interesting, and I also find a lot of similarities and overlap with what I'm interested to do.
So I think we can take a quick break around, I think, 3 minutes.
Yeah, we have 3 minutes for a quick break, and then we will start with the presentations.
Yeah.
Kathal, if you want to start your screen sharing.
Yeah.
Or ask. Okay. Thanks, Ofra. Lovely to see you.
You too.
Thanks for your talk. It was great.
Thanks.
Hey, Ofer, do you have a minute to talk?
Yeah.
So I was wondering if you found the evaluation strategy that Hoffman and friends put forward to be very helpful. It looks like you did, but I was just kind of wondering if you saw any limitations of it.
So I think it is very useful. I think it ultimately probably right for each task and each domain, it's, I guess, a bit different, right? So we had in the Ichikai workshop, we had a talk from Simone Stampf. I don't know if you know her work. So she talked about, and I think, on how we need to kind of consider who's the audience, right? And what are they trying to achieve? So I guess it's hard. So a lot of people asked her in her talk if we can standardize the evaluation, and she was like, you know, and I kind of agree with her that we probably can't really. I think it's a very useful framework for thinking about different types of evaluations and also the intelligibility types work, which is probably less familiar to the people in the AI. Yeah.
Sorry, if you don't mind, I have to interrupt. We have to start our first session of papers in counterfactuals, and the first one is with Kathal. Take it away.
Okay, thank you. Hi, my name is Cathal Ryan. I'm a PhD student in University College Dublin, and I'm also working within Vistamilk. Vistamilk is a leading research centre in Ireland who have a major focus on precision farming. And today I'll be taking you through how we were able to work alongside stakeholders at each step to build and develop a decision support tool that we use to predict mastitis infections alongside input on which features might be seen as actionable or confidence building for the farmers. So what is mastitis and why is it a big deal? So these type of infections cost billions of US dollars globally each year on dairy farms. So the main causes for these type of infections include swelling in the udder, and then also changes in the color of the milk. So this can be seen in the milk samples on the lower left-hand side. So I suppose most of you have seen at least what milk looks like. So the left-hand side looks like a healthy milking, and then the other ones are mastitis infected milking. So you can see a different color in the milking or lumps. And then the main way for testing of this is through somatic cell count, which is the idea of the amount of white blood cells that are present within a milk. And this shoots up dramatically when a infection occurs. And then also, due to less skilled labor on farms, it is resulting in infections becoming found too late. So farmers aren't being able to do as much to help the cow. And this is resulting in cows becoming more infectious or the cow just can't become healthy for a long state of time. So what our approach was, so firstly, we developed a mastitis risk prediction system in the hopes of predicting if a cow will become infected with mastitis within the next 7 days, or if it will become healthy for the next 7 days. And then this was an end-to-end system with input from the stakeholders throughout the design and build process, because we wanted to bake this the whole way through for the stakeholders, that they had input in every step of the way. And then the explanations of predictions are created using features that are actionable and also build confidence in the end users, which we'll talk about later on. And then the system also needs to perform at an accuracy level approved by stakeholders, because there's no point in us being able to create explanations or reasonings on a model that just doesn't classify infections at a high enough level, because farmers just won't use it. So throughout the project, we got feedback from our stakeholders. So this included surveying farmers to ask what they would request as minimum accuracy, both with regards to infections and also healthy milkings, because obviously we're looking to classify infections, but we also want to classify when a particular milking will be healthy for the next 7 days, because otherwise the farmer just won't use it, because they will see in their mind that they'll be better at doing it by themselves. And we also received input from a leading veterinarian in the UK who works on mastitis prevention on the minimum time needed for farmers to help predict the cows. So if we need to be able to tell the farmer at least 4 days before the infection occurs at a high enough level, but we can only tell them at 3 days, well, then that's not going to be any help to the farmer either. And then we also received feedback on which features are actionable for the farmers and the confidence in each feature using input from the stakeholders. So our risk prediction model, so we use data from 7 different dairy farms around Ireland from the time span of 2010 to 2019. And then on the left-hand side, we can see a graph of where each of the 7 different farms were located. Most of them were located in the south of Ireland, but this is just simply because this milk is also located in the south of Ireland. And it also contained information on over 2,300 cows. And the data contained information on different aspects of milking, such as the total amount of milk produced each day, and also details of mastitis infections, such as when and how many times a cow got infected with mastitis. And then for our actual model, our prediction model was trained using a gradient boosting classifier, with the 2 different labels being a milking being staying healthy for the next 7 days, or a milking becoming infected within the next 7 days. And then you can see on the right-hand side how well our model does as we get closer and closer to an infection. So we can see that even at 7 days out from the infection, we're able to get just over 60% of infections correctly classified. And then this thankfully increases as we get closer and closer to the day of infection, with it just stopping at about 80% at 1 day before the infection. So we took this and we went to farmers and asked them what they would feel as being a reasonable accuracy. And they came back to us with saying, even if you were able to find 70% of infections at some stage before they occurred, that would benefit them, that would help them in some way. And thankfully for us, we were able to do that even at 6 days out for them from the infection. And then we took this and we also went to the leading veterinarian in the UK. And they came back to us and said that if you were able to tell the farmer that this particular cow could become infected with mastitis, even like 12 hours before the infection occurs, that would allow them that would allow them to even just move the cow to themselves, or the farmer just to look more closely on that particular cow. So on both of those kind of tasks, our model exceeds both tasks greatly. So for the counterfactual explanations, the main idea of how our counterfactuals are created is through the idea of nearest unlike neighbors. This is portrayed in the picture to the left, which shows an example of trying to find the best counterfactual for a particular input. This idea is largely based upon work done by McGrath and Wachter, who demonstrated a way in which making counterfactuals which are as close as possible to the original input while being of the opposite class label through the use of linear programming that allowed for constraints and bounds from other external inputs. So these are just some examples of our counterfactual explanations. So we can see here that it shows the feature that were changed, the amount changed by the feature, and then also the difference in the prediction score, with the values in the brackets being from the counterfactual. And then also we try to maximize the amount of changes within any reasoning that was created to at most 3. This is just because in literature it's kind of widely noted that anything above 4 or 5 features being changed hinders the actual outcome of that when you give that to somebody else. So we try to keep it as low as possible, while also hopefully being able to change the prediction score as much as possible. But obviously the features, the counterfactuals that we've seen previously would not be what we would hopefully give to farmers. So we would change this and using SMS system or an application that would be able to give alerts to the farmers every 2 to 3 days, with saying cow 42 received the probability of being infected in the next 7 days equal to certain such and such, and then we would give them some examples of how this could be higher or lower. And then so we have been talking about actionable and confidence building inputs a good bit throughout the talk, but actually what are they? So actionable features, these were features that the farmer would be able to change in some way on their farm. So this could be likes of total milk produced. This is seen as actionable. So the idea of adding this into a reasoning would be able to help the farmer see that, okay, this cow is seen as being affected, but if I was able to reduce the milk by such and such units, then this cow might not be seen as being infected, and I can actually do that within the next 2 days. So hopefully that actually changes something. But then the other type was confidence building. So this is, for example, somatic cell count, which was not seen as actionable, but instead was a feature our focus group thought would build confidence in the model. So this is because somatic cell count is one of the features that farmers would regularly use as being a major impact of when they would see an infection being coming up.
3
so
minutes.
if we were able to see we're able to use reasonings that used features that the farmers actually believed in, they might be able to build trust in our model and actually use it more and more. So to evaluate this, we got a small group of farmers and interviewed them about a product. So we asked them different questions like if they use any tools like this currently on their farms. Unfortunately, none of them actually do, but they do use other features and tools like this. So they would mainly use it for the likes of breeding. So trying to choose the best bull for breeding purposes. Yet even though they said that they don't use tools like this for mastitis infections, they said that with our accuracy and also the idea of adding reasonings and explanations onto their probability of our predictions, they would see it as greatly beneficial. And then we also asked them how confident they are with machine-driven predictions. Mainly with the breeding purposes tools, they just kind of take it as given. Whatever the tool gives them, they kind of believe it outright. But this is mainly because that tool has been around for 20 years or so. So they'd be less likely to do that with something that is newer, so the mastitis infection tool. But then the addition of the counterfactuals or the reasonings, they said would greatly benefit them to using them. And the tools that they have right now just aren't up to the same standard. So the conclusion, so there are many pieces in the literature that provide actionable features, but to this point, not much work has been done on the idea of including features that could build confidence on the stakeholders in a model. So that was one of the major focuses of this project. And then also the decision support tool was built from end to end with continuous input from stakeholders to help make sure it was best suited for them. Because in the end, we want to be able to give it to them so that they reduce the loss from mastitis infections each year. And then we also exceeded accuracy thresholds provided by farmers while also giving reasonings on the predictions. And thank you. And there's a link to the paper and some further details from me as well. Thank you.
Thank you very much. That's outstanding. So my question is, if you are focusing on the features that you get the confidence, and the other one you said it was the one actionable. So can you get to the same predictions just with those?
Just using them, the predictions are good, but they don't quite get to the 75% one day out. They kind of get to about just over 70%. So you can use it, but you do get the added benefit of adding the extra features that aren't confidence building as well. So by only having it, you don't do it as well, but it's not that much worse.
All right, thank you very much. Any other questions? Sylvia, are there any other questions in the rocket? I don't see any questions. You can ask.
That I can see.
You can ask questions or type. In the meantime, let's get ready for our next speaker. And Catal, are you evaluating the reactions with the users yet? I missed that.
Yeah, so we only had the last focus group there at December. It was only a small group of, I think it was 8 people or so, but we would like to get to a bigger group, even to 20 or 30 people of farmers, not just within Ireland as well, to see if they have the same opinions.
But you want to do focus groups. That's your method of choice. All right. Very good. Any other questions? All right. If there aren't any other questions, thank you very much. Sorry. If there aren't any other questions, let's move on to the next presentation that is also related to, also within the group of counterfactuals. Saloni, take it away.
Yep. Thank you. Hi, everyone. I am Saloni Dash from Microsoft Research India. And I will be presenting our work on counterfactual generation and fairness evaluation using adversarially learned inference. Let me begin by giving an overview of what I will be talking during the presentation. So I will first highlight the importance of using counterfactual reasoning for assessing bias in image classifiers. I will then present our proposed method, ImageCFGen, which is a general framework to generate counterfactuals, and then use the counterfactuals to evaluate fairness of a classifier and also generate explanations for its decisions. I will then demonstrate our method on 2 data sets, MorphoMNIST and Syllab-A. Lastly, I will conclude by discussing our contributions and potential future directions of research. Right. I think all of us in the machine learning community know that machine learning models are biased. And many studies have shown that they exhibit bias while answering questions like who should be eligible for same-day Amazon delivery, or who sees ads for good housing. But this gets problematic when these models are used for answering questions like what credit score should a certain individual get, or what is the likelihood of person A committing another crime. For instance, let's take this example of a couple where the wife had a much better credit score than the husband, but the husband actually got a credit limit of 20 times more than the wife. And this instance was enough to launch a probe by the US government into the algorithms used to determine credit score limits for individuals. This is only one example of how models can be biased against individuals and how this can impact real people in the world. But we also know that these models can pick up on biases in the data set itself against marginalized and underrepresented groups. As a toy example, let's look at this data set where 14% of all females have blonde hair and 41% of all males have dark hair. But the atypical group or the underrepresented group is this group of males that have blonde hair. And here you see that only 1% of such people exist in this data set. So it's quite likely that the classifier will be biased in its decisions for this particular group. So we know that it is really important to evaluate the fairness of our machine learning models. But how do we do that? So the way forward is actually using counterfactuals. So what exactly is a counterfactual? Mathematically speaking, a counterfactual for a given system is the output of the system had some input xi been changed, but everything else that is unaffected by xi remain the same. Now, let's relate it to the credit score limit example that we saw earlier. If we had only changed the gender of the wife, keeping everything else like her income, the number of credit cards, or her age constant, then would she have received the same credit limit, or would she have received a different credit limit? That is what we would call counterfactual reasoning. To characterize counterfactual reasoning in the context of image classifiers, let's see how we can try to evaluate the fairness of any given image classifier. So the first and the simplest way of doing it is by using association. So let's say we have some classifier that predicts the label for a given face. For instance, say it predicts how attractive a face is. We want to check whether this classifier is biased against people with darker skin as compared to people with lighter skin. So one way of doing that would be to first see what is its output on a face with a lighter skin, and then compare that with its output on a face with a darker skin. But in this example, there's no way of knowing whether the classifier's output changed because the skin color was different or because some other attribute like this face is not smiling or this face has a different hair color, or whether the output changed because of those attributes. So this is where we use counterfactuals. So in an ideal scenario, what we would like to do is give the face of a person with a light skin tone, and then produce a counterfactual for that face where only the skin color is made darker, but everything else remains the same, like the hair color or the person smiling or the structure of the face and so on. So everything else remains the same except for the skin color. So this evaluation method is much more robust than association because we know that the only attribute that has changed in the image is the sensitive attribute or the attribute of skin color. And hence counterfactuals can be a good way of objectively quantifying the biases of any given image classifiers. Now I will show the method that we use to generate counterfactuals for images in a GAN-like framework. So assume we have a data set where you have the image X and the attributes of the image. So for instance, say we have a face and we have some attributes associated with the face like young and gray hair, for instance. Now in this setting, we assume that the causal graph is known. We know that young causes gray hair and both young and gray hair cause the image X. Now given X and A, we have encoder E and generator G. So what the encoder E does is that it takes the image and the attributes as inputs and tries to map it to a latent space distribution Z. And the attribute SCM actually learns the structural causal model over the attributes A. So for instance, for the attributes, we have the structural causal model of young causes gray hair. This attribute SCM would actually learn the structural assignment equations of how gray hair changes when young is changed. So based on that, if I change young, the attribute SCM will output the distribution of young and gray hair, or basically the counterfactual distribution over the attributes. Now, given the latent space variable Z and the counterfactual attributes, the generator takes those as inputs and then outputs the counterfactual image XC. Then in the bottom half, we have the reconstruction procedure, where we directly give X and A to the encoder E. It then again maps it to a latent space variable Z. Then Z, along with the original attributes A, is given to the generator, which then tries to reconstruct the original image as perfectly as possible. Now, the pairs of the counterfactual image and the reconstructed image are used in downstream tasks such as evaluating fairness of a classifier and explaining its decisions. Now, in our paper, we use adversarially learned inference to train the encoder and generator simultaneously. But this is a very flexible algorithm, and you can use any encoder and generator to actually
3 minutes.
Yeah. Okay, it looks like I'm running out of time. So let me just quickly give you our results. So for we generated counterfactuals for MorphoMNIST, which has the attributes of thickness, intensity, slant, and label. And then you can see the corresponding counterfactuals here, where here across B, C, and D, we vary the thickness. Across E, F, and G, we vary the intensity. And across H, I, G, we vary the slant. And across all the rows, we vary the labels. And we see that the counterfactuals change according to the attributes. And we also empirically evaluate the counterfactuals against a previously published method, DeepSCM. And we show that the counterfactuals are comparable to that method on MorphoMNIST. But the advantage our method has is that it uses a GAN-like framework. So it can be used to generate complex distribution like faces. So we generate counterfactuals for celeb A. And a few examples of counterfactuals are changing the hair color to black, or changing the hair color to black and changing the skin color to pale, and changing the hair color to blonde and changing the skin color to pale, and so on. And we see that the counterfactuals change according to the changed attributes, but the other attributes that are not dependent on it don't change. Finally, we use these counterfactuals to evaluate fairness of an attractive classifier, basically a classifier that predicts whether an image is attractive or not. And we also define a bias formula, and we show that with respect to this bias formula, this classifier is biased with respect to brown hair and pale, black hair and pale, blonde hair and pale, and negatively biased towards blonde hair. Finally, we use these counterfactuals to explain its decisions. So we see that pale skin is the most important attribute for classifying an image as attractive, whereas receding hairline is the most important attribute for classifying an image as not attractive. Finally, I would like to conclude by saying that our methodology is very flexible, so we can swap out the generator for a style-based generator to improve generation. And we can also use the counterfactuals for other downstream tasks like mitigating bias for the attributes that we have identified. We have actually implemented all of these future directions, and you can refer to our paper for the latest updates. Thank you so much. I'll take any questions now.
Thank you, Saloni, very much. Very nice work. Are there any questions for Saloni? you may ask.
Hey, Saloni, I've got a quick question.
Yeah, hi.
So thanks very much for your talk. Could you go back to the slide in which you were talking about the top 5? I guess it's slide number 15, the top 5 and the lower 5.
Yeah, sure.
I was looking at them, seeing whether I would agree with the top 5, and I found myself disagreeing with the second one, heavy makeup. And I was thought to myself, can you imagine expanding this approach to account for personalized preferences? Or if so, how could that be done?
Sorry, so am I understanding your question right? You mean that you think that heavy makeup should not be in the top 5, but this classifier thinks it is. So
yes, what I was saying is that I could imagine there'd be disagreements amongst the top 5, for example, and I was wondering if some personalization could be done in that regard.
Right. So I think the first thing I would like to point out is that these explanations are extremely dependent on the quality of the counterfactuals. So we actually, when we improved the generation and reconstruction as well, we actually saw the top 5 change a little bit. Like it's quite dependent on the counterfactuals themselves. But yeah, you make a good point that yeah, we haven't actually evaluated, like quantitatively evaluated whether these explanations are something that everybody can agree upon. And yeah, that's definitely an interesting thing that we can look out for.
Okay, thank you.
Thank you.
Are there any more questions?
I have a question.
Yes, go ahead.
Yes, sure.
We have 1 minute left.
Okay, hi Saloni, thanks for the talk. I just wanted to know, like, the attributes is actually given by you select it from the causal graph, right? When you are giving it to the GAN in the attribute S. So the heavy makeup is also given by it's a user defined thing also, no?
Right. So the syllabi actually comes with these attributes. So it's kind of like a supervised setting. Yeah, so the data set actually comes with
user defined, right? You actually try to generate the counterfactual based on the attributes given, right?
Yes, yes.
Okay, thank you. Thanks so much.
Yeah, thank you.
Thank you very much for your talk, Saloni. Let's have Sahil's slides now. Thank you very much. The next talk will be given by Sahil Verma. You are muted. Okay.
Okay. Can you hear me?
Yes, perfectly. Thank you.
Okay. So should I begin?
It's good.
Okay. Thank you. So hello, everyone. I'm Sahil Verma, and I'll be presenting the paper titled Generating Fast Counterfactuals for Black Box Models Using Reinforcement Learning. This is a joint work with John and Keegan, and this was done while I was interning at Arthur AI. So interpretable machine learning has taken strides in trying to explain decisions produced by machine learning models. Machine learning models can be broadly categorized into interpretable models like decision trees and rule sets, and complex models like neural networks and random forests. Most of the interpretability research has been trying to explain the decisions from complex models, either in a model-specific or model-agnostic way. Explanations are generally given in form of feature ranking in a global or local sense. Counterfactual explanations, which is the focus of this talk, is also a kind of local explanation. So what are counterfactual explanations? Counterfactual explanations are an emerging technique under the interpretability umbrella. For a given data point and a machine learning model, a counterfactual is a data point close to that original data point, but has a different prediction. It's helpful in answering questions like, what minimal changes do I need to produce in my features so that the loan request is accepted next time? So in the figure on the right, you can see there's an data point labeled X. That is an individual whose loan request has been denied by the bank. And there are two counterfactuals labeled CF1 and CF2, which are both valid, but they differ in certain properties, about which we'll talk next. We pointed readers to two recent surveys in counterfactual explainability, one by the authors of this paper and another by Karimi et al., to get an in-depth discussion and understanding of counterfactual explanations in machine learning. Counterfactual explanations have existed in philosophy from decades. However, in the context of machine learning, they were first proposed in 2017 by Wachter et al. There are certain properties that are desired from a counterfactual explanation, and that is what we have listed over here. For example, considering the same loan example that we discussed in the last slide, in order to be actionable, a valid counterfactual should not suggest changes to immutable features like someone's place of birth. It should also be close to the original data point. There is no point in suggesting an individual to increase their income by $1 million in order to get the loan. It also should suggest changes in a few features rather than suggesting small changes in many features. Prior research has also pointed out to the fact that counterfactual is generally more actionable if it's close to the training data manifold, and if it respects causal relations. Causal relations can be of the form something like age cannot decrease, or if you increase the education level, age will also increase. The last two properties listed over here are for a method generating counterfactuals, and such a method should be able to generate counterfactuals for black box models and generate counterfactuals from multiple data points after a single optimization, which we term as fast counterfactuals. So most of the prior research has addressed subsets of the desiderata that was listed on the last slide. Ours is the first approach which follow all the desiderata. We translate a counterfactual problem into an MDP, a Markov decision process problem, and use a off-the-shelf reinforcement learning algorithm to learn an agent that can generate counterfactuals from this for new data points sampled from the same data distribution. Thereby, the counterfactuals generated by our approach are actionable, they are sparse, they are close to the original data point, they adhere to the data manifold and respect the causality relations. They also work for black box models, and once optimized, they can generate counterfactuals for several data points, or fast counterfactuals. So here I give an example of an MDP formulation for a very simple data set consisting of two features A and B, both of which take integer values ranging from 0 to 2. So the state space consists of 9 states, which is the combinations of values of A and B, and those are represented on the figure on the right using these nodes. The action space consists of changing the values of feature A and B, either decreasing or increasing the values by an amount of 1. So there are 4 actions in this for the simple data set: A plus 1, B plus 1, A minus 1, and B minus 1. The transition function in reinforcement in an MDP gives given in a state, and an action gives you the next state. In this very simple setup, it's mostly obvious that given a state, if you take the action B plus 1, that will increase the value of the feature B. The reward function, which is the most crucial thing to train the agent, in this case, for this simple data set, there is no reward for reaching any state except for the state colored in green, which is 2, 2. For all other states, the reward is 0. However, each action costs a constant amount of -1, and therefore, when the agent is trained, it's supposed to go from any state and take the minimum number of paths it takes to reach the state colored in green, 2, 2. There are other things that we can incorporate in this reward function, which we'll talk about later. In this version of the paper, we have used discrete state and discrete action, and therefore used the most preliminary policy iteration algorithm to train the agent. So here's what the system looks like. You have a black box classifier for which only the predict function is accessible. You have the training data on which this classifier was trained. You have the actionable features for this training data. You have the causal constraints between different combinations of features of this data. You have a data manifold enforcer, which is a tunable parameter. So you can tune this to force the agent to be very close to the data manifold or a little far from the data manifold, or not care about it at all. That's a tunable parameter, and a discount factor, which is the gamma in a MDP, which which discounts the future rewards. These all go into and form the MDP, which is used by the reinforcement learning algorithm, any off-the-shelf reinforcement learning algorithm, to train an agent. When trained, if you sample a new data point from the same distribution, it will take and feed it to this agent, it will take one step. This one step will change one feature at a time, and therefore sparse counterfactuals. The updated point is fed to the classifier and checked if it's in the desired class. If it is, that's the end. You get a counterfactual. If it's not, you feed back the updated point into the trained agent to help it generate, to get into this loop until you are at a counterfactual or you exhaust the number of steps, which is a user-provided hyperparameter. So we performed preliminary experiments to verify the problem formulation using a German crate data set. The original German crate data set has 20 features. Since we are using the policy iteration algorithm, which would build a table for all the features and all its particular values, we had to reduce it to 6 features in order for the problem to be tractable. However, we ensured that the accuracy of the classifier on these 6 features was still more than 80%, which is the state of art on German credit. We performed a series of experiments with more and more constraints. In the first experiment, there was no constraint on any, all the features were actionable, and there was no causal constraint or data manifold adherence constraint. In the second experiment, out of the 6 features, 2 features were made immutable: personal status and number of liable people. In the third experiment, a causal constraint, age cannot decrease, was added. In the fourth experiment, another causal constraint, job, which in the German credit data set refers to qualification, cannot decrease. These are natural. In the fifth experiment, we added another constraint of being close to the data manifold with a varying value of lambda, which hugs you to the data manifold. Our metrics were validity out of given data points for how many of them could you generate a counterfactual, the path length, which is proximity, and average, how many steps did you need to take to reach a counterfactual, data manifold distance, which is how far you are from the data manifold for the entire path, and the time taken. In this particular case, thank you. In this particular case, the data manifold adherence was incorporated by using a k-nearest neighbor agent, k-nearest neighbor trained on the training data, German credit training data, and which returns the L2 distance from an input data point to the nearest point in the training data. So if that's L2 distance is lower, we are close to the data manifold. So these are the results. You can see there are two, with increasing constraint, you see this experiment number 1 to experiment number 5, the constraints are only being added. So it's an increasingly constrained environment. And what we see is there are 2 different trends. Validity decreases and average path length increases. And those are natural to happen. And we exemplify them using 2 specific data points in the next slide, which is here. So there are 2 specific data points here whose feature vectors are represented by 130341. And the second one is 0300241. In the first experiment, when there's no constraint on what feature you can change, the agent found it most rewarding to change the third feature from 0 to 1. Unfortunately, this is actually the gender feature, and it's most easy to change the gender from 0 to 1, from female to male, to get a loan or get to a credit-worthy side. From second experiments onward, this change is restricted, and therefore both the data points take a different path, which is of path length 2. For the first data point, after the lambda is made non-zero, it switches the path, but it's of the same length 2, and the average k-n distance, or that distance from the data manifold, becomes 0, and increasing lambda therefore on has no effect. Whereas for the second data point, after the lambda is increased beyond 10, the data point takes a different path. It has 3 steps, and when at the highest value of lambda, it's not able to do anything. It's not able to reach a counterfactual and still get a positive reward. So it's the agent finds it better to stay at the same point. That's what we have done in this. Our current research revolves around generalizing the algorithm to both categorical and numerical data types, developing algorithm that can translate any causal graph to constraints in an MGP, trying to learn partial causal graphs from time evolving data, and performing experiments to extend this to multiple data sets and multiple other kinds of constraints, and also compare this to existing work. So that's all. Thank you for listening. I'm Sahil Verma, and this is, you feel free to get in touch if you're interested in an internship at R3I this summer. And I'm happy to take any questions.
Sorry, I spoke at the same time as you did. I saw you finish. Thank you very much for your presentation, Sahil. Are there any questions for Sahil now? Well, while people are warming up, let me ask you something. You mentioned at the end that you want to learn the graphs, the causal graphs from time evolving that data. Is that what you said? How do you plan on doing?
Yeah, that's correct. So, so what we have seen till now, for in most of the counterfactual work, the causal graphs are either like the authors design themselves. For example, we design like age cannot decrease, or if you increase the education level, age has to increase. Like that is what we design. There's a natural to occur in a to happen in real world, but we would like to, if we can learn some of them from data. Although if you have a static data set, you cannot learn those things of a causal graph. However, if you have the same general trade data set, the same individuals over 2 timestamps, for example, the individuals in 2009 and 2015, then you can learn things like if someone increased their education level, their age also increased, things like that. So you cannot learn everything, but you can still learn partial causal graphs from data sets at different timestamps, although we are not aware of any such data set available at different timestamps. And if anyone in the audience is aware of such a thing, we'll be happy, we'll be thankful if you can point us to that.
That's very good. I'd love to hear more about that. Are there any other questions?
So I have a quick question. It's also related to the causal graph learning because my research is also around that area. As I know, there's like 2 particular ways of like learning the causal graphs, like from the observational data and also like from interventional data, right? So there are like different data sets for interventional data, right? So the most common way is from observational data because that's the data we have, because we can't actually do interventions to like make a new data set. So like in my kind of area, I'm doing causal learning in reinforcement learning. So it's possible to have a interventional data set using the agent's kind of behavior. But I wonder how would you like to learn a good causal graph? Like there are causal discovery methods that use observational data, but what is your like opinion in like these 2 data sets? So what are you planning to use, I guess, for the learning of the causal?
I'm sorry, I'm not aware about the interventional data thing. I'll look into that. But from this data set at different timestamps, I think we cannot learn for example, we will not be able to learn something like age cannot decrease. You cannot learn that from data pointed to the stamps. But what you can learn is a different thing is like if you increase the education level, age will increase. So it will be like a subset of what is a real causal graph.
Yeah,
May I suggest that you continue offline, please? We have another presenter.
Sure.
Thank you very much, Sahil, for your talk. Next presenter is Negar Stefanianian.
Yes.
Thank
you.
Hello.
Yeah. Hello, everyone. My name is Negar Stefanianian. I'm a PhD student at KTH based in Sweden. And I'm going to present this paper towards the interpretability of mixtures of hidden Markov models. So an outline of the presentation is the following: some motivation on clustering of actually sequential data and its interpretability using the mixture of hidden Markov models, So we want to measure and improve the interpretability of this model. And the problem is that previously no metric is defined to measure interpretability of HMMs or the mixtures of them. And so the objective is to measure and improve the interpretability of these models using the vanilla EM. The solution we propose is an information theoretic measure, entropy, and then we propose a regularized EM algorithm to further improve the interpretability of the transition matrices learned by EM. And in the results, we compare the interpretability of vanilla EM, a recently proposed method OM-HMM, and our method EM, our version of EM. So here's an example of clustering of sequential data, gene expression data, and you can see that along the x-axis, which is time, you can cluster this data into 3 possible clusters, expression level going up, down, or some has some more complex patterns. And so we choose the model-based approach, and we put aside the feature-based and deep learning ones, because the model-based approach has the advantages of being probabilistic, transparent, flexible in modeling, and we can have representation of variable dependencies. And so when it comes to handling sequences, which is our previous slide, it's very common to use hidden Markov models. So then the next question comes that if we have different HMM per sequence, how do we cluster them, and which sequence come from which HMM? So the answer is using a mixture of HMMs or M-HMM proposed in 1997. And this is the motivation of our work or our method. Here is the graphical model for the HMM. We see the variables in circle, and then the model parameter are the squares. And so we basically work with this parameter in our work, and it's called transition probability. And so if we extend the previous slide to this one, here is the model we actually work with, mixtures of hidden Markov models. And it's basically the previous slide, it's just that we have n different HMMs, and then we want to cluster them into k clusters. And so this purple new variable is added, which is Z, and is the cluster assignment or mixture assignment variable. And it has its own parameter pi, so that the model parameters are is theta and is updated with pi. So the vanilla EM for learning the parameters of an M-HMM is the following. We have some initialization for the theta, and then we repeatedly do the E and M step. When the E step, we calculate a Q function, and then in the M step, we maximize that function with respect to theta, which is all the model parameters. And in this work, as I said, the focus is on parameter A, which is the transition probability. And so the maximization problem looks as the following. And yeah, so the contribution number 1 in this work is that we propose to measure the interpretability by using entropy of Markov chain. And why using Markov chain? Because we think that transition matrix, the parameter A, can capture underlying state transition patterns in data. And why entropy of that? Because low entropy corresponds to that higher weights have been assigned to certain transitions. And then from that, it comes that we get transition importance and subsequently high information regarding the transition pattern, and finally high interpretability. So regarding the first contribution, which is the introduction of this measure, we use the following formula, H of C, which is already there. It's something there when you want to calculate the entropy of Markov chain. And it's basically the Shannon entropy. It's just that we add this mu to that and sum over all the possible mu. And the mu is actually the stationary distribution, which we always assume most of the time that the Markov chain is stationary, which means that the transition matrix is not changed after training a sufficiently long sequence. Right? So an example here to have an intuition is, imagine you have two transition matrices, and the left-hand side, we say is more interpretable with respect to state transition pattern, because you have this diagonal or self transitions, which is highlighted and has high probability. While to the right-hand side, it's not very interpretable because the weight is almost uniformly distributed and you cannot guess which transitions are more important. And so contribution number 2 is a method called informational MHMM or IMHMM. And this is the recap of the M step in the EM algorithm. You have this maximization problem to the left-hand side and the solution is to the right-hand side. And what we propose is to use a regularization, and we do that by adding a Dirichlet prior. And it's nothing strange. It gives a solution like this. You can compare this to the original term we have an extra parameter here introduced called eta. Now the question is, how can we encapsulate our belief of low entropic transition matrices in this formula? And here is the way we do it, which is we convert or reparameter here. And basically the last expression is the final solution. Instead of having eta, we have a function f deciding for setting weight for common transition versus not common transitions. And then lambda is the regularization hyperparameter. So f is basically an indicator function to allow for, to favor actually low entropic transition matrices. And then we have some results on two types of data set, biological data set and hand movement data set. We compare our IMHMM to the vanilla version, EM, and a recently proposed, again by us, called OMHMM. And we see that both IMHMM and OMHMM are in bold outperforming the vanilla version. But when it comes to here, the V measure is showing the clustering performance, but when it comes to the entropy, we see that the IMHMM actually outperforms.
3 minutes.
Yeah, so, and then, yeah, so that's basically it. And then we reduce the number of iterations, which is good. But it's for some data set like here, we do not perform well, and it's because the data is oscillating. And so to enforce low entropic values is against the nature of the data. So that's why it's not working for all types of data. And to summarize then, we have introduced the interpretability measure for MHMMs and a regularized EM for MHMMs called IMHMM, which we favor low entropic transition matrices, giving high interpretability. And to conclude, both OMHMM and IMHMM can decrease entropy of Markov chains without sacrificing clustering, but rather improving it. And to include some future work, one can solve the non-convex regularization in the original problem, which is more detailed in the paper, and also to investigate other metrics that can be examined, like the number of hidden states. Yeah, and here in the results, actually, we we just did the experiments for different numbers of states because we didn't focus on that part. Yes, and that's it. Thank you very much.
Thank you, Negar, very much for your talk. Very interesting work. Are there any questions for her? Anybody?
I have a question.
Okay, go on.
So hello, Negar. It's very interesting to see. Like, so it's the sequence clustering done by using the mixture of hidden Markov models, right? That's what I understood. And about the low entropy, like you use it to use the regularization, right? And the low entropy is to, you want to impose the low entropy or you want to diffuse so by the regularization, what you wanted to achieve there? I didn't understand.
So low entropy means that you can have more towards deterministic probabilities. So then you have,
it's a kind of peak. Okay, so you want to diffuse the predictions of the clustering, or you want to...
Yes, so the point is that we want to have the more diversity in the clustering by having the more deterministic probabilities.
So in the regularization, you have to give some kind of prior also there?
No, the prior is actually, I can show you.
Uniform or?
So here, everything is based on data. So based on data, you get this value which represent the most common transitions, and then it's automatically comparing to the other parts of the data, and then puts more weight when it's more common transitions. So the idea of prior was just to have a mathematically correct regularization. That's all.
And the convergence, there is any issue of convergence here for the algorithm or no?
So the convergence I haven't proved, but for different regularizations, sometimes, I mean, it's common that they converge or sometimes they don't. And I showed in this data set that if the data has a nature in itself, which is very oscillating and very chaotic and with high entropy, then reducing the entropy does not help. So then
in future work, you also suggested to make it as a concave convex programming, right?
Yes.
Interesting. Thank you so much.
Thank you.
Thank you. Could you please stop screen sharing, please, so we can have the next presenter. Negar, thank you very much for your talk. It was very nice. Next is going to be Elise. I will not try to pronounce your last name, Elise, if you don't mind. And okay, take it away. Elise, you're muted.
That's a good thing to not have. Hi everyone, my name is Elise Heddewijnen. That's how you pronounce my last name. I'm presenting to you from the Netherlands, and I'm going to talk about machine annotated rationales, which is a way of faithfully explaining text classification. So our initial goal in our research was to find parts of text that are relevant for classification. So we focus on text classification, and the dataset that we use is the IMDb movie review dataset that's enriched with annotated rationales by Zidane et al. And I'm going to talk about annotated rationales in a minute. So the classification problem is to find the polarity of a movie review, so it can be positive or negative. And we have two main focus points, namely faithfulness. So whether an explanation is according to the inner algorithm of a model, and the explanation quality. So whether an explanation is understandable and usable to a user. So annotated rationales. A rationale is a human, a natural language explanation for a given decision. And if you would ask a human to read a text like a movie review, then make a decision, and then highlight the sentences in this document that support his decision in a way of explaining his decision, then you would get annotated rationales. So in this example, you can see that the yellow highlighted sentences are rationales for a negative decision. So in our work, we try to find annotated rationales that are generated by a machine, and we call these machine annotated rationales. So a machine first makes a decision and then explains the made decision, and it's both done by the same model. So our proposed method, we were inspired by Brendel et al. They split their images into different chunks and then calculate a prediction over every chunk and then use all predictions together to form a final prediction. So we apply this to text documents. We split the documents into different sentences. Then we encode them using the sentence transformer BERT from Devlin et al. We determine the classification results for every sentence in the document. Then we use the average of all sentences to find the prediction, and the sentences that strongly contribute to the document predictions are selected as machine annotated rationales. So if you would plot all sentences in a document and their predictions, you would get a histogram like this. And you can see that the leftmost and rightmost sentences most strongly influence a given prediction. So if the original prediction is below 0.5, the leftmost sentences in this distribution will be machine annotated rationales. So what does the model look like? Our first model is called a bag of sentences. We use a convolutional network to stack all sentences on top of each other. Then there's a fully connected layer to calculate one value for every sentence, and then we take the average of all sentences to find a final prediction. One alternative to our model is the bag of rationales, which looks like this. And instead of using the average of all sentences in a document as the final prediction, we use the average of all selected rationales as the final prediction. Evaluation. We looked at it from a qualitative and a quantitative perspective. So for the quantitative perspective, we look at faithfulness. We use the comprehensiveness and the sufficiency metrics that are used by De Jong et al., which basically, as simply said, calculate the average difference when removing all annotated all rationales from a document and by removing all non-rationales from a document and then measuring the difference in prediction. So as you can see in table 1 on the left, the bag of sentences model does not receive a very high comprehensiveness score, but the bag of rationales does. Well, they are both equally faithful. And we also compared our machine annotated rationales to the annotated rationales. So we compared our rationales by machines to rationales by humans. And we do this through the Jaccard index, precision and recall. As you can see on the right table, the F1 score for both models is similar, and the Jaccard index, which is the overlap of two sets, is not very high for both models, but it is higher than the random baseline that we used. So for the qualitative evaluation, we used the user evaluation, where users were presented with a set of rationales that were generated by either a human or by a machine. And based on these rationales, users could make a prediction or select, I need more information, meaning that the explanation is not complete enough to base a prediction on. Yeah, and this is a blind study. Users did not know where the rationales were coming from. So in our evaluation, you can see that we made a distinction between correctly and incorrectly classified documents. You can see that users made similar predictions as the model did when the model made the correct classification. And when the model did not make the right classification, rationales were often marked as incomplete. So the users could not make any sense of them. And our annotated rationales were mostly correctly interpreted by the user. So my conclusion and discussion is that machine annotated rationales can be found using a bag of features approach. They do show some overlap with the human benchmark of annotated rationales, but not very much. But they can be useful as explanation because users could make the same prediction based on only the rationales, as I showed you in the previous slide. Some questions that were raised was whether faithfulness can actually be measured by comprehensiveness and sufficiency, because both models are equally faithful, but the scores do not tell us that. And also another question was whether the focus should lie on faithfulness or interpretability, because a faithful explanation might not be usable, but an interpretable might also not be useful. Okay, this was what I wanted to ask you. Are there any questions? I have to tell you.
Thank you very much, Elise. Any questions for Elise? Elise, before anyone else asks something, I was wondering, it was not very clear to me, the whole idea of the being useful or not useful to the user, to the receiver, right?
Yeah.
Or making sense versus not making sense. How is that defined? How is that, how can you tell that?
Well, I can show you in the reuser evaluation. So if you would give a user or receiver like a set of rationales that's an explanation, and the user cannot come to a conclusion based on only the explanation, then the explanation is indeed not an explanation because the user can't use it to come to a conclusion. So yes, does that answer your question?
I think so. Thank you. Anybody, any other questions? Anybody else have any other questions? Well, all right. If not, then we'll thank Elise for your presentation. And if you please stop screen sharing, we can get ready to have Fabio. Screen
Hi, here I am. Can you hear me?
Yeah.
Great. Hope you can see my screen.
Yes, we can. Thank you.
Okay. Okay. Can I start?
Yes.
So thank you. I'm Fabio Mercorio from University of Milano Bicocca, and I'm presenting this work on symbolic approach to generating contrastive explanation for black box classifiers. So the introduction and motivation of this work is quite simple. So imagine to have a machine learning based system deployed, and then after a while, you need to retrain for keeping the system updated with the data that also changes. So the underlying learning function of the new trained model might change the system logic with respect to the past. And these, as a consequence, may produce unexpected outcomes that might contradict past prediction without any reason for the user. So just imagine, for being more concrete, just imagine a system that has machine learning model that perform a single label text classifier. So C1 is a model trained in once at a time on a dataset D1. And of course, it just has to assign a label over a set of labels, predefined categories C. So new dataset arrives, and you have to retrain this model accordingly on a new dataset. Some questions that a final user may ask could include: can we estimate to what extent the new classifier C2 classifies the new dataset currently with the previous version? Why does the criteria used by the previous model result on a given class, but the new one, the new trained one, does not classify on the same class anymore? And can we use natural language to summarize to the final user the differences between two instances in the time between the two models? So the second question specifically can be seen as a contrastive explanation of the form YP written time Q, and specifically it's a T-contrast explanation that is ask for the property of the model over time. That is, why does an object A have a property P at time T, but the property Q at time T first? So this is exactly our case in the example of text classifiers. That is, why does a class at time T has these characteristics, but have another characteristics at time T first? Explanation, we generate explanation at the global level. So for the model as a whole, by generating the surrogate model. So this process has been very well classified in a very recent survey by Burkhardt and Huber on Gyre that clarified very well this part. So what kind of explanation? Global for the model, model agnostic, T-contrast explanation. So our approach, compute model agnostic global T-contrast explanation from black box text classifier, basically performs two tasks. The first one is to encode the differences in classification criteria using the surrogate model into binary decision diagrams, and then estimate to what extent the new model is different with respect to the previous one. The methodology is implemented within a tool named TraceX, and here in this paper we tested it on 20 group benchmark for making it reproducible and also usable in the community. So the main idea is that one. Imagine to have two classifiers, C1 and C2, and imagine just for representation purposes, the first one encodes the logic that we can express through a Boolean formula, A and B or A and C. And the new version encodes a new formula that removes a variable and adds a new variable, that is not B and C or D, sorry. At the right part, you have the BDDs, better the arrow BDDs, that basically is the representation of the formula in a compacted and reduced way. So we compute two new BDDs, B major, B minus. The first one basically is negates the first and the second, whilst the second is basically the first and negates the second. So intuitively, the idea is that the firmer encodes the reduced path that the second classifier used to classify the instances that have not been applied by the first classifier while classifying the first dataset. And exactly the contrary for the second, that encodes all the path that the second classifier used to classify the new dataset, but the previous dataset did not use for classifying items on D1. So then, having these two BDDs, the idea is to compute the SAT, so all the true path over the B major, that is the BDDs that encodes the difference between the two, such that there were either false in B1 or not present at all. So in this case, we can see the new formula added a new criteria, we may say, that is B0, C1 has been added by B2 as a true path. So this means that now the new classifier is not using A anymore for classifying. That is a discarded feature. And another path is B0, C0, D1. sorry, B0, C0, D1, another path that still does not depend at all by A anymore. On the other part, SAT B minus are all the true path. So true path means all the path that leads to the positive class. So classifying on that class that were either false in B2 or not present at all. So in this case, that is, yeah. So in this case, we have A1, B1, that was a true path added by B1, but now removed by B2. So what we are encoding here is a classification rule that the new retrained model is discarding whilst the previous model was using. So the idea of the approach is just this, to have two data sets, DT and DT1, a black box classifier, text classifier, of course, we will see at the end why. And the system performs this step twice. So take a text classifier, a set of document and a class, and for each class, get the prediction for the class, compute the solution for the global surrogate fitting problem. So the problem basically, we use the formulation of this survey. So basically they perform an optimization problem that aims at solving, mimic the behavior of the predictor, maximizing the fidelity. And we added a constraint that is the model complexity bound, that is to allow the explanation to be comprehensive to the user. For example, in this case, we are using decision trees, so the user can specify a maximum depth of the decision tree to make it comprehensible. Then it synthesizes the BDDs, as we see in the previous slide, and then this explain steps just compute B measure and B del, as we seen in the slide, and just a couple of indicators that gives a raw estimate of the amount of classes that changed the most. And we add also a module that transforms BDDs into natural language. As said, we use 20 news group, and this is publicly available. We trained using many supervised text classifiers. All of them, of course, reached high accuracy, and the fidelity we choose in this case to show you the one that gave the better fidelity to explain as we are explaining the surrogate. At the end, the system TraceX produces this figure. On the x-axis, we have the classes of this data set, and we have both the add and del as we seen before, and also an add and del normalized over the whole number of paths over all the classes, just to have an idea of the how to say, the differences intra-class and interclasses.
3 minutes.
Yeah, I'm concluding. What you can see here is the class that changed the most in terms of add and deleted path. We select this just to show you an example. This is what the TraceX produces as output. That is a sort of text that summarizes the changes. In this case, for example, is interesting because it's saying that the new version added 3 classification rules. None of them requires political atheists. So the path you can find for all the paths not political atheists. And then each of them adds those paths. The same for the del. What is interesting here is that Bill, that is strange as a feature, of course, is the name of one of the major publisher in the data set, in the new data set, whilst Kate is exactly the name of the most active user in the previous data set. What this means, basically, that even though the accuracy of both models are very high, anyway, the system, in some sense, understood as a feature importance the source of the post. And here you are catching these as a criteria, not just as a feature relevance, but in a path, in a set of rules. Those explanation helps in observing the classification logic, in understanding why the new training model is changing after retraining through natural language. A Spearman correlation test we performed confirms that the indicators R and L are not related with the FMU score with training models. So this means they estimate the behavioral change in handling new data and gives new insight that is not related at all with the quality of the training. In the related work, I don't have any time to go in depth, but of course, many papers are working on contrastive explanation, T-contrastive, model agnostic, but as far as we know to date, the most important ones partially lack one of the following characteristics that we include in our paper. Concluding, so TraceX is a model agnostic approach to globally explain how black box text classifier changed the criteria over time, so T-contrast, using BDDs. We evaluated on a benchmark showing the fidelity is good, because we explain basically the surrogate model. And the Spearman correlation test revealed that the indicators are novel in the sense that they not correlate with, are not related to the quality of the model in terms of accuracy, let me say, of the training. We are working on extending TraceX because it is limited now to text classifier, also to tabular visual. We are going to realize it as an off-the-shelf Python tool for the whole community that could be improved. And we are working on applying on a project that basically inspired this job, because we are working on a EU project classifying 1 million vacancies over countries and languages. And the problem is to be coherent between retraining model over time. So that's all. Thank you.
Thank you, Fabio, very much. We have a question here for you. How does the control of the depth of the decision tree ensure the comprehensibility of the explanation for the user? The person says, maybe I missed something, but how did you measure this aspect?
Of course, this is a parameter that the user is free to specify. To date, we use 5 to 10, and we basically perform a sort of simulation. So the system starts with the lower one and then improves until a sort of threshold on the fidelity is reached. So the idea is that basically the user can specify which is the value, let me say 85%, 90%, that is acceptable as a fidelity to reach. And of course, this can provide, if you use the maximum depth, you will have a fidelity very near to 1, perhaps, but you will pay a very low comprehensibility because the rules we showed before could be very, very, very very dense. So this is a threshold that the user can specify.
I'm sorry, Silvia, was that your question?
Yeah. But I was wondering, how do you measure that? Because when you, there is a lot of talking around building the minimal decision tree, and I think this concept is very far from a human way of thinking. I mean, if you I understand if you reduce the depth of the tree, you have less accuracy, but how do you know, if you are new to the task or to the system, which is the best depth and which is the best compromise, and how do you ensure that the output is actually understandable for the user? So how did you measure this aspect?
Yeah, there is no, or at least we don't use any measure of understandability, let me say, that would be interesting to add something that in some sense give an estimate of to what extent the output is understandable. to date, the only measure you can use is to what extent the output is mimic the original model, that is the fidelity. Okay, this is a good point. Perhaps we may think, you know, to translate, to embed within decision tree something that recommends a sort of threshold.
Thank you for the answer. Great talk.
Thank you, Fabio, very much for your talk. Next, we'll hear from Hendrik Bayer.
Yes, do you see my slide?
Yes, I can.
Perfect. So let me try to get rid of this. Okay. Good afternoon, everybody, or whatever time it is for you right now. My name is Hendrik Bayer, and my talk today is about a paper I wrote with Michael Kaisers on our first steps towards explainable Monte Carlo tree search. First off, motivation. Why do we care about explainable MCTS? We've actually proposed explainable MCTS or explainable search in general as a research challenge at the HKI workshop this last month. So please do check out our vision paper there, titled Explainable Search. Just as a small excerpt from this, the basic question we're interested in is how can a search-based agent explain its behavior? This could be a chess AI or other board game AI, as in the examples I will be giving today, but also a self-driving car or a search and rescue robot or a trading bot or any other sort of AI that is using search, meaning online planning. Search algorithms like MCTS are at the heart of many recent breakthroughs in AI, such as, for example, AlphaGo and AlphaZero famously. So in our vision paper, we've described a variety of interesting challenges around this, and today I'm presenting our first steps towards tackling some of them. We're working on a tool set for explainable MCTS here, a set of basic building blocks for MCTS explanations, which is what I'm going to very briefly lead you through 6 different techniques today. But first, a little bit of background for all of them. So how exactly can we derive explanations from a massive MCTS tree that contains information collected from thousands or even millions of simulated possible plans and possible futures? The basic idea underlying the following techniques is this. When you explain a search decision to someone else, for example, a move in a game of Go, you typically say something that sounds like this. If you make move A, you'll strengthen the connection between these two groups. But if you make move B, you both help connect your groups and threaten an invasion here. So that's the stronger move. So what you're doing there boils down to 2 processes. In the first process, you simplify the enormous space of possible futures in the game to a few that you think are most important. So you explicitly discuss only moves A and B, for example. In terms of MCTS, you pick a subset of the tree to use in your explanation. For example, that representing moves A and B or their resulting states. This is what we mean with these red highlights on our slides, and we call it tree simplification. And in the second process, you then decide what to say about that subset of the tree, about A and B. And you do that by comparing the expected consequences of these moves, which for MCTS means you compare the subtrees that you've built under move A and under move B. We do that here by using a set of outcomes or scenarios that we assume to be intuitively understood by the explainee. In our example, connecting your own groups is assumed to be known as a good thing by any Go player. And having a territory invaded is assumed to be commonly understood as a bad thing. And now we simply look at the probabilities for those scenarios in all trajectories we've simulated following move A, which is the green subtree here, and following move B in the blue subtree, and we compare them. This is what we mean by highlighting subtrees in green or blue on these slides, and we call it subtree summarization. We can't walk the explainee through every possible future, but we can abstract over possible futures by speaking of the probabilities of good and bad scenarios. The crucial point about scenarios is that when we're using MCTS with Monte Carlo simulations, we can treat all scenarios as random variables and compare their expected values under different plans. For example, what's the expectation of capturing your opponent's rook, given that our chess game trajectory tau starts with making move A versus the same expectation when we start with move B? This is exactly what happens when we're doing subtree summarization. And now I'm finally getting into the actual explanation techniques. There are 6 of them in total in 2 groups, 3 techniques that can be used to explain a search after it has already happened and is a done deal. Even though they can be interactive, they will not change the search outcome anymore. And 3 techniques enable the user to give feedback to the search algorithm, making some progress towards the idea of explanations as a two-way street, as a collaborative effort between AI and user that we're describing in more detail in our vision paper. We start with the first group that we call post-hoc explanations. We've designed these as potential answers to 3 very basic requests for explanation. 1, why this action? 2, why not this other action? And 3, but what if this happens? So the first technique for answering the question, why do you recommend this action? The action that was preferred by the search, here marked in red. Our answer to this has 3 parts. The first part is presenting what in games is called the principal variation, or PV, which is just the most likely short-term future found by the search, explicitly shown over the next couple of time steps. For example, until the value estimates become too uncertain to be sure. So, for example, after doing a search from this state in the game of Connect 4, on the right, it's the actual text-based format we're using because we don't have any graphical interface yet. We walk the explainee move by move through the near future that MCTS expects to be most likely, using text templates to make statements about how certain we are about each move happening. I don't have time to go through this in much detail now, but I can answer questions later about it if you're interested. And the second part of the explanation is a general overview of what MCTS expects to happen in the long-term future. This means simplifying the tree to only the current state, represented by the root node, and then summarizing over all of the tree by giving the expectations for relevant scenarios. So for example, in our Connect 4 position, we can use all possible groups of 4 disks as scenarios to summarize in which way the game is likely to be won by which player eventually. Yellow is currently 41% likely to win with the group shown in the top left, while it's looking rough for red with no group having more than 1% winning probability. We can also show expectations for other scenarios in the form of heat maps. For example, here, the probabilities for yellow or red making the eventual winning move on any given square of the board, which also helps the explainee understand where to focus attention. Or we can show the probabilities of owning each square of the board at game end, where green and red here stand for the 2 players. Which scenarios are most interesting depends on the domain. In chess, for example, we could also plot a heat map of the chances of each piece to get captured, or a heat map of where both players' pieces are likely to go eventually, all averaged over all simulations that we've done in our search. And then, now that the overall situation of the game with the short-term and long-term expectations is clear, we can directly answer the user's request in the third part of the explanation, or the only part if the overall situation has been explained before already. A contrastive explanation why the recommended move is better than all alternatives. So this means simplifying the tree with the recommended move and its alternatives, and then comparing summaries of the subtrees under them, respectively. In our Connect 4 example, concretely, we can show that the recommended move for yellow increases the probability of the winning group in the top left by 26% compared to yellow taking any other move. And it decreases the chance of red connecting the 4 disks in the top right by 4%. It's clearly a good move for white, yellow in this case we call it. We can also demonstrate that the recommended move makes it 14% less likely for yellow to win on square d4, but 27% more likely to win on c3 eventually. So this focuses attention again, and so on, for any scenario we think is relevant. But the question, why not this alternative action now? If the user thinks the blue action should be better than the red one, we can again show the most likely near future in detail, now comparing the principal variations through both contrasted actions. And we can again show the expectations for the distant future by summarizing over 2 subtrees, now the ones under the 2 contrasted actions, the fact action and the foil action, so to speak. And finally, The question, but what if this happens? Asking what MCTS would do in a specific possible future. For example, in this highlighted state, we've implemented a simple set of commands with which to navigate the tree. So users can request why or why not explanations anywhere in the tree, not just at the root. Limited, of course, by the amount of data at that depth. Moving on to the collaborative explanations now, we're also proposing 3 variants, 3 ways in which the user can request additional search by giving their own thoughts as input back to MCTS. For the question, what if you think more about this action when the user feels that there's a promising action that MCTS simply hasn't explored enough? MCTS will do some additional search in the direction it was asked to, which might or might not result in a change of the recommended action. And then, for example, if it did, and we found that the user was right, MCTS explains this change by showing the most likely near future in detail, comparing the old and new recommendation, and by showing its expectations for the distant future, again, by summarizing the subtrees under these 2 actions in order to explain which one is better. For the second question, what if you knew that the opponent will do this, or what if you knew that this will happen in domains without opponents? We allow the user to specify constraints that they think will hold true in possible futures, and that MCTS might not have known about in its search. The entire search is then repeated, respecting the user-specified constraint, possibly leading to a different recommended plan. And if it does, again, the old plan and the new plan are compared in terms of the near future, step by step, and in terms of the distant future, by summarizing consequences of the old plan and the new plan, now in 2 completely different search trees. And last but not least, we also came up with a truly collaborative search mode in which MCTS is given permission to proactively ask the user for input whenever that would seem helpful. When a future state is visited very often by the search, for example, it can pause the search and ask the user, this state seems important for the plan. Do you have an intuition what to do here? And if the user, yes, thank you. If the user then answers, yes, I do, the user suggestion can be built into the search from here on out as a soft or hard constraint. If the user answers no, then MCTS continues normally. And finally, after MCTS and the user together have come up with a new plan, the new plan and the old plan are again compared the same way we've seen before in terms of the near future and in terms of the distant future to explain to the user the influence of their choices. So that's the end of my talk. Thanks for listening. Any questions?
Thank you, Hendrik, very much for your talk. Yes, we have a question. Tata, do you want to ask yourself?
Hello, can you hear me?
Yes.
Yes.
Yeah. Hi, Hendrik. Nice talk. I had a quick question about how much of the explanations you looked at really tie to the search algorithm itself versus the underlying domain theory. Like, so for example, the questions you were asking on why this node had this action taken and not these other ones, would the examples you had more or less depend on what domain is working on, like the rules of the game, the constraints, etc. As I would imagine, if you are looking at the search process, it would also depend on the actual search algorithm selected, and they would have different ways of picking things. And on the same domain, they will have different responses. I wonder if you have thought about how to untangle those issues.
Yes, we've thought a little bit about this because in explainable planning, there's this idea that you can have plan-focused or model-focused or algorithm-focused explanations, right? And it seems that when you do online search, it's hard to disentangle them because the tree, all explanations are based on what we know from the tree. And that contains, of course, explanation that contains information about the plan. For example, that we think in this future state, the opponent will probably make this move. So that's a plan-focused explanation that we can give. It also contains information about the domain. So the human user might have simply overlooked that certain actions are possible or might have misjudged the probability of certain events happening, and also those will be in the tree. And you can also necessarily, your explanations will also be algorithm dependent because the tree contains information such as we have
traversed this state 517 times, and the average reward was 0.73. And actually, even if you start the same MCTS algorithm on the same problem twice, you will get slightly different trees as outputs. So you can never give a completely algorithm independent explanation. So yeah, they are, in a way, they are integrated, and we're trying to shift the focus a little bit more towards the direction that seems to be interesting for the target audience that we have in mind. For example, for me as a developer, for debugging MCTS and so on, I want the most algorithm-focused explanations. But in this talk, I gave examples that were completely projected onto the domain instead, because that's what a user who wants to play the game will probably want to know.
Yeah, exactly. I was also thinking about the same case. Like if the developer, you want a different kind of explanations.
Yeah, you want to know the statistics in the tree, actually, because they will show you that something maybe went wrong. But for an end user, in that sense, it's very difficult for them to understand what the statistics of the tree mean. That's why I came up with this translation into these verbal templates that say things like, oh, I think this is the best move, but if there's no statistical significant difference to the second best move, then it will say, well, this one also looks very good, you know, and things like that. So it translates it to more the kind of language that I would expect from people.
Thank you. We have one more question from Pat Langley. Pat, you want to ask?
Sure. So this is great. I'm not convinced it's limited to MCTS. Does it generalize to other types of search methods?
I hope you're not convinced. That's good. It's in the strict sense, the way we've implemented it so far, it's limited to search methods that are based on simulating trajectories through the domain. So sample-based search, basically. And there are other approaches than MCTS. I've just focused on MCTS here because it's a very prominent framework.
Yeah, I got that. But any system that does look ahead will effectively could collect the statistics you're talking about, even if it's not MCTS, and you could use similar kinds of ideas to give insight.
Yes, you could. Well, when you use something like alpha beta search, for example, it's a bit more tricky because you visit every state only once, and you do quite a lot of pruning to avoid visiting as many states as possible if you can prove that they won't influence the move choice at the root. So it won't be as easy to collect expectations in the same sense, but of course you will still have a tree, you will still have subtrees of it, and so you can try to do that. And in fact, sometimes I'm thinking about switching to much simpler search algorithms than MCTS for toy examples to maybe approximate a little bit better how humans might have thought about the domain, but I find that still very challenging to model, to come up with any sort of user model for how users might think about the next move. They might think one move ahead only or two moves ahead. They might have completely different valuations in their mind. So sort of trying to approximate what the user's thinking.
No, this is great. I just wanted to make sure people were, MCTS is great, but it's not the only game in town, and your ideas aren't limited. I don't think they're fully limited to it. So, but carry on. It's very good.
Thank you, Hendrik, very much for your presentation and your answers. We'll hear now from Vinil. It will be the last talk in this session. Take it away.
Hi, everyone. Can you hear me okay?
Yes.
And is my screen displaying fine?
Yes, it is.
Perfect. Okay. So I know I'm keeping you from the next virtual session, so I'll try to keep it brief and quick. My name is Vinil Nagisetti, and the talk that the work that I'm going to present is titled XAI GAN, Enhancing Generative Adversarial Networks via Explainable AI Systems. This work was done in collaboration with a few others. Laura Graves, Joseph Scott, Vijay Ganesh, we're all from University of Waterloo, Canada. So why should you care about this work? Generative adversarial network, or GANs, are a class of deep neural networks that are used to learn a target distribution and, more importantly, generate instances that were previously unseen from that distribution. GANs have been used successfully in many applications, like generating images, music, text, other forms of data. However, a notable limitation of GANs is that they require a lot of data for training. Collecting data is a non-trivial process. It requires time, effort, money, and is considered a major bottleneck in machine learning research. So as a consequence, there is a need for making GANs more data efficient. GANs at a high level are made up of two networks, a generator and a discriminator. And a common analogy used in explaining GANs or in understanding GANs involves thinking of the generator as a forger. So this forger is trying to generate forgeries of some real art. And there is a detective, that's the discriminator network. And this detective is trying to distinguish between real art and forgeries. So each of these networks, each of these forger and detective, try to get better at their role. There is this adversarial relationship between the two. The forger is trying to better fool the detective, while the detective is trying to better distinguish real art from forgeries. And after many learning steps, as you will, in an ideal scenario, the forger can generate forgeries that are indistinguishable from real art. And that's what we hope the generator will do after GAN is successfully trained. Now, these aren't really people, they're neural networks. It's a little more complicated than that. So let's take a deeper dive into generator training in order to better understand what we're doing. So we can think of generator training in two steps. The first step is a forward pass, and the second one is a backward pass. In the forward pass, we sample noise from a latent distribution, prior distribution, that's Z. This is given to the generator, which generates data based on this, that is G of C. This is given to a discriminator, which makes a prediction, that's D of G of C. And all of this is produced, given to the loss function. So the loss function essentially computes this error between the prediction as well as some true label, and produces this single value loss, which is a real value. Now, in the backward pass, what we do is we're computing the parameters of the generator in order to minimize this loss. In order to do that, we perform gradient descent and in particular backpropagation. So we calculate the gradients of the discriminator with respect to that loss. We use that to calculate the gradient of the generated instance. That's this here with respect to the loss. And then we use that to calculate the gradient of the generator. And finally, we update the generator parameters. Now, knowing all this, we ask if it's possible to provide richer corrective feedback to the generator, as opposed to just that single real valued loss information. And if so, can this help us improve GAN learning? Now, to look at how we could provide richer corrective feedback, we look towards explainable AI systems. Traditionally, XAI systems aim to make AI models more interpretable to humans. And that's what most of the works here, the previous presentations were, that's the angle that they were looking at. However, in our view, we're using these XAI systems in order to provide richer feedback to GANs, to the generator in particular. There's different kinds of XAI systems in the context of deep neural networks, such as DeepShap that uses a game theoretic based approach, LIME that approximates a local model, and saliency map that uses backpropagation in order to compute this feature importance. For our purpose, we treat an XAI system as a black box that takes in the discriminator as well as the inputs to that discriminator, G of C, and assigns feature importance to each of the features of that input in the form of an explanation mask M. And this mask is in the range of 0 to 1. A value of 0 means that that feature was not important in the prediction, whereas a value of 1 means that feature was very important towards this prediction. So taking this explanation mask, we incorporate this into the algorithm of generator training that I described before. So here, the forward pass is still the same, where we're computing loss. However, in the backward pass, we query the XAI system using the discriminator as well as the input G of Z and produce this explanation mask M. And this explanation mask is combined with the gradient information in order to produce a focused gradient information to the generator, which uses that to better update its parameters. So the intuition here is that the XAI guided, this XAI system acts as a guide, shaping the gradient descent in such a way that focuses generator training on those input features that the discriminator recognizes as important, compared to standard GAN that in which gradient descent is simply moving towards minimizing some loss over space. In order to evaluate our this idea, we implemented XAI GAN, and we used 3 different versions of it using 3 different XAI systems, so saliency, LIME, and SHAP. For each of these, we compared against standard GAN with the same architecture, same parameters, and trained them on MNIST and fashion MNIST datasets. And for all of these models, we used 100% of the data in one setting, as well as 35% of the data in order to simulate data scarcity in a separate setting. And for all of them, we evaluated the quality of the generated images, and we used Frechet inception distance or FID score for that, as well as the training time, the time required for training. Now our results are given in this slide here. Towards the top, we have the FID score results. And on the left of this graph, we have the score for MNIST dataset. On the right, it's for fashion MNIST dataset. For both of these graphs, we split the 100% data towards the left and 35% data on the right. And standard GAN is given in blue, whereas each of the XAI GANs is given in its respective color. So for FID scores, the lower the score, the better the quality, because that means that that image is, or that generated set of images are closer to the data set, the images from the data set, or the inputs from the data set. Now, a few observations. One, XAI GANs show an improvement in image quality as using FID score over standard GANs. And this is particularly true using the LIME XAI system that we found. In some cases, we've got up to 23% improvement in FID score. And this improvement of XAI GAN over standard GANs is more prevalent when the data is scarce. So in 35% data, the improvement is higher percentage-wise compared to 100% data. Another interesting point is that the scarcer the data, so 35% data, the poorer the overall quality for all GANs, which makes sense because GANs require much more data in order to produce good results. So while XAI GAN, in our experiments, has shown to produce better FID scores, better image qualities, this comes at a cost, and that cost is the amount of time required for training. So there is overhead because of the XAI systems. So as you can see on the bottom, the table here, we've aggregated the scores for each data set for each of the GANs. And on average, the XAI GAN using saliency takes about twice as long as standard GAN for training. And this gets worse.
3 minutes.
This gets worse with SHAP and LIME taking about 10 to about 35 times as much time required for training. While this is pretty steep, we believe there may be settings where this is still advantageous. For example, a lot of GAN research focuses on improving image qualities and also on handling data scarcity. So in a setting where training time is not as important, this can still be useful. Further, with improvement in efficiency of XAI systems, this amount of time required to train can also go down. So in standard GANs, while all the feedback originates from this one value, this loss, there are many ways that this feedback is used. For example, several GANs vary the type of loss function used, such as Wasserstein GAN. Several GANs vary the selection of the optimizer, and they do all of this to control how GANs learn. We believe that XAI GANs will allow for greater control because you can not only vary the things that standard GANs did, you can also vary the XAI feedback in different ways. This can probably be done by selecting the type of XAI system, so varying the parameters in that XAI system, or combining that XAI feedback with the gradient information in different ways in order to better control how GANs learn. To conclude, we introduce a class of GANs called XAI GANs that leverage XAI systems to provide richer feedback from the discriminator to the generator and to enable more guided training and greater control. In our experiments, we show that there is a trade-off between data efficiency, training time, and quality of generated data. We believe that the XAI GAN using saliency provides the best value out of the systems we compared. We note that XAI GAN can use many types of XAI systems and allows GAN with different architectures and different objective functions. So this should allow it to be applied to many scenarios. That's all I had here.
Thank you very much, Neil. We have Zico as a question.
Hi, Vinyl.
Hi.
Well, the work is very straightforward and very interesting to me. And I had, so straightforward means like you just generate the mask from the explainable AI systems, and then you also just, do the Hadamard product with the gradients accumulated in the generated images, right?
Exactly, yeah. We mask that, yeah.
And then you just try to guide it based on those responses. So my question is, while you are taking the discriminator, so is, previously while you are doing the GAN training, you pre-train the GAN before incorporating the explainable AI?
No.
Or it's always end-to-end process?
It's an end-to-end process. So we compare end-to-end.
So that's the beginning of the iteration. So we don't need any pre-training of the discriminator or anything, right?
So you don't need pre-training, but in our experiments, we found that a better approach would be to pre-train the GAN for a few iterations and then almost turn on this XAI guided feedback. And that's because initially the discriminator does not have does not understand the task at hand. So once it trains for a few epochs, then it's better. The explanation is a little more helpful.
Okay. And also, like when you are using the explainable AI systems, so you take the discriminator and you incorporate that discriminator architecture with the explainable AI system, or you just use a separate architecture for the explainable AI system?
Oh,
you use the discriminator as the next, and on top of that, I mean, like how you do that? I mean, like for the discriminator, you also have one output, right? But in this case, you change the outputs, or while you are incorporating with the explainable AI system? That's my question.
No, we don't change the outputs. We use the XAI systems for like a binary classification, and we use the discriminator directly.
In previous, you use some kind of fully connected layers or something like that?
Yeah, we used both fully connected neural networks for discriminator as well as convolutional networks, because discriminators are binary classifiers.
Yes.
Directly. There was another scenario where we used a separate classifier, and we found some good results, but intermittently. So we ended up just using discriminator for the explainable system.
Okay. I think I will go through the course. Thank you so much. Thanks.
Sure.
Thanks a lot.
Well, I also had a question, but we're running out of time, Daniel. I'll catch up with you later.
Sure.
Thank you very much for your presentation and your answer. And I'd like to thank all other authors for doing such a great job in this session. And it is now 1 p.m. Eastern. I'm not sure what time it is in PST. And we'll now go through our virtual networking session where you will remain here. And from that, we'll have a lunch break as well. And Sylvia.
Okay, we wanted to do some pool with Prashant just to know each other a bit, but we have some technical issue from this side. So we will ask question on chat, and if you wish to reply, you can also raise your hand. Prashant, do you want to ask the question?
Which question? I forgot.
No, we wanted the first like to understand the audience, like where do you come from, and what's your motivation for joining the workshop. We can write down some option, and you can vote by raising your hands, or if you prefer to discuss or do other activities in these 10 minutes, it's nice. Unfortunately, we don't have the possibility to meet in person, but it would be nice to have some like talk.
Yeah, so we wanted to do a poll, but unfortunately Zoom isn't cooperating. So we wanted to know the background of the participants, mainly which area they're from. Maybe they're broadly in the AI side, or maybe they are broadly in the cognitive sciences, and maybe from the HCI side. So we wanted to get a feel of the distribution of the participants.
Who is from the AI side?
Maybe they can raise their hands.
And if you want, you can turn on your camera so that we can all see each other.
Okay, let me check. I'd imagine like most of us are from the AI side. You can see.
Thank you, Nazanin. Nazanin wrote on chat. You can talk if you are here.
Yeah.
Yes, hello, I am Nazanin. I'm from Umeå University, Sweden, and working on XAR research group. My supervisor will give a presentation in this workshop later. I'm mainly working on the explainability in the affect computing domain. That's a short brief of my.
Okay, Mark Kane raised his hand. It's for replying to the question, or do you want to say something?
No, I was just saying, as I was making dinner, that what side I'm on. But then I thought I had to raise two hands because I work both in AI and in cognitive science. So, and I didn't have a second hand, so I left my hand up.
That's great.
Sorry about that.
Maybe it's interesting to know who's working on cognitive science side, or maybe in social sciences. Maybe they can raise their hands. Oh, I can see Shane. Shane, do you want to say something about your work? I think you're giving a presentation as well.
Right, I'll be presenting tomorrow. You know, I don't think anyone who's purely social science side of this is purely social science, but I'm involved with the DARPA XAI program, studying the psychology of explanation, especially in the context of AI algorithms. And a lot of what we're doing is in my own lab is studying how people explain things to others, how we can build algorithms that do this and take that approach.
Yeah,
I guess I'll talk more about that tomorrow.
Yeah. Thanks, Shane. Who else? Maybe if anyone wants, they can speak.
There's Arish.
Harish, do you want to?
Yes. Hi. I'm a PhD student at University of Illinois at Chicago, and we have a paper at this workshop, and my advisor, Gyuri Turan, will be presenting it tomorrow. My interests are in explainable AI. I come from the AI side, although I have dabbled in HCI a bit. I did work in HCI for the first couple of years of my PhD research. And our current work at the workshop is, however, not directly hard AI. It comes from the philosophical foundations of explainable AI. So that's another field that's of interest to us as well. And I particularly work in generating explanations for problems on graph neural networks. Yeah.
Yeah, that's great. Thanks, Harish. Maybe we can ask who's working from the HCI side as well. Maybe they can raise hand if there are any people. Nope, seems like we are missing.
I could speak a bit, could I?
Yes. Yes.
So just to say that we're sort of trying to work, I guess, from both directions, both from doing AI techniques, mainly on post hoc explanation, where we're looking at factual, counterfactual, and more recently semi-factual explanations. But we're trying to do that hand in hand with doing user evaluations as well, which of course is turning out to be the hard bit of the work. But we're, our group is sort of half and half between the psychology, cognitive science side, and half between on the AI side. And then I sit awkwardly between both, pretending to be an expert in neither. But that's essentially what we're trying to do. And we have a sort of fairly big program in the sense that we have about 3 or 4 people on either side doing that work.
Hey, Mark, I got a quick question for you.
Yeah.
Do you see a large increase in the amount of publications and efforts that involve conducting HSR studies for explainable AI in recent years?
No.
Oh, you see.
This is currently, I'm currently trying to do a review where I'm looking at just that, like what's the percentage essentially of studies that do some sort of user evaluation in the XAI context. And it's very like the review I did a year or so ago in the CVR area, where we found about 1% of sort of published papers were doing any sort of user evaluation. I think the percentage might be slightly higher is my sense so far, but it's not an awful lot higher. So 3 or 4% maybe. And I think one of the things that worries me is the evaluative side of, assessing the techniques, specifically, I was just looking at counterfactuals, and now we have something like 50 plus papers on counterfactuals. So there's 50 plus different techniques. We've evaluated very few of them, I'd say 2 or 3, and very few of them have been evaluated competitively. And that means we're in a situation where we're creating all sorts of techniques with bells and whistles, and we have no idea whether people are interested in any of those bells or whistles. And that concerns me, I guess. And I think the community should be concerned about that too. So that's my rant.
Thanks.
Yeah, definitely. I think there's a real need to incorporate user studies for XAI work. So I think we are up for the lunch break. So we'll meet at 10:45 PST after the lunch to a great talk from Tim Miller. So exactly in 35 minutes. So see you all after 35 minutes. Thank you, everyone.
Bye. Thank you.
We can begin in 1 minute. Is Tim there?
Yeah, I'm here. Yeah.
Okay, so I'll introduce you. So it is my pleasure to introduce Professor Tim Miller as the next speaker in the workshop. Tim is a professor of computer science in the School of Computing and Information Systems at the University of Melbourne. And also he's the co-director of the Center for AI and Digital Ethics. Tim's primary interest lies in the area of artificial intelligence, in particular explainable AI and human AI interaction. His work lies at the intersection of artificial intelligence, interaction design, and cognitive science and psychology. And his areas of expertise includes artificial intelligence, software engineering, and technology innovation. And also he has experience in developing novel and innovative solutions with industry and defense collaborators. But maybe for this audience, Tim is perhaps best known for his seminal paper titled Explanation in Artificial Intelligence Insights from the Social Sciences, where he surveyed more than 200 papers in cognitive science and social sciences related to explainability and explanations. This paper has been very influential in my research, shaping my own research agenda and also other research directions in explainability. Tim has also co-organized many XAI workshops, for instance, the workshops at HCI and many others. And Tim is also my PhD supervisor. So thank you, Tim, for making it this early. I think it's around like 5:45 a.m. in Australia, same as my time. So over to you, Tim. Thank you.
Thanks very much. And let's move this over here. Yeah, so thanks very much for that introduction, Prashant. And yes, I hope my work has influenced Prashant because he's my own student. So I hope he did it. He did take a lot on board, and I've been very lucky to supervise Prashant, and he gets quite a bit of show at the end of this talk. Towards the end, I'm going to talk a bit about his research on explainable agency. The title of the talk is one I've probably given this in a couple of different versions over the last few years. And one was, it was the title of a paper I gave in a workshop that David organized in 2017, I think, here in Melbourne at ICHCAI. And this is kind of then an update of, I proposed this kind of research agenda, and this is what I've done since that in the last 3.5 years since then here. So it's Beware of the Inmates Running the Asylum, or how I learned how to stop worrying and love the social sciences. So the bottom parts are plugged from a sort of, I don't know, I've taken that from a Peter Sellers movie, but the top part I'll explain a little bit for those who haven't seen this talk before. So let's see if I can go down. Okay, so yeah, so I'm going to I'll explain what I mean by inmates, and then I'll talk a bit about the scope of explainable AI, how I see the scope of explainable AI, which is not the way that I think some other people see it, especially in the interpretability community. And I'll talk a bit about infusing the social sciences here, about why I stopped worrying and love the social sciences. And then I'll talk quite a bit about some work that Prashant's done as part of his PhD thesis in explainable agency on model-free reinforcement learning. And so the inmates thing comes from this book here, and this is a book by Alan Cooper that's now 15 years old, called The Inmates Are Running the Asylum, and then the subline is Why High-Tech Products Drive Us Crazy and How We Can Store the Sanity. And so what Cooper was saying was the inmates running the asylum were software engineers, and he was asking the question, why is software so bad? We train lots of people on software and we get bits of software and we completely dislike it. And he made the analogy he made the point that the problem is that really software engineers or software developers are designing software to work for themselves. And they're not really figuring out how the software should work for other people. And they're making an assumption that the way they want the software to run is the way that everyone else wants it to run. And that's not really the case. And he called this, it's kind of like the inmates running the asylum. You give people this control and they'll design something for themselves and not for you. And so he presented a whole lot of what is basically interaction design techniques or HCI techniques from the literature to help restore the sanity. And if you haven't read this book, and if you're familiar with, for example, the idea of personas in design, this was the first time anyone had proposed it, this book here. So it's been quite influential in that community. And it's a great book. And I think anyone should read it if they're into developing systems for other people at all. And it's quite a seminal piece of work now in HCI. And the reason I wrote this, the title of this paper in 2017 was because at the time I thought this is the way XAI research was going. I was reading a bit of stuff coming out of XAI, and lots of people were kind of throwing around ideas. They were, sort of experts in whatever technology. So they're experts in a particular optimization technique, and they were saying, "Oh, I'm an expert in optimization, therefore I'm going to come up with techniques for explainable optimization." But the point I was trying to make in that was, yeah, when you're the world expert in optimization, you're probably the worst person to judge what a good explanation of that is if your intended audience is people who aren't the world's expert in optimization. And probably what you can do here is work with other people who are good at these types of things. So interaction designers, but more importantly, or just as importantly, people like cognitive and social psychologists who understand how people consume explanations and use them. And so I think in a later paper, I kind of proposed this simple figure here of when we talk about, I hope you can see my pointer here, when we talk about explainable AI, I sort of think it fits here in this subfield that's called human AI interaction, right? Which is, I mean, it's a really abstract view of it could be artificial intelligence as one group, cognitive and social science is the other, and HCI is the third group. And there's a whole lot of people who were working in human AI interaction, but at least in 2017, not many of them were working in this explainable AI subfield. It seemed to be just a problem for AI people to solve. And I was sort of trying to drag people from here over to this way and get these people involved. And I've had, success in my own work getting a cognitive scientist and a social scientist at Melbourne Uni to work with us, and a couple of people from our HCI group to work with us on this topic here. But since then, I think it's changed a little bit. There's lots of people, there's workshops at HCI, people are really interested in it. I saw Shane Muller here earlier. There's people from cognitive and social sciences are interested. And people from what I would say is the human AI interaction community have become interested well. So it's become a much richer tapestry. But in that paper, what I kind of pointed out is this observation that explanation's triple pronged. And so first off, it's a kind of cognitive process. When we talk about explanation, we say, well, you explain to yourself what's going on. And really that's the kind of end goal of all explainable AI research, is to have somebody be able to explain to themselves why something happened. But sometimes you need to give them some help in order to come up with that explanation themselves. And the second thing is an explanation is a kind of product, right? It's some statements that you might give somebody here that it's this thing and it's this thing, and that's the kind of product side of it. But between humans, it's also a social process. It's this interaction that goes back and forth. You never have something where you say, oh, why did that happen? And someone just gives you an explanation that works. There's usually some back and forth, and that holds for explanations between humans and machines as well, as we'll see a bit later here. And so this kind of triple process, I think in explainable AI, we were focusing at that point, and probably still are, focusing a lot on the product, about, oh, what's the explanation for something. But don't forget these other parts here that you're explaining to somebody who has to link together these things themselves, and you're doing it as a process. And so this whole thing, we use this word explanation, or that's here to mean these three different things, but really explanation is just answering that why question. That's the sort of, I guess, the high level definition of explanation. But in sort of 2016, I sort of came up with this thing. Well, really this is just philosophy, cognitive science, social psychology. Surely they've studied this problem already quite hard. And some of the work I was doing at the time that was basically explainable AI, but we didn't call it that. We were using a lot of social psychology and collaborating with the social psychologists. And I thought, well, surely someone's looked at this. And I was lucky to then get to go on a sabbatical in early 2017. And I thought, well, I'm going to find some papers in this area before I go, and I'm going to read them when I get there, and I'm going to spend the first month just reading up on this literature. But within it, after 3 months, I'd kind of, I hadn't yet exhausted all the literature, but I'd read what I thought were the most seminal bits of work here, and thought, well, I have to share this with the community, because actually, as it seems, probably this social science community understands explainable AI already better than we do. They don't understand how to write the algorithms, but they probably understand what's needed. So let me give you a bit of an example of why I think infusing the social sciences is important. So what I want you to do is get ready with the chat window to give me an answer here, and we'll see some interesting answers, because I'm giving you a bit of a test now, but it won't be on the final exam, don't worry. Okay, so imagine that a patient goes to the GP, and she has 3 problems. She's recently gained a bit of weight, she's very tired, and she's had some nausea. And the GP looks at the couple of tests she's done recently and recent history and her recent medical history, and comes up with, well, these are sort of the most likely things that are probably causing this problem right now. The weight gain is maybe caused by stop exercising, because she just had a knee injury, so she stopped exercising, and it's probably 80% that's probably the cause here is to stop exercising of weight gain. She's also, the fatigue is probably caused by there's mono going around, hasn't got the test results back yet, but it's probably 50% likely that she's got mononucleus. The nausea could be a stomach virus. There's also a stomach virus got around, that's 15%. But also the doctor knows that she's trying to get pregnant. So perhaps the weight gain, fatigue, and the nausea is just caused by pregnancy. And that's maybe 15% chance of that because she's only just started. So it's really unlikely. So the question here is, what's the best explanation? I want you to answer, is it A or B? Is the best explanation of these 3 symptoms that Cheryl stopped exercising, she has mono and stomach virus, or is it that she's pregnant? So I'll give you, I don't know, 20 seconds to figure it out. We're all hopefully somewhat experts, and try and think what it is, A or B, in the chat window. Pregnancy, says David. B. When good. All right, so we're getting 1, 2, 3, 4, 5, 6, 7, and 9 votes so far. We've got 8 for B, and now 2 for A. Hickham's dictum. Okay, so we've got one vote for Occam's razor, 1 for Hickham's dictum. A's Prashan's going for A. Thanks for balancing it out. Okay, so I think now what you'll know is there is no best explanation, actually, really. There's because there's 2 ways you can kind of look at this. Yes, David picks up here. He said pregnancy, but what you'll notice is if I asked a group of statisticians or data scientists, I'd probably see more of them saying A, because if you multiply the probability of these 3 things, 80 by 50 by 50, it's 20%. Well, that's more likely than 15, so that's the best explanation. But as you see here, sort of Shane saying, well, Occam's razor says this is a simpler explanation, and the simpler explanation is often more likely. But actually, we know it's actually less likely from calculating the probabilities, but somehow that just feels right. And so this thing here, there is no best explanation, but this is actually, I took this from a paper by Tanya Lombroso, who's a cognitive scientist, and she's done a lot of these studies where she asked little questions about this. And I don't want to get bogged on this particular example, but the point is there's no right answer. If you ask people what the best explanation is, it's going to depend on the audience here. But what the finding in that paper actually says, well, yeah, well, people will prefer this simpler explanation that's only got 1 cause that explains 3 symptoms over these 3 causes that explain these 3 symptoms, even though it's less likely according to this probability table. And actually it turns out that the probabilities need to be, it nearly needs to be double. This nearly needs to be 30% in order for people to really start preferring this as an explanation here. And so I don't want to get torn down this example, but it turns out that from a perspective of cognitive science, there's all these little examples around this, around how people prefer to consume explanations and what the properties are of an acceptable explanation. And probably we should know about these things if we're writing explainability systems, or at least we should have some idea that a body of literature exists that does a lot of this. And the literature is full of studies that are, you know, somewhat counterintuitive, but when you do it yourself, you can see why people think this. And so I read, I don't know, like 250 papers that were all like this, different studies, some philosophical thought. And I thought I have to share this with the community. I've switched my slides incorrectly. And I wrote this paper now that Prashant mentioned. It's had quite a bit of impact here that summarizes this whole thing. And that's the archive link there. And probably a lot of you will have read it, I think, here. And it was a really useful way to get my head around how this happens. And now I ram it down my students' throats, as Prashant's learned here, of saying, well, yeah, go back and read whatever someone says here, and you go and look at the paper and find out who's doing that work, and go and look up what they have to say about it. And I'll give an example later about from Prashant's own work about how it's influenced some work of ours. And when we talk about social sciences here, one of the things we also should be talking about is human-centered studies. And I think human-centered studies are important for validation, and not every paper needs a human-centered study, but when you're proposing this is a better way to explain, I think you've got to really take care to make sure you evaluate it properly. And so here's an example from a talk that Bean Kim gave on interpretability. Interpretability community haven't been great at doing these studies at all. In fact, if you go to my Twitter, I read a paper yesterday that summarized this argument so much better than I did, but I'd already prepared my slides, so I didn't put it in. But this is an example about not infusing human-centered studies, but that's not what Bean Kim's talk was about. But they were studying these kind of saliency maps. And here's an example of a saliency map generated by a program called SmoothGrab, and this explains the classification of this picture. So in this picture, we have an ATM here, and the classifier that they use, a neural network classifier, labeled this as an ATM. And if you use SmoothGrad, you get the explanation that this is why. And there's lots of these kind of intuitive examples presented in a lot of these saliency map papers of saying, you see, that's the explanation. Doesn't that make sense? It says ATM, the ATM's highlighted. There's a person highlighted. Obviously, you must learn that people use ATMs. This is a really great explanation. And that was the validation. Now, it was this particular image that gave Bean Kim and her group, I think, an inspiration for something that said, well, if you look at the strongest part of this image, it's this wheel. And this wheel belongs to a trolley, and this trolley has nothing to do with an ATM. And surely pictures aren't being seen. These aren't being seen in pictures of ATMs very often. So they went back and sort of did a study and basically found out that if you take this neural network that's doing this and just jumble the parameters such that it's random and just gives random classifications and run a lot of saliency map generators, you get the same looking explanation. And what it turned out was a lot of these saliency studies are really just edge detectors, which are not useful for explanation. And the point of that talk wasn't about human studies, but the first thing I thought was, well, if you had designed human studies properly in this work, they would have found this, because a human study would have asked, wouldn't have said, this is an ATM, this is a picture, isn't that right? Isn't that great? It would have said, well, here's an explanation, and here's the picture. Can you tell us what it's classifying from this explanation? And you wouldn't have guessed ATM from that at all. And some proper human studies would have generated that. And as I said, there was a great paper about falsifiability, interpretability research that was released quite recently that I read yesterday that summarized this argument much better than I ever could. Okay, so when I wrote this paper, I guess there was 3 lessons that I'm going to talk about, 2 of them today, and some of you will have already seen things, but for those of you who haven't, I want to push these 3 lessons. And this one I want to push quite a bit around contrastive explanation, because I think this is probably the most important thing that I've read that's influenced the way that I do work in this area. And it's this is a quote from Dennis Hilton, that the key insight. So Dennis Hilton's quite a well-respected social psychologist who does a lot of stuff on causal explanation. And I happened to be lucky enough to meet him when I was in Toulouse on sabbatical. He works there. And this is a quote to say that the key insights that we don't explain an event per se, we explain why some other puzzling event didn't occur and the target case did. So we usually don't ask, you know, well, why did you do that? Or we might say, why did you do that? But we mean, why did you do that instead of some other thing, which is what I expected. Why did you give that answer? The explanation usually comes from, well, I know you were expecting some other answers. So what I'm going to do is compare those two answers. And so to give a kind of little toy example here, imagine you've got some classifier that can classify arthropods. This is just an example from a paper of mine. And it can classify spider, beetle, bee, or fly. And it uses these properties like number of legs, stinger, eyes, and whether it's got compound wings and how many wings it has. And so if you said, why is it a fly? Well, you could give this explanation. It's I said it's a fly because it has 6 legs, a stinger, 5 eyes, compound wings, and 2 wings. But that's not what you'd usually ask. Usually you would say, well, why is it a fly? Because actually I thought it was a beetle. And so to say, why is it a fly rather than a beetle, you could give all the reasons it's a beetle and all the reasons it's a fly. But it turns out that's not what you and I would do. If someone presented this question here, we'd say, well, why is it a fly rather than a beetle? We would focus on this property here, right? Which is the property that's different between beetles and flies. They have the same number of legs and neither of them have a stinger. They have compound eyes and 2 wings. If you said, well, why did you say that was a fly rather than a beetle? A good explanation would usually say, well, the beetle has 2 eyes and a fly has 5. The fact that beetles and flies both have 6 legs is not relevant to asking this question. And this is known here as the difference condition that Peter Lipton proposed, probably early 90s work, proposed that this is the way that people use to explain things. And there's a lot of people in philosophy and social science who'll tell you that's actually when somebody asks a question, why is it a fly? They always mean, why is it a fly rather than something else? We always explain stuff in a contrastive manner. There's other people who disagree with that, but that's generally the prevailing wisdom. And we usually mean that, and it just, as human beings, we're just very good at figuring out when somebody says, why did you do this? We're usually good at figuring out what they thought we should do, and we explain relative to that. And eliciting that sort of rather than a beetle or rather than something else I did turns out to be probably a lot harder for machines to figure out, but you know, I'm sure there's ways we could do it. And certainly if we explicitly elicit that, we can give better explanations. So in this example here, we've only got 5 parameters, but you know, sort of models that do things like credit scoring have in the region of thousands of parameters here. So this is a good way to hone down on sort of using the rather than a beetle, using the rather than to sort of get a window into the mind of the person who's asking and really hone in. The second thing that I kind of learned is that, well, that I talked about at the start, is that explanations are really social. So here's another quote. It's also from Dennis Hilton, coincidentally. I did read people other than him, but he has a knack of coming up with good quotes in his papers. So causal explanation is first and foremost social interaction. And so he says this: explain is a 3-place predicate. Someone explains something to someone else. And that explanation takes the form of a conversation. So it abides by things like Grice's maxims. And at that point, I don't think I'd seen much at all around the social part of explanation. There's more and more work happening already now in this area. But some work that Prashant's done on this early in his thesis was around studying this phenomenon here. So you can ignore this picture for now, but basically what Prashant did was went and looked at various sources and took around 400 explanation dialogues from a variety of different sources, from court transcripts to interviews, these types of things. And he went through and used content analysis to look at the sort of main concepts and the flow of control in these things here. And here's a picture from the paper here. I'm not going to go through the whole thing. I don't want you to understand the whole model. But just if you want to think about how to read this, it just says, well, the questionnaire queue will begin with a question and the explainee will explain it, and then it can finish there. That's the way you would love explanations to work, but they don't work like that really between people. Usually there's some interaction that goes back and forth. And what's interesting here is this idea, this back and forth between this left side, which is an explanation, and the right side, which is an argument. And you tend to see this a lot, where there's a question, there's an explanation giving, and then the questioner argues about the stuff in the explanation. So why did this happen? Well, because X equals 5. no, actually, I don't think it is. I think you've got that wrong. I don't think X is 5, or I don't think that would cause this here. And there's some argument where they resolve something, and then sometimes they can't resolve it and it fails. But other times it comes back, they agree, and it comes back into the explanation and says, well, okay, if we agree that's not the case, now why did it happen? And this goes round a loop a few times. In this case here, and we saw that they usually end up, it's more than one loop most of the time. It tends to be 2 or 3 loops around here, and that's I think that's a pretty nice model that we can build on, and a few people have started looking at work that builds on that work, and in particular when you're explaining this kind of complex causal chains of of planning agents or something like that, where there's a range of things. Well, yeah, I did this because of that. Well, why was that the case? Well, because earlier I had done something else to make that the case here. And this kind of social explanation, I think, is something that's important. We haven't really looked at, and Prashant sort of went a slightly different way in his thesis. So we didn't really get to that point where we investigated that well. Okay, so just a matter of time. So what I want to talk about now is about how we've learned some of these, used some of these learnings in different areas. And I'm going to focus, because this is a workshop on agency, I'll focus on the agency work, which is largely Prashant's work. So I'm going to talk about 2 of Prashant's other papers now here, but we're doing similar things in the group. Similar other students and postdocs are doing similar things. So Prashant had his paper in AAAI last year where he looked at explainable reinforcement learning. And so we actually looked at model-free reinforcement learning. So if you're not familiar with model-free reinforcement learning, this is somewhere where you have to, you don't have a model of your environment, like a strips model or something like this. The learner has to learn it by just interacting with the environment and getting rewards back, getting rewards, positive or negative rewards, in order to adjust its behavior. And so that's pretty complicated to, when you don't have a model of the world, just to pick out things about the world that are important and use it to explain. So in this paper, what we've tried to do is to come up with an approximation of the world in order to get hold of things, to explain things. And so we came up with this idea of an action influence graph, which is based on Pearl's structural causal models. You don't have to worry about this whole graph here, but just to give you an intuition, that the nodes are variables in your state here. So you have to have a factored representation, and these arcs are the actions. And so what this really says is that this is W, that's the number of workers in a StarCraft game. S is the supply depot. You need a certain number of workers to build a supply depot, which is a S, the action here. And we modeled the relationship between this. And so the idea was you draw this graph by hand, and then we used pretty standard linear regression to learn what these relationships are. Like how does W influence S when you select action A? And we came up with an approximation of the environment that's was kind of okay, and it was enough to get hold of variables in the environment to give explanations. And so I don't want to talk about this work in particular now. It was okay, it was pretty good work, but what was interesting about it was the human insight we got out of it. And so as part of this, we did some experiments where we asked people, we gave them a whole lot of explanations, and then we did what's called a task prediction study, where we said, okay, you've seen a whole lot of explanations. Now here's a situation. Can you tell us what the agent would do next? Not what you think it should do next, but what you think it is going to do next based on what you'd seen here. And what we saw was people in different explanation conditions were able to predict this better than people who didn't have explanations or who had a baseline. But interesting, what we also did was we said, okay, make that prediction. Now tell us why you think that's the case. And so people would give explanations for why they made that prediction. So this gave us a corpus of explanations of reinforcement learning agents, or of agents who are in StarCraft. And so Prashant went back and did a thematic analysis of all this to learn, well, how are people explaining agents' behavior in this case here. And there was quite a few findings from this, but he came up with this one key observation, was this idea of what we call distal explanations or opportunity chains, that said, well, actually people are using this pattern a lot. They'll use what's called an opportunity chain, which is something that's come out of social psychology literature, that says, well, here's a chain of explanations here. And it turns out sometimes when you're explaining, well, why did you do action A? It turns out you say, well, because that allowed me to do action B, which then allowed me to do C. And that was when I could achieve what I really wanted. So I didn't really want to achieve this thing here that A achieved. I just did that to enable me to do B, which would enable me to do C. So it's called opportunity chain. That opened up the opportunity for me to achieve my goal. And so we found this pattern here, and Prashant said, I found this pattern. I said, that's opportunity chains. We can go back and read about that. And we read about it and came up with an improved model for this that's under review right now. But it's available in archive about distal explanations for reinforcement learning agents. And so again, we kind of learned these patterns. We can't get hold of a model. So we learned, well, when do we see B always preceded by A? If it's always preceded by A, that's probably a sign it's an opportunity chain. And we use recurrent neural networks to learn these types of things in order to improve our explanations. And so here's an example of what the previous model would have done here. It's why did you build Marines in a game of StarCraft? Well, because it's more desirable to train Marines and to have more allied units, as the goal is to destroy units and buildings for your opponent. The distal explanation is something similar because ally unit is less than blah, blah, 19 here, but it's more desirable to train Marines in order to enable the action attack, as the goal is to have more destroyed Marines. And now you can see a little bit here, we have more allied units to destroy things here, but we've got a more explicit thing that says, well, we want to destroy buildings and units. And in order to attack, we need to have more Marines. And that gives you a better link through the causal chain as to what's going on, and feels a bit more natural, I guess. But it turns out this is probably what we thought people would like. So we went and did, again, we ran a whole lot of user studies on three different scenarios here and collected a whole lot of things. And before I do that, I want to shout out to this paper. I saw Shane was here earlier. This is a great paper that if you haven't read, I'd love you to read it. So this comes from Robert Hoffman and Shane and Gary, who are on the DARPA XAI project, the cognitive team. They've come up with a whole lot of nice explanation of ways to evaluate explainable AI that focus specifically on AI. And if you're explainable AI, talk about task predictions and how to elicit mental models properly. There's a nice couple of pretty simple surveys you could get to sort of measure people's perceptions of things here. We've used this quite a bit, and we used a couple of things out of this for this study. One being the idea of task prediction, which most of you would be familiar with already, which I talked about. You show people a whole lot of examples, and then you explanations, I should say, and then you give them some holdout examples, and they have to predict things without explanations. And we also ran some satisfaction scales from this that are very useful, that have been well validated. And so I'm not going to go over all the results here, but I just want to go over the task prediction score. So again, this is saying, well, here's 6 scenarios with explanations, try and figure out how the agent operates. Now here's 6 holdout scenarios or 4 holdout scenarios. Go and work with the agent now in order to do things or predict what the agent's going to do next.
3 minutes, Tim.
Thanks. So we had 3 models. No explanation, the causal previous paper and the new paper. Here we had 3 different scenarios. So a sort of adversarial scenario where they were doing task prediction. And then the middle one was a collaborative scenario where some actions the agent could do and some actions the human can do. And then a search and rescue scenario. And what we saw the other graphs around satisfaction, all these things similar here, but we see that just by using this idea of distal explanations, we were able to improve how people worked with these agents in 3 different scenarios. They also found that found a bit more natural, didn't have any effect on trust, which was, I think, is a good thing. It didn't make trust go down, but we just saw that bringing in this small insight from a previous human study, building on an existing theory, was able to improve the way that people saw things. And so I think that's a nice example of applying social science theory into explainable AI. Okay, so that's all I want to talk about here. But just a couple of things to take away here. If you're I'd say a fellow inmate, so I'm one of the inmates of all this. I'm a computer scientist. I just want you to remember that how people generate, select, and evaluate explanations is already pretty well understood. There's lots of work around this area, and social interaction of explanation is really well understood, and having that grounded knowledge is useful when running studies, as I find sort of just every paper we write. And validation on human behavior is necessary at some point. I'm not saying every paper needs to have a human study, but when you're proposing, this is a good way to explain. If you're not doing behavioral studies, what we're seeing coming out of, say interpretability, is that 2 or 3 years worth of bodies of work of a group of people becomes almost meaningless if it's not evaluated properly. And more, if you're sort of one of the wardens, right? If you're someone who's not in computer science, I'd like, if you're interested, help improve this link between social science and explainable AI, or in interaction design, I should say as well. Here, there's lots of people from that community coming through, but also work with the experts here, and don't try and do it in isolation. And helping computer scientists to design these interactive studies. I think a lot of the reason we don't see more is because it's hard. People don't have the experience, and just helping people to work through. But it can't, when you're experienced, it's not that difficult. I mean, it is still hard, but it requires a lot of thought, but it's also very interesting. So if you're one of the wardens, really getting down and helping to design these studies. So here's just some funding acknowledgements for you from a few grants that have funded all this work, and I'll just leave the overview there, and I'm ready for questions. Thanks for listening.
Thank you very much, Tim, for the great talk. So we can open the floor for questions if anyone wants to ask a question.
Sure, I think I could jump in. So thank you very much for your talk, Tim. My name is Adam. I actually work closely with Rosina at Drexel University, and I don't consider myself an inmate nor a warden, more probably a jail guard in training, so I think I'll say. But kind of building to that point, I'd love to hear your perspective on maybe any challenges that you encountered in your collaboration with social scientists in analyzing qualitative data that you obtain from any sort of user studies or evaluation?
Oh, that's a good question. I mean, there's not so much challenges with my collaborators, who are somewhat a bit pragmatic about things. But the two problems are the standards you might expect in some social science studies are probably more than are expected in a computer science study, and more than we're willing. So if you come from a community where, I mean, I'm oversimplifying things completely here, but if you come from, say, the cognitive psychology, really the study is the main part of the findings a lot, where in computer science, we also have to propose algorithms and validate things other ways. So often in a 6-page conference paper, the human study has to take a 1 page at most, and that means by definition you have a simpler study that's smaller and focuses on something. So that can be a little bit challenging to sort of say, yeah, I agree that we should probably run 3 studies, but this is probably not what we're going to be able to do in a PhD, to do that several times. The second one is around the way people go about analysis. So we deliberately keep it pretty simple. I think I mentioned thematic analysis a few times here, and quite often you have to justify, why didn't you do grounded theory, or why don't you do this model? And this is more from a reviewer perspective. And sometimes it's just, look, we just don't even really know those models that well. That's why we have these collaborators who do know them. But you do have to spend a lot of time, justifying and reasoning over why you did particular analyses. And often the reason you choose it is because it's simple, because the student or the postdoc doing it's not an expert in qualitative data. So we do a fairly simple thing, and it can be a challenge. And probably we're right to be called out by it, but it can be difficult to sort of, make sure you choose the right model and of analysis and explain it well to reviewers who are, in a good workshop is hopefully you do get reviewers from different areas. So you're trying to explain the study you've done to a computer scientist and maybe a psychologist and maybe someone from HCI all in the one audience. It's a challenge.
Yeah, thank you. And it's definitely very, very interesting hearing your perspective as someone that, has immersed yourself in those adjacent fields. So thanks.
Tim, I'm going to stop sharing your screen to let the next speaker set up the screen.
Could I ask a question while you're?
Yes, please.
So Tim, very interesting paper. I guess one of the things I started thinking about during it was, you know, when people are going to go to evaluation, I think the first thing they'll try and do is what you might call single shot evaluation. So does this explanation improve this single shot test thing? And of course, that's fairly hard in my view and gets very complicated very quickly. But you're adding a layer of interaction on top of that again, which means that you have the complexity of all the sequence of steps that are going to be gone through when the explanatory conversation is happening. Do you want to apologize for that or do something like
Yeah, I mean, I'll say something. You can see Prashant didn't go down this pathway because it's a hard pathway to go down. And I think that's part of the reason why nobody is really tackling it. So it's hard to design interactive systems, and it's hard to evaluate interactive systems in that manner. And I think that's why, you know, you'll see me saying, oh yeah, social explanation. Not many people are looking at it, and neither am I looking at it so difficult, because there is that struggle. I mean, especially you got a PhD student, you have to get them through in a fixed amount of time, and you can't afford things to go wrong too many times. So yeah, I mean, I won't apologize. I won't apologize for bringing it up, but I probably will apologize for not having the goal to try and solve it myself, because I agree that's the challenge.
Tim, I'm sorry, we're going to have to stop now to get on to the next session. Thanks very much for your talk.
You got it. Thanks very much for the invite. And I'll stick around for a bit, but my kids will be up soon bothering me. So
yes, and we've got a Racket Chat channel for others who would like to continue to ask some questions. In the meantime, can I ask the next speaker to please take control of and share the screen? That'd be Johannes Haug or great.
All right.
Fantastic.
I guess you can see the screen.
And if you could, yes, can see you. And if you could please mention your co-authors as well. Thank you.
Yes, of course. So my name is Johannes Haug, and I'm presenting you our study on baselines for local feature attributions. This is a joint work of myself and my colleagues Stefan Zürn, Peter Elschis, and Jessica Snetzi. We are all members of a small research group for data science at the University of Tübingen in southern Germany. And I guess we can go straight to it. I will begin by a quick outline of the general problem and the motivation of our work. However, I will try to keep this brief, as I suppose that most of you are familiar with the basic concepts that I'm going to talk about. Right. So generally, suppose we have some complex predictive model, and the predictions of this model, so be it a neural network, for example, or some ensemble classifier, the predictions of this model are not explainable in human understandable terms. And so since this could raise some issues in practice, for example, we could struggle to justify predictions made by our model, or we could run into regulatory issues. This is particularly important in Germany, where we have quite strict regulations, for example, in finance. To this end, we want to provide explanations post hoc. And so one recent and very popular approach are local attribution methods. And so generally these attribution methods, they try to quantify the importance of, or the local importance of input features for the predictions generated by our complex model. And so popular examples of such local attribution methods are, for example, the SHAP framework, which is a model agnostic and game theoretic approach, or inspired by a game theoretic principle, namely the Shapley value, or integrated gradients, which is the more specific local attribution method, which essentially exploits the gradient information that we have in neural networks. And also recently, there has been an ongoing discussion about the limitations of these local attribution methods. So usually what we find are limitations regarding like the computational complexity. For example, to generate the correct Shapley values, one would need exponential computation time. Other limitations concern, for example, like sensible theoretical properties that are violated by certain approaches. And then recently, there has also been an ongoing discussion about the sensitivity of these local attribution methods with respect to their hyperparameters. And in fact, it can, for example, be shown that just by changing the random seed in some of these approaches, we will generate attributions that look very, very different. Now, in our study, we focused on like a very central hyperparameter, which is the baseline. And the baseline is essentially the reference value that expresses the absence of information in our system. And usually what we do then is we express the importance of input features relative to this baseline, meaning we express the importance of an input feature relative to no information being present in that feature. And now naturally, this concept of missing information is very domain specific. We can see this in a quick example here to the right. So you see an image of a camera and its corresponding explanation obtained by the integrated gradients model. And here the authors used a zero baseline. So that means essentially they used a black image as the baseline. So, and indeed, one could argue that like a black pixel resembles the absence of light, and therefore it also resembles the absence of information. But at the same time, one could also argue that like the absence of light and a black pixel is indeed discriminative information. For example, just suppose if we didn't have these silverish patterns on the camera and it would be all black, we would just perceive all zero attribution scores essentially. And so the problem of choosing, or the difficulty of choosing an appropriate baseline also applies to other domains than image data. So for example, suppose we have a feature that is categorical. If we would use a zero as the baseline, so as the representation of missing information, it could very well render our explanations completely meaningless, just because zero could also be just another category in a data set. And so essentially most of the open source packages one finds has the baseline as a hyperparameter, and usually the baseline is chosen only heuristically. Right. So our goals are first of all to categorize existing baseline techniques. To this end, we specified a very simple taxonomy, which is based on two properties. Our goal was then to investigate the effect of different baselines on the local attributions generated by some of the most popular attribution methods. In our experiments, we focused on tabular data sets, since they are commonly used as benchmark in explainability and fairness literature. And in this context, we're also complementing existing studies that investigate the effect of baselines on image data. And finally, and I think that this is essentially the most important goal of this work, is to increase general awareness about the important role that the baseline has on local attribution methods. Now let's begin with this taxonomy. So as I said, this essentially consists of two properties. To this end, suppose we have two observations that we aim to explain, here denoted as xi and xj, which follows some distribution. And we also have a baseline method, capital B. Note that we don't make any requirements towards the functional form of B. Now for the first property, suppose we compute the baseline values corresponding to each of the observations, xi and xj. We then say that the baseline method, capital B, is static if for all possible observations, the baseline values are equal. So essentially, a static baseline says that we use the same static value for every observation that we want to explain. And otherwise, we call a baseline method dynamic. So this property is mutually exclusive. Now, the second property concerns randomness in the generation of baseline values. And to this end, suppose that we compute baseline values with our method twice. So b to the 1 is the baseline value obtained for an observation xi in the first run. And then we compute the baseline value for that very same observation xi a second time, which is b to the 2 here. And now we say that the baseline method B is deterministic if the probability of these baselines obtained from the 2 runs being equal is exactly 1. And otherwise, we say that B is stochastic. Now, based on this taxonomy or these 2 properties, we categorized some of the most popular or common baseline methods you will find in literature. And note that, like, most of these baseline methods have their origin in the image domain. However, one can also apply them to tabular data with some slight adjustments, as we show in our paper. To the baselines. So first we have this constant baseline, and essentially that's a static value that we choose once and use throughout all the explanations that we want to obtain. So this could, for example, be that 0 vector or black image that we saw in the introductory example. And then there is the maximum distance baseline, which corresponds to the observation that lies furthest away from the observation in question that we try to explain in terms of the L1 distance. The blurred, the Gaussian, and the uniform baseline, they all apply some random noise to the original observation to retrieve the baseline. And finally, the expectation baseline corresponds to the expected value in the training set or a randomly sampled subset from the training set. And so what we did in our experiments is we applied these baseline methods to 4 popular attribution methods. First off, the Shapley kernel, which is a model agnostic scheme. That means it can be, or it doesn't make any assumptions towards the complex model that it is aiming to explain. But it is also very inefficient, right? So the kernel set requires exponential time to sample all the possible subsets of features that it wants to investigate. And then we also looked into DeepShap, integrated gradients, and DeepLift. And these are model type specific attribution methods for neural network architectures. And specifically, we then obtained explanations for 5 tabular data sets. And we used both binary and multi-class classification data sets with different dimensionality. And so to evaluate the effect of baselines on these local attribution methods, we used top-K ablation tests. So some of you might be familiar with this ablation test. Essentially, it's just quantifying the discriminative power of the generated feature attributions by gradually removing the input features that have received the highest scores and then investigating the change in the predictive outcome. And so essentially the intuition behind this is that the better a local attribution method is in identifying the truly important input features, the larger the decrease in predictive accuracy, or in our case, we used F1 score is. So as I said, we used the F1 score in this case, which is the harmonic mean of precision and recall, since we also had imbalanced data sets and the accuracy isn't meaningful in this context. So these are essentially the aggregated results of our experiments. And maybe, yeah, so just again, as I said, whenever a local attribution method is performing good, we suppose that we obtain a sharp decrease in F1 score here. And so one observation that you can see straight away is that there is indeed a large difference in the results corresponding to these ablation tests given the baselines that we choose. And so
Johannes, about 3 minutes left.
How many, sorry?
About 3.
Okay, that's fine. That's very fine. Yes, essentially, what we see is that this intuition that we had earlier, that like the choice of a baseline is very domain specific, this is also supported by these findings. So depending at which baseline we are using, we receive very, very different attributions. And this is undesired in practice, right? So we see that these local attribution methods are very sensitive to the choice of baseline. And maybe to be at least a bit more specific, so we also found that in general, the maximum distance and the uniform baseline perform worse than all remaining baseline methods. And we attribute that to the fact that these baselines tend to produce outliers as a reference value. So essentially, this is just because the maximum distance baseline and the uniform baseline don't acknowledge high density regions. So it could be very well the case that our maximum distance baseline or the uniform baseline generate a baseline vector which lies in a low density region of the original data generating distribution. And this is what we suppose the reason that like also expectation and Gaussian baselines perform better in general. So as I said, so some of these findings are also supported by more recent studies. However, as always, these results should be considered with care. So there's no guarantee that these results apply outside of our experimental setup, although we try to like have different types of data sets, dimensionalities, data types involved in the evaluation. Yeah, but to the summary, so essentially, we found empirical indication that baseline values significantly alter the generated feature attributions on tabular data. And this is across all the local attribution methods that we investigated. Yes, in general, it is very important to note that whether a baseline method is appropriate or not largely depends on the domain that we have. And sometimes it's also not that simple to come up with a good baseline. So this is also why we argue that in general, the choice of baseline should receive more attention in both practice, but also in research and the development of new local attribution methods. All right, but that's all from my end. Just one hint, if you have any interest in our research or want to learn more about this, please visit our website. Otherwise, I'm now looking forward to your questions.
Thanks, Johannes. We have time for 2 questions. Rosina, you said you had one?
Yes, thank you for your talk. This is very important work. I have to say that I've been missing this aspect. I wonder if you could help us clarify better the use of baseline across different types of feature attribution methods. I don't see that in something like Lime, for example. I see you mention how SHAP uses. Are these like mostly valid for gradient-based feature attribution methods?
So you're absolutely right. So I think there's like differences in how deeply this concept of a baseline is involved in the development of these approaches. So we see that, for example, in integrated gradients or deep lift, they motivate their whole example with saying that a feature attribution is only meaningful if we quantify the difference to some reference value, which is this baseline. in Shapley framework, we essentially see that the baseline value is rather a computational heuristic where we replace missing information, since we want to sample feature coalitions and therefore have to simulate missing information. And then we just replace it by some vector. But here it is rather computational heuristic. And you're right, I think in Lime, we don't really specify a baseline as a hyperparameter, but there we sample in the local proximity. And essentially here, I guess we could say that depending on what, or the role of the kernel that we use to sample in this local proximity plays a similar role to what the baseline does in these other approaches.
And indeed it does. Yeah, that's a good point, because it does, the sampling does. Wonderful, thank you so much.
We have time for one more quick question. Lang, did you have a question?
I have another one.
Go ahead, Rosina, and that'll be it.
Johannes, did you learn about the work done by Alan Fern and the studies on salience methods?
So I'm aware of one study on saliency maps, but I'm not sure if it's by that author. So maybe you can hint me at that in the comments or so.
We can talk offline.
Yes, please.
All right, thank you.
Okay, thanks very much for your presentation. So next up will be Carrie. If you could please go ahead and push your slides.
I just have to share my screen first, sorry.
That's right.
Let's see that I get the right one, and then we go ahead. Once. Okay. I hope you can see the slides, and I'll just put stuff away. I hope you don't see the Zoom stuff there. All right. Does it look okay?
Yes.
Great. So then what I'm presenting, it's the CIU package implemented in R for the contextual importance and utility method. So what I'm actually going through today, it's sort of the background behind the contextual importance and utility and how it works. And I don't see where the baseline would be there, but let's see if we could have an interesting discussion with Johannes. But I'll go ahead. Okay, so the background and history of CIU is that it's something that I developed back in my PhD thesis back in the 1990s. So as many methods that we are using nowadays. And the problem that we had at hand was waste disposal site selection in France. And actually this jumped a little bit too quickly. So the challenge that we had was to select among something like 3,000 different potential sites where which site would be the least problematic for putting industrial end waste there. And we had quite a lot of decision makers involved there, of course. And once we came up with this recommendation, we had to justify it pretty well for the decision makers, but also the local inhabitants, because well, it was France, so we don't want to have this happening. So very much about producing explanations that are are understandable by even by end users, meaning decision makers, but also the people concerned by the decisions. So we developed 3 different decision making tools. So we had this rule-based system, a system based on weighted sums or analytical hierarchy process, and something called Electra. So this is the kind of explanations that we produced back then from this rule-based system. So for rule-based systems, you typically use this kind of what was called and is called intermediate concepts. So we had this sort of top-level intermediate concepts: nuisance to population, aesthetic value, access, geological properties, and hydrographical properties. So then we also did the structured explanation based on these but I'll try to avoid using up too much time on this old stuff. But there were some key concepts that you can see in these explanations. So when we were using the weighted sum or this analytic hierarchy process, so we scored all the sites with a numeric value in the range of 1 to 100. And the kind of explanations that we could give was then that, okay, we could rank the input features according to their importance, which then corresponded to the actual weight. But we did also have this concept of utility. So if a value is good or not, it's all in French, sorry for this, but you have this proximité de marne. So how close are you to swamp, which is not very important, but it has a very good value for that. Okay, that wasn't the best example. But we do separate this importance of an input feature and the utility, or how good the input value is. Then there was a third method used also, but I'll skip this one. It's called Electra. So what we did want to do was to actually learn this kind of decision-making models using neural networks. Then next question, is it possible to find some kind of a model agnostic way to explain these results that would be sort of homogeneous for no matter what the black box or decision-making system is? So the idea behind CIU is to try to explain the same way as humans do retrospective explanations. So I was actually selecting a car for myself and then thinking, how shall I justify this to my wife, and how shall I tell to my friends why did I choose this car and not the other one, and so on. So then we know that that leads to questions such as what were the most important features influencing the decision, and which features were favorable or not for one decision or the other. And it should also be possible to explain why not and compare the different decisions or different options. So this contextual importance of utility, the first paper is from 1995, actually. And as a side note, I did think about using the linear regression also, or a Lime kind of approach, but that I deemed insufficient for many reasons. And I would say that CIU is kind of counterfactual by nature. The kind of explanations produced by CIU back then looked like this, so they were pretty textual. So this example actually comes from a paper that we published 2 years ago. So it explains why an iris flower is an iris virginica and why it's not an iris setosa or an iris versicolor. So what we are doing here is that we actually use CIU for identifying which are the most important features and then use that as one part of the explanation, but also saying if they have a favorable or typical value or not for that kind of flower. So this is actually goes into a deeper discussion on vocabulary used in explainable AI. So I'm using a linear example here, a very simple linear function, y equals 0.3 times x1 plus 0.7 x2. So I think most of us would agree that the importance is usually expressed by the weight that we see here. And the utility is how favorable or good or typical this input value is for the output value. And then influence is how much does the input contribute to the output value for a given instance. So it's a sort of, well, a weighted sum. So if you want to calculate a student's average grade from university, the number of credits per course would give the weight, and the course grade give the utility. And I'm afraid that I'll be running out of time if I talk too long about these utility functions. So how does this work in practice? Well, contextual importance and utility. You have these two core formula that you see here, and then we have a parameter that you will be seeing also soon that defines a limit for positive or negative contextual utility. So the way in which contextual importance or utility is calculated. So when we have this kind of very simple linear function, if we want to get the importance of the input x1, then we just set the input x2 to a fixed value, which is 0.8, the value at the red dot that you can see here. And then the CI value is simply the ratio between this range that you see on the right, C max minus C min, divided by abs max minus abs min. So it gives you an importance of 0.3, which of course happens to be exactly the weight that we have in the actual function. So CI indeed produces the weight that we had originally. And the same thing applies for x2. It gives a weight of 0.7. Then contextual utility, I have in yellow here the neutral CU value, which is the limit between good and bad values. So we can see from here, CU is defined as the ratio between this range and C max minus C min range. So we can see that, okay, for x1, it's slightly above the neutral CU, and for x2, it's much higher. So what kind of explanations would we get from this then? Well, one way of showing, of illustrating, visualizing CIU is to use this kind of bar plots, which is probably not the best one, but that seems to be quite fashionable in the explainable AI domain. So what can we see from here? Well, we can see that x1 is less important, as we know, 0.3, and it has a sort of medium good value. And x2 is much more important, 0.7, and it has a very good value, which we can actually read from these images that we can see on the left. Now, this should be pretty obvious for everyone. As a side remark, Lime and Shep don't actually give these weights exactly when you try to apply them. But if you go to something more complex, so if we have a rule-based system, for instance, then the situation looks something like this. Again, the red dot shows the instance that we want to explain. And what we can see from here is that, okay, x1 has quite a big importance, which we can again read straight out from here. It's CI is 0.6, and we can see that it has the best possible value in this context. So CU equals 1. Okay, I hope this is clear. Then we go to the more interesting case, sombrero function, so something that we could have learned by a neural network or something similar. So here, if we use CIU for the same instance, or for this instance that you can see here in red, then you can see from the image here in the lower left corner that we get the contextual importance of 0.7224, and it's obviously x1 is obviously much more important than x2, as we can see from the bar plot here, and the value is slightly below neutral, whereas for x2 it's slightly above neutral. Okay, so that's how CIU is calculated using, or showing it using fixed and static known functions. So then if we move on to real life cases, we have explanations that can be produced in the same way, of course, for the iris data set, for instance, using CIU, an LDA model. Boston housing, here, this visualization differs, of course, from the typical Lime and Shep visualizations, because we actually have two different dimensions that we cannot visualize, so importance and utility. I'm running out of time, I think, so I'll go on with this. Titanic survival, same thing, explanation of what are the chances to survive for an 8-year-old boy in first class without parents and siblings. So again, there are only 3 input features plotted out here, but you can quite easily see from this visualization where the CIU values and so the bar lengths and the colors come from. Okay, So that's sort of the basic functionality that you can expect from CIU. Then there's also, you can also use CIU for intermediate concepts. So you can actually calculate CIU values also for something like, for instance, the performances of a car, which is a combination of sub-features: max power, weight, top speed, and acceleration. And I'll skip that. This is sort of a generalized conceptual importance formula, which doesn't differ too much from the previous one. And what you can do with intermediate concepts, for instance, is that you can see from, if you plot out two different input features in a three-dimensional plot, you can actually read out also CIU values from here, and then use that for explaining iris classifications using only the petal size and shape, or the sepal size and shape. So you can go up to higher abstraction levels. But
Carrie, about 3 minutes left.
Have the impression to see this very often. Okay. Intermediate concepts, so I'll skip all this. You can use this way of, you can use CIU in this way for, well, structuring your explanations into different levels of details. And of course, also use counterfactuals, so test what if you would change the safety from medium to high, sorry, from high to medium, how that affects your system. So then to the actual CIU package. For the moment, this kind of visualizations are supported from there. What is ongoing work is also CIU for images. I won't go into details because I really don't have the time, but let's say that it gives at least as good results as Lime, but something like 20 times quicker. The classical dog and guitar explanation. So CIU on the left, 15 seconds, Lime on the right, 4 minutes. And I won't go into details why CIU explanations, in my sort of subjective opinion, are better. CIU properties. Well, it's a model agnostic method, as you saw. CIU is not a black box in itself. You can, as you saw, really read out CIU values directly from input-output graphs from the model. It's relatively insensitive to parameter values. I don't see what the baseline actually, or what the baseline is. It's a much more calculation efficient than Lime and Shapley values. Okay, my question is there, what would be the reason for not using CIU rather than Lime and Shapley values? Of course, that's something that I would recommend to try out for yourselves. So there's a package published, the version 1.0 on CRAN in November, and on GitHub you can find some new developments as well as a lot of test cases. All right, thank you.
Thank you, Carrie. Can you go back one slide so that people can continue to see that for a few minutes longer? Thank you. So
yeah, sorry for having been too slow in the beginning again.
Oh, yeah, that's all right. You finished on time, so thank you. So I guess one question I had was, at one point when reading your paper, I thought that you said you had some tentative plans for extending. Well, you focus on tabular problems, and the impression was that you may have already thought about extensions for image recognition and related tests. I was wondering what your thoughts are on that.
Yeah. So actually, you saw these slides, I suppose.
Yes, I did.
Yeah. So, well, one reason why well, it's sort of interesting to do this, but it seems like everyone is expecting or explainability methods to work on images. Yeah, I don't know what more to say. This package is quite ready to be published quite soon, and I have some colleagues who are working on medical imaging, but I don't have those examples here.
Fantastic. So there's been a lot more since it's been written.
Yep.
Any other questions?
Okay, I can ask one if nobody else wants to.
Please.
Thanks for the good talk. I mean, when you got to this slide, Carrie, I was struck by how similar the two the two explanations are with Lime. And I mean, I think there's been some work on Lime that says that you sort of get different answers if you run a different explanation because of the random perturbations. And did you see similar things with CIU, or because I'm just shocked at how similar they are, given that you get different outcomes, but maybe they're not as different as what I think. But have you done a similar study with CIU?
I haven't, but I would say that you always systematically get you get the same result. Actually, it's very deterministic, completely deterministic.
Thanks.
We have time for one more question. Okay, so Carrie, they should contact you if they're interested in getting a copy of CIU to work on.
Yeah, or just to go to the GitHub page, or it's freely available.
Great. Well, thank you very much. This seems like a nice thing to make available to the rest of the community. Greatly appreciate it. And thanks very much for your talk.
Thank you.
Okay, so next up, could Sheng Min or one of the co-authors please go ahead and take control of the presentation? Well, are any of the authors for the paper on GANMEX here right now? I should ask. Well, if not, then we'll have a break in the schedule, looks like. Sylvia, Rosina, and Prashant, do you have any suggestions for how to use the time?
Well, we can, I think we have 20 minutes, if I'm correct.
Yeah.
We would.
Yeah, we would have a 20 minutes. So I guess we can always do like a virtual network session again.
Yeah, like we
because
were
there's
doing before.
also like the next session is again a contributed talk session.
Yeah, or either we can, if there are the authors, we can go for the next contributed talks, and at the end of if we have still time, we can do another virtual networking session.
So you mean to move up the schedule?
Yeah, if you want. I mean, we can also.
The only danger about moving up the schedule is that if people are coming here specifically for those talks, they may not be able to find them if they're shifted in time.
You're right. You're right. Yeah, maybe it's better if we do something else.
So.
No, I think we can just chat as we did earlier, or take a break.
Yeah, as you wish. Before it was interesting also the discussion that was coming, and we had to cut it because we didn't have time. So if we can also continue from there. I think like a participant also changed it during the time, because now we have other people. So before
So I'm hearing you say that we can open this up to, for example, more questions for the recent speakers, including Tim's invited talk. So if anyone has more questions for any of the recent speakers, be happy to entertain those questions right now. Well, let me ask one. Tim, you had to rush through your third point, if you're assuming you're still on, Tim.
Yeah.
And that was explanation is selection, if I recall correctly, from looking at it very briefly. I'm not sure you had as much time to talk to that as you would have liked.
Yeah, right. It wasn't key to the rest of the talk, so I skipped. I mean, the point is just, I think the quote is something along the lines of there are as many explanations as there are causes, and often there's, you know, thousands of causes to an event or more, but somehow when we are giving an explanation, we will just select one or two, maybe three causes, and that's enough to satisfy someone such that they're able to construct the explanation themselves to the level of satisfaction they want. And so I think there's a lot of work around how do we try and, in Explainable AI, how do we select those few things? But I think, there's reasons that as people we select them sometimes, and we could probably learn from some of those. I didn't have an example in the slides, but I've got some in other work.
Your focus, Tim, was on data-driven models. Have you given more thought to model-based approaches in this context?
I've given thought. I've done a bit of work with Dan Magazzini on model-based planning approaches, and I've got another student who's just started, 4 weeks ago, looking at model-based explanation in planning. So yeah, definitely I have. And I think, Prashant, you might even know why did we go down the reinforcement learning route? I can't remember early in the PhD. It was a problem that I've always been interested in, but I think the model-based thing gives opportunities.
Yeah, so the reason I went down that path was because I thought it was easier to give an explanation for a model-based kind of system. And if you are trying to do that for a model-free kind of system, we'll have to maybe learn kind of approximation itself, like even a model itself. But yeah, that's why I think I want to show that this could work for model-free agents, and so it can definitely work for model-based agents as well.
Sounds good. So, okay. So there were also two other recent speakers. Johannes talked about variety of baseline methods, and Rosina brought up a question that pertained to whether or not they're focusing on just one subset, which is gradient methods, and he pointed that out. I'm curious, Johannes, is there work on other categories of methods that we should be aware of that you'd want to highlight?
Do you mean other than local attribution methods?
Yes.
Well, in general, there are different approaches to these, mainly based on some form of decision rules, I would say so. But I'm not really aware if there's a similar concept. So I don't really know enough about this. But so as I said, so for the most popular of these attribution methods, and one has to say that most of these local attribution methods are specifically designed for neural networks, because they're one of the main examples for an explanation model that isn't explainable out of the box. They most of them, or at least to the best of my knowledge, make use of some concept of missingness. Yeah.
Rosina, were you thinking of other types? Oh, you're on mute. Sorry.
Thank you. I was having a snack, sorry. In addition to the ones that I mentioned, which are kind of different types of feature attribution, the other thing I was wondering, Johannes, there are also similar methods that they're doing instance attribution. Mm-hmm. And they also requiring that baseline. Have you looked at any of those? Do you see suffer from the same problem?
So we haven't really looked into those yet. So one of my colleagues, he wasn't working on this paper, but he's actually looking into the robustness of tabular Lime, and I think he's currently also working on something which, or essentially he found some form of sampling in the local proximity that guarantees certain robustness. However, so in this work, we only essentially looked into the Shapley value as a like an example for these input perturbation based methods and these gradient based approaches. But you're right, so it would definitely be interesting to extend this this evaluation. So as I also said, so this is kind of I wouldn't call it preliminary work, but essentially it's just a first a first step into a more in-depth and conceptual comparison of such baseline methods. And in this context, it will also make sense to investigate the effect of the baselines, not only on tabular data, but also on text-based classification. As I said, there has been some work on image recognition tasks. But yeah, so I think this is an ongoing problem that needs further consideration.
Great.
Can I ask a question? I don't know, Johannes, if you had the time to follow my presentation, and you probably haven't had a look at CIU, but to be honest, I don't see where the baseline would be there, for instance. Did you have any?
Unfortunately, I didn't really witness all of your presentation, only the last parts. But so essentially, I guess intuitively, intuitively the baseline, like conceptually, baselines may differ from approach to approach, but in the intuition of these local attribution methods, there's always some concept of missing information, I would say so, because essentially what you try to quantify with local feature attribution methods is local discriminative information, and that means you have to compare this discriminative information locally with respect to like some global absence of information, I would say. So I'm not exactly sure how it would apply to your framework, but yeah. So I'm also I'm also not aware if there are already works that look into this from a more theoretical point of view, other than this experimental evaluation that we did here. So I mean, this very simple taxonomy that we introduced might be a good reference point to start there. But yeah.
Carrie, is there anything more about CIU that you didn't have time to discuss that you'd like to?
Well, I could, of course, give a presentation of 1 hour without any problems, but I don't think anyone would like to have that. But
so
there was this.
One of the things that struck me was that there aren't a whole lot of talks on tools of this nature that in XAI that seem to be specifically being made available for enhancing reproducibility of work and comparisons. And so that's where my mind was at when you were giving your presentation. Hopefully that's what you wanted me to say.
Yeah. Well, I don't know what I wanted you to say, but the reason for this submitting this paper is that I see even with my own researchers, they seem to be so convinced that there's not much more in the world than Chap and Lime and so on. So if there's not something that they can just take off the shelf and try it by themselves, then they will not start programming anything different.
Yep.
So I'm actually a professor, so I normally I wouldn't program that much anymore. But it's kind of fun, and it seems to be the only way of getting things actually happening.
Yes, understood. Okay. So with that, we've got about 7 minutes before the next presentation will start. And Prashant, that's one that you'll be moderating. Do you want to take a quick break before then, or what would you like to do?
Yeah, I'm fine. I can take the long break. Yeah, my brain is a bit slow now, but it's fine.
Okay, so why don't we take a bit of a 5-minute break, and we'll restart at that time.
Yeah.
Thank you.
Recording now. Can you go check that you can pause it? You muted.
Let me try. If I click on you and I do stop
At
video.
the very top of your screen, there is a pause.
Let me try 1 sec. I stop it.
Okay.
I guess I stop it, and now I need to ask if I want to restart it. So I cannot restart it directly, I think.
Don't you see a triangle shaped icon there now?
No, I see only the round shape, and I'm allowed to stop your recording, but I'm not allowed to restart. So maybe you can, but I'm not sure that if we enter at your place, like how long will you be?
Presentation, and maybe around 3 minutes from that for questions.
Yes.
So yeah, David, you can go ahead and start.
Okay, perfect. Okay, thank you. Okay, so thanks everyone. My name is Davide Motin, and I will present the paper Bandits for Learning to Explain from Explanation. This is a joint work with Freya Behrens from TU Berlin, Stefano Teso from the University of Trento. And let's start with a very simple scenario in which a physician uses some sort of a classifier to diagnose sickness for patients. The scenario is just the physician asking, is John sick? And the classifier or the predictor just says yes and no. So the main question is, which is a very prominent question in the last years, is can we trust this? Well, the answer is better not, or better to investigate a bit further. And there has been a lot of development in this area about explanations. So explainers are basically associated to the prediction some sort of explanation, some interpretable explanations that can be in terms of the features of the concepts or some parts of images that the machine learning model uses. So in this case, the machine learning model can output a prediction, and then there might be another model saying that some dots are due to some funny syndrome. So that's why these symptoms are associated and are basically classified as sickness. So this, I also introduced some small notations. So X, Y, Z is for the explanations. And this is useful. So explanations are in general quite an interesting concept, and there must be development in this area, but they highlight bugs and some misconceptions of the classifier or the predictors, like the famous pictures of the husky and the wolf. So basically, here was a classification of dogs or wolves. And the idea is that there was a good classification, but for the wrong reason, because the classifier was looking at the snow. So far so good. So it's good that we have explanations, but what happens if the model is broken? Can we do anything with these explanations? So in the original versions, in the original problem, not much. So we have a way to debug, but we don't have a way to correct. So there are other issues. So many of these explainers, even though there are also other explainers, are post hoc. So on top of the original model, there is another model that tries to explain the prediction of the machine learning model. So this can be misleading. So they might not capture the right reasons, and they might actually not work in the proper way because they are detached from the original model. Plus, another issue or challenge is that there are multiple different definitions or multiple different set of explanations. So they can be feature relevance, for instance, that is a very simple one. So whether features are relevant or not relevant. So fever is relevant, skin rash is not. There can be feature importance, so where you associate a score for each of the features. So fever is 1.3 or some number, and low pressure is a negative number. And feature ranking, for instance, fever is more important than anything else. So somehow we have a lot of different explanations and different explainers. But what we really desire is, and there are a few works recently going in this direction, is that we would like to learn to explain. So we would like to have the model which automatically somehow understands how to explain the predictions. And the second is that we would like to learn from explanations, or at least a way to assess whether the explanations are good is to ask directly some users. So that's why interaction is also very important. So there is a feedback loop in which we ask the user. More in particular, our desiderata and our way of modeling things is to use bandits, and I will explain how. And the other thing that we would like to achieve is flexibility. So is it possible to adapt or to have a model which actually can ingest and use different kind of explainers and different kind of explanations? So let me give you again the same example, but now in the light of what we have been thinking. So is John sick? So well, this means that the user sends the symptoms or some features, some example to the machine learning model. The machine learning model replies with a prediction and with an explanation. So among all the possible explanations, the machine learning model selects some of them, actually one, and the user can actually say something, can give a score to the fact that the explanation, the prediction, and the input are actually coherent. And the user basically quantifies this with a function that we call the reward here, for historical reason and because we have used somehow a multi-R bandits framework. So what is actually our proposal? And this is a preliminary work, but we would like to expand it a bit further. So our recipe is basically that we can combine a few theories together. So bandits, Gaussian processes, which is a non-parametric model based on kernels, and some special kernels and rewards. So basically, if we can find the recipe for fitting all these things together, we have also a way to learn explanation, to interact with the user, and to improve the model over time. So in this recipe, we basically borrow some theories from contextual bandits, where the context is given from the input, the user basically input. Gaussian processes are by definition flexible because they basically accept any kind of kernel, so in general kernels. And we also design something new. So basically we worked on designing a special kernel over triples, because the triples are the input, the explanation, and the classification. And the reward is basically again over triples. So let me show you how this algorithm works, and to give you also an idea of where the bandits come from. There is an input coming, so a set of symptoms, a patient with a set of symptoms. Our model has a Gaussian process in which the reward is defined over the triple of the input, the explanation, and the prediction. And yeah, and the x-axis is basically the triples themselves. So we have a reward function which is modeled through a Gaussian process. And here we have a bandit framework where we would like to select actions. So to select a point, or better, a set of one explanation and one prediction to show to the user to be evaluated. And of course, our purpose is to learn as much as possible, so to have a model which have a high reward. In this case, so the red box is a low variance and also a high reward. Here is the x-axis. And here, and the green point is basically what is a more exploratory point, has a large variance, but the predictions are not so sure, basically. Quindi, there is some uncertainty in the model. So to do that, so to select the best explanation and the best prediction, we basically use a trade-off, a UCB algorithm, an upper confidence bound algorithm, which has been proposed by Krause and Long in 2011, and basically trades off exploitation and exploration. In order to prove the bound, they basically you basically have to play with this beta parameter. And there is a theorem that says that the regret depends on the norm of f. And the regret, which is the deviation towards the reward, the best action, is sublinear in the number of rounds t. This is very important. Actually, we looked it up, and it is possible to bound the norm if you have very expressive kernels, so RBF kernels or very expressive universal kernels. So basically, what we do is that the algorithm selects an explanation and a prediction, and then the user gives us some sort of a reward. So one thing that we needed to answer is which kernels. Well, we need somehow to devise a kernel for triples. And it is easily done, luckily, because product, so tensor products and sum, products and tensor sum, they are themselves kernels. So we could choose between product and sum. So basically, here it is only in pairs, but you can extend it for triples in an analogous way. Although product is time-consuming, is quite expressive. It's time-consuming because you have to consider all possible combinations here. But sum has a very big drawback, and that is independence, basically. So the explanation, the input, and the predictions are actually independent. And this causes problems because, so if explanations and predictions are not tied together, basically you incur in the same problems of the other explainers in the past. What kind of kernels you can devise? Well, I said in the beginning that you can have a flexible model. Yes, that's true, because for instance, you can devise for feature relevance, you can use Hamming or Jacquard kernels. For feature importance, you can use where feature importance is where you have real numbers associated to each of the features. And you can use a dot product or a cosine similarity. And other kernels are possible and even more complicated. So like traces. Traces are, for instance, decision trees where everything is conditioned to the previous action. And there are some kernels also in this case, even though we didn't experiment on them. I just want to show you our preliminary experiment. So we have this, we can call it a toy dataset basically, because it's 5x5 images with 4 colors. And we have 2 rules that define the explanations of why something is predicted positive or negative. So it is positive if the corner pixels are all identical, so have the same colors. And the rule one is positive if the three top middle pixels are different. So these three pixels here. We train on both rules, and we test examples only in one of them to see whether the model can actually generate the right explanation. The reward is defined on pixel relevance, so whether the pixel is relevant or not, or importance, and so we associate a 1 and -1, so it's a slight variation. And we measure the regret, which is the difference between the optimal triple that you can select and the predicted triple by our model. So in these preliminary results, so this basically was our idea that it is possible to learn even in this quite challenging setting. It is true, we can do that. So the regret goes down. So you can see that our predictor, so our Gaussian processes are actually learning. What we didn't see consistently is, for instance, that the sum, which has that very strong independence assumption, actually outperforming the product kernel. This can be surprising, but it can also very much depend on the dataset. And this is what we have seen in other datasets, that this is not true. And another thing is that at least so for the strategy that we use, so the upper confidence bound, is better than the random. So this is for feature relevance. These are the experiments for feature relevance. And so our hypotheses were somehow validated, even though in these toy datasets. And we can see that also by changing the kind of features, so by changing the kind of, explanations, we can still learn. And interesting enough, we have found, okay, in other experiments that we haven't reported, that it is possible to learn in even more. So in conclusion, what is Explearn? Explearn is a contextual bandit framework with the Gaussian processes and some special kernel. And it is self-explainable, so it basically generates the explanation lives in the same model as the predictions. It is kind of controllable because you have the advantage of choosing your kernel, and it is flexible because you can really fit a lot of different explanations. And it supports some guarantees. So we have some future work, which is probably evaluation and consistency, because we don't have still the fact that whether the explanation is zero, then the change in X shouldn't affect. Okay, and of course, fast inference, because for now we have to generate all the possible triples. So thanks. And if you have any question, the code is available. It's still research code, but it's you can download it and play with it. So thank you very much.
Thank you, David, for the great talk. So I'll open up for questions. Anyone has any questions? I think Sylvia had one.
Yeah, I did one on the chat because I didn't know if there was enough time. It's one of the concerns also of the reviewers. So how the explanation affect the predictive model? Like, it's not clear to me that as well, like how the explanation affect the predictive model. And isn't it possible that the user will want something from the explanation that negatively affect or influences the predictive model? I don't know if this makes sense to you.
Yes, so we have seen in some more challenging datasets that can occur indeed. So there is a way in which the user somehow understanding, or even if you generate, because we have basically simulated these experiments, the user explanations can actually be harmful for the predictions themselves. And that is basically a problem that you have to design very carefully your kernel. So you have to be very, very careful on what are the assumptions on your kernel and how you interpolate the points in the Gaussian process. So it is a very, very valid point, and I think we still have to do a lot of experiments to understand how to better resolve this problem.
Okay, I think we have around maybe 30 seconds to ask a quick question. If not, we can move to the next speaker. Or you can ask any other questions in the chat, in the Rocket chat in the website. Okay, thank you very much, David, for your great talk.
Thank you.
Can we have the next speaker share the screen?
Yes. Yes. Just give us.
Jalin.
Yeah. Hi. Yeah.
Hi.
Hi. Hi. Can everyone hear me?
Yes, Jalin, go ahead.
So we'll be introducing our work improving VQA and its explanations by comparing competing explanations. This is the joint work with my colleague Lian Chen and my advisors Raymond Mooney. First, we'll introduce the tasks of the VQA. It's about answering a natural language questions about an image. So for this image, the questions could be, is this in Asian countries? And you will notice that the train is actually from Japan, so the answer is yes. So most of the high-performing VQA systems treat these problems as a multi-class classification problems where they collect tons of answer candidates from the data sets. The numbers of the candidates should be more than like 3,000 or so. And then they feed the questions of the image into VQA systems, and then they output and logics for each one of the class. So the main drawback of these high-performing VQA systems is the lack of explanatory capabilities. So there could be some dataset biases that could introduce lots of shortcuts in these tasks. For example, the model may simply learn to recognize whether is this is in the questions and answering no if the is this exists, or rather recognize if there is red lights. Maybe they will just learn that red lights means no. Also, probably there are more US trains or US subways in the data set. So for these questions, even the model understands the visual questions correctly, able to answer it in a run answer. It may also be because that the key features are very subtle. In here, it's only the characters on the train's marquee that will help you to answer this question correctly. But it's just hard to let the system to automatically learn to focus on the train's marquee and notice what type of the characters what type of the characters this marquee belongs to. So to address these problems, we take advantage of the recent techniques. We use textual explanations in our project that we think if human could provide a sentence that tells the model which or where or why you should look at some place in the image, the model could make more rational and correct predictions for this complicated VQA questions. Then we'll introduce our key concept here, competing explanations. It's the plausible explanations that supports talk-directed answer candidates. So it describes the behavior the image or the question should have when a certain answer candidate is true. For example, for the incorrect answer no, so you will expect that the word on the train is in English to appear in the image. So that could be right. And of course, for the correct answer yes, the signs should be all in Japanese. Then we'll introduce how we collect these competing explanations. We first collect the answer candidates we want to verify. We choose the top 5 answers from high-performing VQA systems. Even though the system doesn't make a rational or interpretable predictions, but it actually raises very good VQA candidates. Then we use 2 approaches to collect those explanations for each one of the answer candidate. There is a retrieving approach that tries to collect the top 8 explanations with the most similar questions for the questions, image, and answers. And there's a generation approach that uses a trained explainer to generate the sentence for each answer candidates. We use the current good explanners in 2019 to ensure the quality. So then we'll introduce how we use these explanations. First, we first takes the original VQA input, VQA systems as input. The original VQA systems will give you a VQA prior confidence for each one of the answers. And then we use an explanation system. We use the explanation systems to either generate or retrieve the explanations from the training set, and then pass them together with the questions, visual, and answer features to a verification systems that tries to decide the supportiveness scores for the collected explanations to the current answer candidates. Then we combine these 2 scores together by multiplications to get the final accuracies. Yeah. So in terms of the verification systems, we train a very simple network which takes input the questions, visual answers, and the explanation features denoted by bolded Q, V, A, and X. And then here in the inquiry agents, each F means a feed-forward neural nets, and then the sigmoid means the sigma means the sigmoid activations. So that basically output a scalar range from 0 to 1 to decide how supportive of the explanations respect to the current image questions and the answers. In terms of the training of the verification systems, we collect the positive training examples by all of the VQA examples in the data set we use. So for each questions and answer pairs, there's the human annotates human textual explanations inside. And then for negative examples, because we don't have good ground truth explanations for incorrect answer, so we simply replace either visual or question features in the current batch, and the answers features within the top 5 answer candidates, and then the explanation features which supports the incorrect answers most. Then we'll present our experimental results on the VQA tasks first. We use 2 data sets. One is called VQAX. This is also where we collect our textual explanations from. This data set contains 33 more than 33,000 image question pairs. Each training pairs have one textual explanation sentence. And then we also use the standard large VQA data sets that there are more image inside. We also try two base models. The one is a simpler one. This is the winners of the VQA task in 2017, before all of the transformers birds coming out. We also experiment with our framework using a transformer model to verify the effectiveness. So we present the performance where we pre-trained our VQA systems on VQAX. For here, the orange and yellows are our performance using generated explanations. We achieved around 78 for if we pre-training on VQAX and test on VQAX test set. And then with the transformer models, we also improve the performance as well. We even get better performance if we are not generating the explanations by ourselves. Rather, we retrieve the explanations from the training set, which have the most similar questions, visual and answers features. And explanations for this is that when we retrieve explanations, we guarantee that the explanations is for the same answers and similar image and questions. But when generated the explanations, we actually, because this is from explainer model, so we are no longer guaranteed that the generates words sentence tries to support the original inputs answer candidates as well. So it is more noisy in the generations approach, in the generations parts. When we pre-trained our model on VQA version 2, which is a much larger data set, we get, of course, better results. And our models in both up-down model and LX merge models have the improvement if we add this competing explanations framework. So we then show some qualitative results. The questions here for these images was type of the fruit choice the cat is holding. Maybe by some dataset bias that the VQA system recognizes the cat, so it gives more VQA accuracies to the cat, so it will make a wrong decision, but also a fair confidence for banana because it's the case. But for our verification systems, the model learns to criticize that it is the fluffy animals is not the food, one of the food choice, and it's not the correct answers to the questions. So it decreased the VQA scores for the cat to 0.00 and remains very high for the bananas. So the banana finally win the battle and get the full points for this example. Also, this is another example, probably because of dataset bias, there's more milk inside. So the model learns to open milk, but the explanations tells you the beer, actually the beer is in the amber in color. So the verification systems helps the model to realize that the milk is a wrong answer. We also tries to use the competing explanations for better explanations. Normally explanation system takes the questions in the image and some answers as inputs and output the sentence. We also use the retrieved explanations as the input as well. So it provides the references to the explanations to similar visual questions and gives you a template about how similar questions are explained. So for this case, the question is what is the piece of the furniture used for? And we retrieved the explanations in the training set. saying this is a bed and pillow in the room. So the generated explanations could take that as input and modify these explanations to these more image-specific ones, and gives us a more impressive sentence. This is the automatic and human evaluations for the generated explanations. We use the Bayes system faithful explanation paper and add our competing explanations for the correct answers during the input process. And then we get better results on all of the 5 automatic evaluation scores. These are all sentence-based evaluations that are frequently used in image captioning. This measures the qualities of the sentence in the output. We also do human evaluations, denoted as AMT here. We compare it with we rank this of the we rank the explanations with the 2 models and see who wins. And then of the 55 points of times, and our systems achieves better human evaluation scores as well. Yeah, thanks all for listening.
Thank you, Charlie. I think Pat might have a question. Pat, do you want to? So the question was, NG and Mooney did early work on the role of coherence in evaluating explanations. Can you incorporate their ideas into your approach?
Sorry?
Pat's question was, Ning and Mooney did early work on the role of coherence in evaluating explanations. Can you incorporate the ideas into your approach?
Oh, yes. Yes, you mean when we generate the explanations, right? In the generation process.
Yes, I think, but Pat is the one who asked the questions. Maybe Pat, if you are here, you can clarify.
Yes,
sure.
yes.
Sure. Well, I didn't understand the details of how you were evaluating competing explanations, but there's this work that Ng and Mooney did back in 1990, where they talked about, they had a coherence metric. It basically was to what extent did different parts of the how well did the facts hang together through various connective links, and you could imagine doing the same kind of thing with a multi-layer neural network. And I am just trying to understand whether or not there's any way to incorporate a coherence metric to help evaluate the quality of your explanations.
There could be a way, but sorry for this, I'm not very familiar with Ray's that paper.
It's a great paper. It's very easy to read.
Yeah, I should have read that, but
I recommend it to everyone who's interested in explanation.
Are there any other questions? So I have a very generic kind of question. So it seems to me from the examples you gave, the question itself is very important as well as the explanation, right? So
yes.
What do you think about like maybe methods of selecting the correct question, something along that line? I'm not very much familiar with visual question answering, but are there any works along that line, or have you thought about that in your
I actually don't start in that line before, because actually in VQA that the questions the human provided in the data set and also the image, we don't actually have lots of chance to select which answers, which questions we should be able to answer for.
Yeah. So this came to my mind because you, in your example, in the trains with the Chinese or Japanese text and versus the English text. So it's important to know what question to ask, I guess. That's why I thought of that question.
Yes, great. But just in the data set that they provided us, and we don't actually have a lot of chance to select which one. And
okay, we have maybe time for one quick question. If not, we can invite the other. Are there any other questions? Okay, maybe if there are any other questions, please use the Rocket chat to mention that. Okay, thank you very much, Joelin. Very interesting talk.
Thank you for listening.
So the next speaker is Pulkit Verma.
Yeah.
Hi, can you maybe share your screen?
Can you guys see the screen?
Yes.
Great.
Yes, you can begin. Thank you.
Okay. So, hello everyone. I am Pulkit Verma from Arizona State University, presenting the work Asking the Right Questions, Active Action Model Learning. This is a joint work with Shashank Rao Marapalli and Siddharth Srivastava. So, if you have an autonomous agent, how would you determine that it is reliable or even safe for a certain task? Especially in the cases when you don't have the access to the agent's internal model, meaning that it is essentially a black box for you. In such scenarios, if you have a person, you can simply interview them. But could we do this for an autonomous agent? And if so, what queries will we ask? So for this, let's see an example scenario. So this is Alice, and she is an expert in biomedicine. Now she gets a new robot, which is a black box to her. Now, how can she determine that this robot is safe to use in a lab? If this was a human assistant, she could have interviewed, as I said earlier. But from a user's perspective, there's quite a lot of research on like how to get agents to answer questions effectively. But AI systems have different failure modes and performance profiles than humans in general. So it will be very difficult for Alice to figure out which questions she should ask and how to extrapolate the robot's capabilities from those responses. Now, to solve these issues, we propose an agent assessment module that queries the agent and receives its responses. Now, this module takes as input the user's preferred vocabulary, and like these are the terms that the user understands. These can be predicates. And at the end of the querying process, the model returns a user interpretable model. And the user gets an understanding of the agent's capabilities after this whole process. Now, in this framework, the agent need not know this vocabulary or the user's modeling language, and it can have an arbitrary internal implementation. Also, the user knows the names of agent's primitive actions, and even when it is not known, like we can, like without loss of generality, the first step can be like listing of names of these actions. Now, these assumptions on the agent are pretty common, and in fact, simulators are already used for verification, and their instruction sets have to be reviewed for their usability in such cases. Now, this paradigm also assumes that the agent can be connected to a simulator, which can help the agent in answering the queries. So now we will see like what a typical interaction will be like. So here the agent assessment module could ask a query to the agent on behalf of the user, like asking what will happen if it must perform a set of actions in a certain situation. Now the agent uses its own internal mechanism or a simulator to respond to the query. The assessment module can ask such questions multiple times until it understands the agent's capabilities and estimate the complete model of the agent. One of the major technical challenges and our main contribution here is to ascertain like what queries to ask and in what order we should ask them. So now we'll see like how we overcome these challenges. So at a very higher level, we generate an interrogation policy and use the agent's answers to estimate its model in a user interpretable vocabulary. in the context of this specific work, user interpretable means strips like, because such models can be easily translated into interpretable descriptions. Now let's see why. So here on the right, you can see an action in strip-like form. It indicates that if the precondition holds and the agent executes the action, the effects will occur. If the action is executed when the preconditions don't hold, then nothing will happen. In this case, it's saying that the agent will be able to pick an object if its hand is empty and the object is on the rack. And after executing the action, its hand will not be empty anymore, and the object will not be on the rack, and the agent will be holding that object. Now, such models have an advantage that they are clearly predictive, and they also allow counterfactuals and assessments of causality. These are also easy to convert into natural language. But one of the major problems is that there are too many such models possible, and actually exponential in terms of actions and variable instantiated predicates. So now we will see what a query looks like for our work. So formally, a query can be viewed as a function that maps models to responses. In our work, we use a specific class of queries called plan outcome queries. So these queries ask an agent what it thinks will happen if it executed a certain sequence of actions, like we call it a plan, in a certain initial state. Now, using its internal model, the agent responds with the length of the successful execution of the plan and the resulting final state. So now the next question is how do we generate these queries and how we use them to infer the agent model. So what we use is the concept of abstraction. So we take two abstract models and generate queries that in a such a way that their responses can help in distinguishing between these two models. So now we'll see what kind of abstractions we use. So now let's assume that we have this concrete model on the left, and on the right, you can see a possible abstraction of this model. Now, since abstraction loses information, here the information about how on table appears in action pickups precondition is lost. So here positive, negative, and empty indicate that on table predicate might be in positive, negative, or absent form in precondition of this action. So now we'll see how we'll use this in an algorithm. We will try to predict the model of an agent having the internal model set to this model shown here on the left. So now for each action, as I said earlier, the predicate can appear in two locations, precondition and effect. And we name such predicate, action, and location combinations as N1, N2, and so on. We also start with this most abstracted model, which is shown here in green. At this level of abstraction, we do not have any knowledge of how any predicate appear in any action at either precondition or effect. So we go ahead with the concretization using any one of these at a time. We can choose to refine them in any order. So for this example, I'll go in alphanumeric order, N1 to N4. So here we can add hand empty to the empty models. So in the precondition of pickup action in three forms, positive, negative, and absent. So here we show these three refined models as MA, MB, and MC. So now what we do is we pick two of them at a time, and we can pick them in any random order and generate a query which can distinguish between these two models based on their responses. We reduce this query generation to a planning problem. I will not go into detail that how it's done, but you can refer to the paper to see how exactly we are creating this planning problem. But for now, let's assume that it is possible. Now we pose this query to the agent, which responds using its own internal model or a simulator. Now we check the consistency of the responses of those two models with that of the agent. And based on this, we can reject one or even both of them in some cases. Now let's assume that MA's response was inconsistent with that of the agent. So we go ahead and prune that. And then we take the other two remaining models and generate a new query. we again do the whole process, like we again reject the inconsistent refinement. Now, remember that at least one of these three will always be consistent with the agent, because that would correspond to the correct model of the agent. An advantage of this approach is that at each step, we know exactly what we do not know till that point. So at this stage for pickup action, it is not known like how on table appears in both precondition and effect, and how hand empty appears in effect. This approach also provides convergence guarantees, as after refining each of these predicate action location combinations, like this N1 to N4, we reduce the set of information that we do not know. So this is hard to determine if we are learning passively from some previously observed data. So now let's see why this approach leads to less number of queries. Now remember that when we refine in terms of hand empty, we created three models, MA, MB, and MC. We show them here in three colors, gray, green, and orange. So now what would have happened if we didn't prune it at that time? So in that case, we would have had 9 models at the next level to consider and ask queries to. And like these are corresponding to 3 different concrete versions of each of those 3 abstract models. I think you can see like where this is going. Like by the time we reach the most concrete, level, we would have had a very large number of models. Like to be exact, 9 raised to the power number of predicates times number of actions. So when we prune a model at an abstract level, what happens is that all the models that would have been its possible refinements are pruned out. And by the time we reach the most concretized node, we have just 3 models in most of the cases. So a key feature of this algorithm and the central idea of this approach is that we are generating queries and pruning out models at abstract levels. Hence, we keep the interactability of the approach in check and end up asking less number of questions. Now we'll see some approaches which solve similar problem. Okay, so several approaches have been developed for learning interpretable models. Some of these use passively observed data as input, and the prominent ones include ARMS using weighted max set problem to learn this action model, LOCM, which uses finite state machines, LOUGA, which uses genetic algorithm, and PhRMA, which uses a custom planning problem to learn the action model. Now, but one problem of these methods is that they do not feature any interventions like during their inferring process. So hence they are susceptible to learning buggy models. So for example, if you have a robot that picks up only blue beakers in training, these approaches might learn that a beaker has to be blue for the robot to pick it up. Now, of course, with more input, these might learn the correct model, but there is a dependence on the input data, like whose generation is not controlled by these methods. Also, recently, Bonnet and Kepner proposed another approach which takes as input one or more label directed graphs, which encode the structure of the state space of those problem instances. This work requires no symbolic information, but is more suited for smaller problems because it generates a very large set problem, which becomes infeasible to solve for very large problem instances. For comparison of our work, we use PhRMA. You can refer to a paper for a more extensive survey of the related work. But for now, I'll quickly go through how we evaluated our algorithm empirically. So we tested our algorithm on 2 types of agents using symbolic sims, that use models from the International Planning Competition as the internal model, and agents using black box sims that report states as images using PDLGM framework. As I mentioned earlier, we use PhRMA as the baseline for comparison. This method PhRMA takes as an input a set of plant traces and learns the action model that conforms to those input traces. Now, since the focus of our approach is on automatically generating useful traces, we provided PhRMA with randomly generated traces on the same problems that we use. Now we will see how symbolic and black box sims work in more detail. So for the agents with symbolic sims, we initialize the internal model of agents with one of the 10 IPC domain models, and then we let the algorithm estimate the model of the agent. Obviously, the algorithm did not know what the actual model was. Then we evaluated the performance in terms of the accuracy of the learned model, the number of queries asked to the agent, and the time it took to generate those queries. We then compare the results with pharma in terms of stability of the models that are learned and the time taken per query. So here we showed results for the agent in the block-spread domain. So the solid lines show the model accuracies, and the dotted lines show the time taken per query measured in seconds. Here our algorithm was able to learn the correct model with just 48 queries. And as you can see, the pharma's accuracy keeps fluctuating because it is not guaranteed to converge to the true model. And this would make it very difficult to determine like when to stop the learning process, while in our approach, the convergence is guaranteed. Our approach also took less time as compared to pharma. In another domain called termies, which has negative preconditions, pharma again did not converge to the correct model as it ran out of memory as we were increasing the number of input traces. Here, our approach was able to learn the correct model with 134 queries, and also note that the time taken was not as much as pharma again. So this table on the left shows the detailed results for all the 10 IPC domains. It includes the number of queries asked, average time taken per query, and like variance of time taken per query to learn the correct model. To solve the planning problems, we used FD Planner with LM-cut heuristic. As you can see, for all the domains, our algorithm took less than 550 queries to learn the correct model. Also, except for free cell, our algorithm managed to learn the correct model in less than 25 seconds per query. So now let's see the agent with black box sims. We initialize the black box sims with one of the two domains, Sokoban and doors, provided by PD Tailsim framework. On the right, you can see these domains, Sokoban and doors. Now, similar to symbolic sims, we let our algorithm estimate the model of these agents. Now, these agents reported the states as images, like they only gave the final state images output. So the assessment module extracted the states from these images by using image classifiers for each predicate. We assume the image classifiers should be noiseless for this work. Now, on an average of 5 runs, our algorithm correctly inferred the Sokoban agents model with 217 queries, and for doors agent with 188 queries. Now, to conclude, we propose an approach for efficiently learning the internal model of an autonomous agent in strips-like form through query answering. And to achieve this, we use model abstraction and AI planning. Note that this method needs no prior knowledge of the agent model and requires only the agent to have a rudimentary query answering capabilities. And finally, this learns the correct model in user interpretable vocabulary with a small number of queries and in lesser time as compared to the closest related work that was pharma. In future, like we can extend it to handle noisy classifiers or to replace communication interface with natural language. After this QA session, if you have any further questions, feel free to drop us an email, and you can find the paper at this particular link. And we also had this paper in the main track of AAAI2021. You can access that using this particular link. Thank you. Like I can take questions now.
Thank you, Pulkit. Very interesting book. So any questions? Anyone? Let's check if there's
if there are no questions, I have one.
Yeah.
Is more like curiosity. So could you please define a bit more the notion of abstraction that you use it in this work?
Yeah, so a model abstraction, like an abstraction of like a model is something which loses some kind of information. So for example, if I have a robot which uses some sort of inverse kinematics, but then I can abstract the whole concept and say that, okay, robot can go from this particular initial state to this particular initial state, like it can move its arm, right? So now this capability I can completely abstract, like I cannot mention the underlying inverse kinematics at all. So like when we abstract any model, some information is lost, right? So that I showed, let me go. So here, right, so at this level, I do not know like how on table will appear in the precondition. So a model saying that, okay, whenever my hand is empty, I can pick an object. That is an abstract model because it abstracted out the information that the object has to be on the table at that particular time. So here I'm losing some information.
Okay. Okay.
I think Tathagata has a quick question. Maybe you can ask.
Can you hear me?
Yeah,
yes.
I can.
Yeah, I had a question about the setup itself. Like the generated queries, who are they for? Because the user will always ask what they want, right? And the query generation system, like regardless of minimizing the number of queries to get to the model, it's not like we are generating the questions for the user as well.
Yeah, so the questions we are not generating for the user. So here the questions are for the agent, right? So the user just tells that, okay, I want, like, I understand these predicates, like I can understand these concepts. I want to know the agent's model in terms of these concepts. So the agent assessment module knows what actions the robot can take or the agent can take, and it frames questions to the agent. And based on the answers by the agent, it comes up with the model in terms of that, for what the user can understand in terms of those predicates.
Thank you, Pulkit. I think that's all the time we have for questions. Thank you very much again for the talk.
Thanks.
Thank you.
So the next speaker is Nirmal. Is Nirmal here?
Yes, give me a second. Let me just share my screen. Is it visible?
Yes, so Nirmal Soba Karsa would present why are you
Correct.
Yes.
Okay,
Thank you.
you,
Go
Prashant.
ahead.
Yeah, so my name is Nirmala Skarta, and I'm going to present our research on interpretability for isolation forest anomaly detectors on behalf of my teammates at KU Leuven. So before we begin, anomaly detection is the task of predicting examples that do not conform to expected behavior. Needless to say, this is a very important task in many mission critical domains like fraud detection, intrusion detection in cybersecurity, and as such has spawned a huge family of algorithms, many of them like with impressive performance and computational complexity, but lesser work has focused on explaining the reason why these algorithms have been predicting these examples as anomalous. So that's the focus of our research. We focus on explaining the predictions of one such black box state-of-the-art algorithm called the isolation forest. Now, the isolation forest presupposes that anomalies can be isolated faster and quicker than normal instances. And how they do that is through a process called random recursive partitioning. So we start with a certain amount of trees, and each tree gets assigned a random subsample. Usually it's 256 in most implementations. And we recursively partition this subsample using randomly selected features through access parallel splits till either one of two conditions are met. Either the example is isolated or we have reached the maximum depth of the tree. So what happens is there is a connected concept called path length. Path length is the depth of the node where the example finally lands up. So when you have an anomaly like this, it ends up having a smaller path length than a normal point in the data set. So it reasons shorter the average path length, we get a higher anomaly score for that specific example. So this is the problem setting. What we would like to generate are anomaly explanations for these points flagged as anomalies, and each point would have its own unique explanation. And what the form that these explanations should take is that, like for instance, if we are trying to explain x1, then the component of this explanation vector along the dimension of attribute 2 should be much higher than attribute 1, because x1 is more anomalous to attribute 2 compared to attribute 1. Now, our 3 core contributions: we design a method that exploits the structure of IF and not requiring anything else to explain its predictions. We also design an experimental study to demonstrate that our method is comparable to some of the state-of-the-art techniques out there while being an order of magnitude faster. And we make our code publicly available on GitHub. So our core key insight is how important a feature is in predicting an example as anomalous correlates strongly with how instrumental it was in isolating it in the first place. So this key insight was distilled into 3 core intuitions that powered our approach. So the first intuition is as follows. If you take any one of the isolation trees in the forest, we consider only the split attributes for a specific example, and we do not care about the other attributes for that isolation tree. For instance, for this example, if you trace the path F1, F3, F1, so we don't care about F2, both only F1 and F3 are considered for this tree. Now, the second intuition, this is also the same as the isolation forest intuition. Split features are closer to the root if they are relevant. That is, like if the point is anomalous with respect to that feature, they get isolated there. And those split nodes that shorten an example's path length are the most relevant when they are imbalanced, which means they result in asymmetric child node sizes, and when the example is allocated to the smaller child, because it becomes easier to isolate from there. So how we went about designing a weighting scheme to assign suitable rewards for these node splits was inspired by how a binary search tree would treat this particular problem. So suppose we start with 256 samples. A binary search tree would have a perfectly balanced splits throughout. So each one of these 256 samples will be isolated at a depth of 8. Or in other words, there would be 8 node splits that take it from 256 to 1, which means that a single node split, a single perfectly balanced split would assist in the isolation of an example by exactly 1 unit step. So we reasoned that an imbalanced split where the point is anomalous across a specific feature should assist by more than 1 unit step. And from there, we kind of devised this weighting scheme, and we have assigned the score to each of these node splits based on the weighting scheme. So we can clearly see that 256 to 64 is a much better split than the equivalent balance split, which would be 256 to 128. So it gets a positive score. 64 to 48, on the other hand, is worse than the equivalent balance split. So it gets a negative score. And we do this process through all the trees in the forest, keeping track of all the scores that each feature accumulates. And in the end, we add them all up to get our explanation vector. So to recap, our weighting scheme actually rewards higher imbalance, larger parent node sizes, and when the example is assigned to the child node with a smaller size. So these were the 3 intuitions we began with, and our weighting scheme satisfies all 3 intuitions. So the returned explanation vector also has a nice interpretation, because the ith feature of the explanation vector kind of corresponds to the importance of the ith feature plays in isolating the example and predicting that example's label as anomalous or not. So as you saw earlier, if the weight is positive, then we can conclude that the ith feature was influential in making that point anomalous. If it's close to 0, little to no influence. If it's negative, it's actually counterproductive. It's worse than what the situation if it had been a perfectly balanced split. So a brief look at related work. What we are interested in is local explainability, and there are 2 very popular model agnostic methods that produce local explanations, which is LIME and SHAP. And although SHAP has been considered extensively in our experiments, our initial experiments found out that LIME as a setting is slightly unsuitable for anomaly detection, because the local neighborhoods of the points of interest of the points we are interested in do not actually approximate the global decision boundary of whether a point is anomalous or not, because they usually lie quite far away from the decision boundary. So we went ahead with SHAP. And the other model-specific method that was closest to our work is Diffie. It was created, I think, in the early part of 2020 by an independently by a research team from the University of Padua. So they do iterate through all the trees in the forest, and they assign weights to features based on the depth of the leaf node where the example lands up in a tree. So all the features involved in all the splits for a given tree gets assigned the same value. They don't get different values. So through our experimentation, we wanted to answer three main questions. Is our method producing accurate explanations for these anomalous points? Is our method more efficient, or at least equally efficient to state-of-the-art methods like SHAP? And why use our method when we have a good method like Diffie or SHAP in the first place? So the setup is as follows. We had an isolation forest made up of 100 trees and a subsample size of 256, which are common hyperparameter values. And we compared the explanations produced on the predictions of this isolation forest of our method, and we compared with SHAP and Diffie on both synthetic data and real world data. Now, one of the issues that we faced, it's actually a common challenge, was the absence of ground truth for these explanations. Because if we do not have anything to compare to, how can we say the explanation produced by one method is more accurate or more right than the other? So a second contribution was a procedure to kind of synthetically simulate a ground truth sort of a situation, where suppose we start with certain normal samples. We randomly pick n samples and we compute an initial explanation W0 for all of these points. Then I randomly pick m% of the features, a coalition of m% features, and I anomalize them. Say I set them to 3 times or 4 times the maximum value, causing this point to jump here. And I compute the new explanation vector, Wn. And I can compute delta, which is the difference between this new and old explanation vectors. And we reasoned that delta W should have high values only for the m% coalition of features that we used to anomalize the point. So this sort of allows us to generate an expected explanation vector, WE, because we kind of know the features that we use to anomalize it, right? And with that, we can compute a term like RMSE, because these are real valued continuous quantities between delta W and WE. So what we realized and what we found out was that our method was not beating SHAP, but it was quite comparable to SHAP in terms of accuracy. And with very similar curve characteristics, it's beating Diffie. But it is an order of magnitude faster than SHAP, right? So this would be very useful in online settings where these explanations are critical to come very quickly so that experts can investigate further. So to explore the difference between Diffie and our method a little bit closer, we created this toy example with 2 clusters of normally distributed points, and we had some pink colored anomalies peppered across. These are local and global. Now what we did was we started from here, and this hypothetical point has x1 values iterated from here to here. And we also iterated independently its x2 values from here to here. And we plotted the explanation vectors produced for this point by both Diffie and our method, right? And x1 corresponds to blue and x2 corresponds to red. So what we found out was, and these 4 charts correspond to 4 different settings that we set up. It's like specifics to how the isolation forest was trained, whether this new point was in the training set when the isolation forest was retrained, etc. So like the core intuition is that our method is able to produce explanations that kind of reflect the real contribution of each feature. For instance, if we move along this axis, we would expect x1 to have a higher value because that point is becoming anomalous with respect to the normal cluster along x1, till it kind of balances out because we can reach the same point from the top, where the point is getting anomalous across x2, right? So whereas in Diffie, it's kind of giving an even contribution of both features in the heat map. Now, to summarize, we kind of, we devised and we are presenting a method to explain the individual predictions of the isolation forest. And we use a weighting scheme that kind of evaluates how much each feature helps in isolation of that point, forming the basis of an explanation vector that we can create for a specific example that's flagged as anomalous. And for reproducibility and fostering research in this direction, we have made the code publicly available on GitHub. This is the link that's mentioned at the bottom. Our method is computationally efficient. It's quite easy to use. It does not require any expertise. It just requires only the trained IAF model. There are no hyperparameters to tune this network. And since it uses the model structure, it's quite intuitive to understand how it functions. And there's no additional pre-processing required. The absence of ground truth was slightly restrictive in the scope of experiments that we could conduct. So we had to design a quasi ground truth situation. And through that, we kind of demonstrated how our method is comparable to state of the art while being an order of magnitude faster. And lastly, some limitations and future work. Right now, this method is capable of producing only local explanations. We can extend this to global model interpretability by combining the anomaly scores produced by the isolation forest, the explanation vectors produced by our method, and host of other factors. We are also not looking at the specific values that make the point of interest anomalous. We are just saying it's anomalous across F1 and F2, say, for instance. So we should consider not just the feature, but also the feature values, because that information is also found in the isolation forest model. We can, of course, extend the method to more refined and advanced versions of isolation forests, like the extended IF and Psi forest. And since this method actually gives sort of like a relevant scheme for features in the anomaly detection task, it can also be used for a task like automatic relevance determination to find the most relevant features for the problem at hand. So yes, that's it. Any questions?
Thank you, Nirmal, for the talk. Great talk.
You're welcome.
Is there any questions? So I have a very kind of generic question. This is kind of like a blue sky kind of question. So, so in comparison to the contrastive kind of explanation methods, what would be the difference with those contrastive methods that provide contrastive explanations versus a method that provides like explanations for anomalies? Because I kind of see the similarities, but I also think there's like a lot of maybe there is differences as well.
I'm sorry, I'm not familiar with contrastive explanations. Can you give like a 1 to 2 line?
Yeah. So for example, like in Lime, you can change a subset of features and see when the decision boundary changes from maybe a one class to another, something like that.
Understood.
So that's kind of a simpler explanation for contrastive explanations. But what kind of differences do you see from those techniques versus anomaly detection?
So, like for instance, we actually tried out Lime, and SHAP is like relatively more stable than Lime in this regard. But one of the first things that struck us was the instability of the explanations that were getting produced, depending on the time we ran the experiment, right? So it was quite unreliable, and especially in a setting like anomaly detection, because on the basis of which experts would investigate the behavior of the systems further, we might have like a slightly higher error rate maybe, because if you compare the exact quantities, but we would definitely want to pick the features that are quite relevant. So that was one, because most of these contrastive link techniques, correct me if I'm wrong, kind of use this perturbation strategy to sort of drive these contrastive explanations, right? And these anomalies by definition are so far-flung from the dataset distribution that we don't know what we are effectively getting every time we sample. Some of the anomalies which are local in nature tend to produce relatively stable contrastive explanations, where our method is like more or less the same. It's doing the same role as say a Lime or SHAP, but we don't know that beforehand, right? So that's, I guess, why we need a method specific to something like anomaly detection specifically, according to my opinion.
Yes, yes. So are there any other questions? Maybe did Sylvia had a question?
Yeah, like this is often a concern that is related to many like interpretable machine learning works. So how does the identification of attribute importance links with a good explanation.
How does the detection of feature importance?
The identifying like attribute importance, how this is linked with a good explanation, because it's often like given for granted that if you have a good identification of attribute importance, then you have a good explanation. But
I understand. It's yeah, I think it is sort of like an assumption that many people take for granted when they do the feature importance study, and it's quite relevant to kind of question it. So from what we have seen, it does not directly translate, but what we've identified is that if we pick features that seem to play some role in isolating certain points faster or quicker, then surely there is something about these features, about these dimensions along which the specific point of interest is a bit anomalous across, because that's why we compared it with completely balanced splits. So since we were interested in creating a system which produces an explanation, you haven't seen an explanation, it would mostly be visual in nature, so it will be easy to understand. That should technically be one step which would inform the expert or user of a system to investigate further. So our system should be sort of like a stopgap where quickly it informs some investigation direction for some user of the system. So in that sense, I feel feature relevance or feature importance in a task like isolation could really help make the task more productive. Did I answer that question?
Yeah, I guess like it's more like related also to the definition of explanation itself. So
correct,
what you define,
and the purpose of it also, I suppose.
Okay, thank you.
Thank you, Nirmal. Thank you for the
opportunity.
So, so next up we have a long break. So after the break, we have a great panel with Freddie Lukur, Vera Leo, and Bin Kim, an industry application panel. So we will meet at, after the break, we will meet at 14:05 PST time, around 20 minutes from now. So see you again then, everyone.
Welcome, everyone, for our last session of the day. We will now have our panel. Can everyone hear me well?
Yes.
I can.
Thank you. We'll now have our panel on industry. I'm Rosina Weber from Drexel University. I'll be moderating the panel with Prashant Madhumal from University of Melbourne. I would like to welcome and invite our panelists, Vera Liao from IBM Research AI, Bin Kim from Google Brain, and Freddie, where are you, Freddie? From Thales in India. I would like to get started by inviting the panelists to give a brief introduction of themselves rather than me doing that. Bean, would you like to start?
Sure. Hi, I'm Bean.
I can hear you.
You can? You cannot. Oh. Boo-hoo.
Oh, we can hear you.
I can hear you.
Oh, I hear you. Can you?
You are not muted.
I can hear you.
I
Wait.
suggest
Can you or can you not hear me?
maybe you have to
No, we can.
switch off. Maybe you mute yourself and then mute again. See if I can see that. If I don't see that, usually your audio is not connected. Could that be?
No, I think
it might be a problem with your audio
her.
because the rest of us can hear her.
You do?
Yeah, so we all can hear her. So I think it might be a problem with your audio.
Okay. I thought there was something wrong with my sound.
I do need Rosina to hear me, so I think we're gonna fix that.
Okay, thank you very much. So I made a fool of myself already, so nobody has to worry about that anymore today.
Perfect icebreaker.
Something strange. That's why I asked if people could hear me.
All right, so can you hear me, Rosina?
Yes, thank you.
Wonderful. Okay, great. Yeah, so I'm Bean. I work at Google Brain. I work on interpretability since I was a researcher. I'm in a fortunate place where I get to experience sort of academia and industry at the same time. I'm involved in many academia work, like being an area chair and going to conferences, pretty much every conferences there you can think of, and also at the same time interacting with customers, sort of internal customers at Google who use my work and have a lot to complain about either my work or other work in general in interpretability. Looking forward to discussion today.
Thank you very much. Freddie?
Yeah, could you hear me?
Yes.
Okay, fantastic. So, so my name is Freddie Lecu. I'm leading the AI and the explainable AI activities in Thales. So Thales is a group which mainly deal with critical systems. So there are systems you can think about trains or any kind of vehicles, and we equip those vehicles with machine learning systems for detecting anomalies, for helping them making particular missions in identifying particular objects. And they're very critical because they may have huge impact on people and on the system that operating them. And my role, and I'm based in Montreal, and the role of my team and myself is try to explore the limit of those machine learning systems and try to detect and identify, well, how we can build systems that can provide explanations. And it's in a particular field where certification is very important, and trust is also a very important factor. So so my team is trying to deploy a system that could be deployed in a safe environment. So they could be for developers, but it also could be for operators or just experts who doesn't necessarily have an understanding of the technical expertise of the system. So much more on trying to help them making the right decisions and trust the system. So from a developer perspective, but also from an operation perspective. And so explanation is very central to the work we're doing, and any system where we deploy machine learning need to get some sense of explanation. And we have really different kind of flavor where we deploy explanation. So that's myself.
Thank you, Freddie. Vera?
Hi, I'm an HCI researcher working at IBM Research. I have been working on human AI interaction for a while. First conversational agents for a year, then moved on to more general machine learning system. I started looking at explanation as more of a byproduct, because whenever we think about interfaces of AI system, we think about how to help user understand it. So we start incorporating explainable AI in conversational agents, and another project to help people judge model fairness. I really got into the topic was in early 2019. I joined a group of AI researchers. We built an open source toolkit on explainable AI called IBM Research AX360. So it provides comprehensive educational and technical resource on the topic. We try to make it accessible for practitioners. It's when I really start understand the landscape of the community, and I start asking this question. The research community always has been very productive, but has these techniques being used, or will they be used by product teams? So I spent some time talking to product teams, especially designers, user experience researcher, because my interest is more on the design opportunities and design challenges. And since then, I've been working on understanding this design space of explainable AI and try to come up with concrete guidelines and tools to help practitioners to navigate the space. So I'll share a few things I've learned today and looking forward to discussion. Thanks.
Thanks, Vera. So next up is the panelists would speak for like around 5-7 minutes, and we can open the questions for the audience as well. So I want to present kind of a broad question. So I would like the panelists to share their perspectives and experiences about the most significant advances they have recognized in the field of XAI, and also how they may have influenced academia versus industry and research versus applications. So maybe who likes to go first? Maybe Freddie or Dean?
Let's keep the same order to make it easy. Dean,
Yeah.
please.
Sure. Let's see. Share the right tab. Can you see?
Yeah.
Am I sharing the right tab? If I full screen, I can't see anybody's faces. Do you have advice?
I think there's this view in the full screen method where you see a strip of. I don't know how to make it. Let's see.
Are you saying full screen is better? It's just full screen. I just can't see anybody. So if you're making faces of skeptical faces, then I can't see you.
We'll tell you.
Yeah, please do tell me. Yeah, so the organizers kindly offered the questions ahead of time, so I had a little bit of time to think about it, and I prepared a couple of slides because it's easier to talk about this way. Significant advances that I like is having some skeptical thoughts about what we are doing and where we're going, and also putting users in the center. So when a field starts, there's a lot of excitement, excitement about technique and what this technique can achieve. You know, the same thing happened with deep learning when 2012 AlexNet came out, and everyone was like, oh my God, this is the best thing, until maybe a couple of years later, GAN came out and people were like, oh, okay, this is not perhaps a rosy dream, as rosy as we wanted to. And then the field matures, we learn things, we iterate, and that's really when the science starts. So here's a set of work that and there's many others that is starting to ask that question and having skeptical about our progress. Some of the work that I want to point out here, you know, first one on the left, where they attacked saliency map and can basically make it attend anything in the picture. There's some other work below it that questions traditional convention about attention mechanism. Is it really interpretable? With a nuance that, no, it isn't, it may not be. Some work on the right that questions popular methods like Lime and Shapley to ask, what are the limitations of such methods? And one on the top where we, a work from our team where we added a constant value to every single input, and it happens to be a cat picture for fun, why not? And we show that any saliency map or the saliency maps that we tested in the paper, we can actually make it attend to that cat faces, even though the cat faces are most likely not very important for classification because it's in every single picture. And we call this catastrophic attribution failure. Particularly, I want to talk about this sanity check for saliency maps work that Julius and a couple of us did to just kind of engage where we are in this process, because the question that we ask in this work is very simple, and also to highlight asking these skeptical questions isn't that hard. So here's briefly what we did. We took a neural network that works pretty well, that actually superhuman performance, and took many images and got saliency maps from all of them. And then we took the same network, copied it, and started randomizing the learned weights of that network from the top layer one by one and the bottom in a cascading fashion. So as soon as you randomize any weight, the prediction is random. So you would think that the saliency map, the explanation should change, but we show that it doesn't. And we show this for many, many popular methods, one of which is my own work, where we show when you randomize the weights and now prediction is random, the explanation actually doesn't really change. Now, one might ask, well, maybe that's okay because maybe it's showing the features that it might have used and not the prediction per se, but still it's like picking out something useful. Here's why this is a problem. Let's suppose you went to a doctor and doctor was using this deep neural network to diagnose a cancer. And he looks at the saliency map and which highlighted many, many cells in your biopsy. Maybe it's in your brain or maybe somewhere, in your body parts. And he says, I got to operate you because, clearly you've got some cancer. And because saliency map showed the candidates for cancer cells, not the cause of the prediction of cancer, but things that maybe could have been cancer. Now you're being on an operating table, and perhaps doctor might end up removing some healthy cells because that's what he believed that model thought predicted the causes of the model's prediction. And this is kind of, obviously made up example, but when we're thinking about interpretability method, we really have to think about the implications of it, like how this could be used and what are the consequences. And what I'm highlighting with this made up story is that consequences could be quite significant. And when we are promising the evidence of prediction, these pixels are evidence of prediction, we have to hold them in that high standard and hold them accountable. Some academic influence this work had created a series of work that help methods to pass this simple check and so on. But what I really want to highlight here is that this is only really a starting point. There's been since many other work that asks better sanity check question, a little more higher standard sanity check questions. And this is exactly, I believe, where this field should head and to make ourselves, keeping ourselves healthy. Second significant advances I want to talk about is user-centric view. There has been many work in HCI, actually, of Vera's work is also here. I actually didn't realize this until now. That think about asking these important HCI questions about, how to design that interaction, how users digest that information explanation, and how do we help them to do that better. And I want to talk a little bit about my work here, just to highlight that these user-centric views don't have to be always HCI-centric. You can actually make a method to be user-centric. And here's what I mean. So this is work that I did a couple of years ago on testing with concept activation vectors. And the idea behind this was pretty simple. Let's give humans control of the language that they want machine to speak. So let's give them quantitative explanation of the concept that was important for prediction. Example is better than better in this case. So let's say you have a popular pizza classifier, and you have a network that takes a pizza picture and say this is popular or not popular. Now, as a restaurant owner, what makes sense to you is the ingredients that you're going to buy. Is it going to be tomato? Is it going to be fancy cheese? Or is it going to be some beverage that goes well with the pizza? And these are language that you speak, the concepts that you choose, and make the machine speak your language, as opposed to trying to understand computer's language, which is pixels, and trying to squint your eyes to see, is tomato more important here, or is it the cheese, and so on. And you know, I was really happy to see the influence of this kind of user-centric approach in both academia and industry. Academia, we've seen this method used for many medical applications, radiology, breast cancer, and what's the word, pathology, and also storm prediction, where Eric used this to explain category classification of storms. Sundar talked about this as a way that Google is making an effort to make machine learning for everyone, and UNESCO also recognized this work as one of the things that will be important in the future. That's it for me.
Thank you, Tim. May I open for the audience if anyone has any questions now? Okay, so let's continue, and then we'll have questions at the end. Freddie?
Yeah, sure. Okay, let's share my screen. Okay, so I definitely agree with what has been mentioned. So in terms of work and the recent progresses in explainability and interpretation in the field, there has been a very huge progress of. Let me make it bigger. There has been a huge progress in the field, and so saliency maps and all the attributions and gradient-based techniques, they have been here and they have been evolving over the last couple of years with much better evaluations and much better quality for identifying which part, particularly if we focus really on an image content. If we do classifications or object detections, for detecting which part might be responsible and what are the saliency part, and I can say more than it's very nice way of progressing the explainable AI interpretation field. Another complementary directions is what I'm showing now on this slide is trying to get a bit more. Try to capture a bit more semantics of what the model is capturing, and by semantics I really mean that again we focus on the neural network architecture for as a way to solve a machine learning task, and it could be at the neuron level. So we have seen work from Google, and now it's shaping some of the work from OpenAI on circuits and really try to visualize what the neurons and what are the texture is capturing. And there have been very nice libraries like Lucene for capturing these informations, and that gives some kind of rationale for a developer or for a person that want to interpret or capture what's going on in. And then you have other work, so Concept Sharp and also recently presented at NeurIPS, some work on compositional explanation. And there are some work where they analyze the neural network and they basically try to label what's the meaning of a neuron and what it does capture. And we have different ways of doing it. You can just feed forward all of the data that you have, and based on which activations level you have for each neurons or some particular layers, you will get you can capture some semantics of the concept. So if you have particular objects in an image and that's activating very strongly some neurons, then the assumptions or the rationale behind is they are strongly activating it. They capture this concept or this object. So if you have a picture with a rabbit and it's on the grass, and you have the concept, and you just feed forward these pictures, and some neurons are more activated than others, well, then you start computing the semantic representation, what those neurons are capturing. And you see more and more of those kind of flavor of paper or research, which I think is it's very interesting from a human perspective and from an operator perspective. And the reason why is because all the Silency map work which has been done so far, it's basically you take the input and the output, and you try to figure out what might be the chemistry going in the neural network, and show to the user, okay, this is what the system pay attention on, and this is basically why you end up with such particular classification results. And I think when I'm talking with stakeholders, or they could be developers, they could be operators, at different level of expertise, what they mean by explanation is not only the final output, but really some are really ask the question about, well, how can we do the inside of a neural net kind of queryable somehow. And then if you start to have those kind of some kind of semantic representation or some kind of representation that you can start exposing interpretation, that will be useful for human. And the work from ACE is also going to some extent to, in this particular way, of trying to add a bit of representation of what's going on in the neural network. And I've seen really this kind of recent work is probably bringing the field of explanation in AI a bit further, I mean, particularly in the machine learning domain. And what also I've seen, and we also all seen is, I mean, if you look back 4 or 5 years ago, it was mainly explanation for machine learning systems and deep neural net architectures. And now if you look at the different workshops, you have workshops in all major AI venues. So people in planning, they care, I mean, we've seen it today, they care a lot about explainable in the planning. You see it in robotics, more and more work on reinforcement learning now. So I think it's slightly shaping an interesting research questions on how we can expose explanation for the different users and for the different kind of AI community. So semantic is one dimension. So that's something I wanted to touch. And here there are examples of papers that you can look at further. Another dimension which I'm not seeing much, it's really explanation. I mean, when I'm discussing with the stakeholders, usually they don't see it as a one shot. So they don't expect the system to come back with, oh, this is the reason why your model is doing such a classification or regression or whatever is the machine learning task you're trying to solve. Usually different people, I mean, think about a teacher in a classroom. They try to convey maybe a complex concept or complex new solutions to a problem, and it's not every students will capture it in the first shot. And usually people, I mean, for user and for people and for students, you need to convey different and use different vocabularies, different way of presenting a solution so people can understand. And maybe in the first shot you'll get 60% of the people, but the 40% remaining you need to have a much more interactive way. And I think it might be interesting to look at how you can expose an explanation in a multi-turn or multi-ways. So then people can ask questions, and they can, and based on their knowledge about the domain or maybe about the problem or the solutions or about their users, they will go different ways. And I think the multimodal and the multi-turn way of providing explanation is very important. For a developer, it might not be as important because they want to make usually the model better and not having any fairness issue, for instance, and they need to get signals so they can fix it, or they get more data or make it more robust. But for others, you need they might need this interactive way of, you need somehow to guide them in the explanation that they need, and not everybody needs the same thing for making a final decision. So yeah, on the evaluation, it's also something I wanted to mention that had been mentioned by Bin earlier, but it's again, if you look back 4 years ago, explanation was mainly a system-based evaluation. The users were not much in the loop, and now probably most of the papers you see on the field, you see much more and more user evaluations, maybe mechanical Turks, which might be questionable for some tasks, but you see more and more of those users, and I think we will need more and more of the expert or the practitioner that will make use of those explanations. So I think it's nice to see also much more work in the HCI space and with much more user evaluation. And we've seen paper at NeurIPS last December that try to figure out which explanation you need for a particular task. And again, the result that you may get on those papers might be questionable, but it's interesting way of evaluating explanation systems. So that's I think the very new interesting directions or progress I've seen in the XAI field for the last couple of years.
Thank you very much, Freddie. So let's move on to Vera now, and then we can open for questions.
Okay, let me share my slides. I hope you can see my screen.
Yes, thank you.
Yeah, I think I would talk a little bit more from practitioners' point of view based on my conversation with them, but keep in mind I live in this bubble of IBM world, and obviously I will draw heavily from my HCI perspective. I think an obvious advance is that the AI community have produced a rich connection of AI algorithms. Recently, we're also seeing a surge of open source libraries and toolkits, mostly focusing on machine learning. They are making this outcome of academic research into practitioners' toolbox. And another advance, I think, is something happening in parallel here. In the academic community, we are really seeing more interdisciplinary perspective, both being and Freddie touched. So perspective from social sciences, cognitive sciences, HCI, philosophy, law. For practitioner, as now they have access to this toolbox, I think products in many domains and different roles really start to appreciate the importance of explainable AI. But I use the word towards real-world XAI. I think they're not exactly a common presence in consumer-facing AI products. They are more used in certain domain by certain role, for example, data scientists. But things are more complicated if you think about different kinds of explanation, for example, post hoc technique versus interpretive models. But now I just use the word towards. People really appreciate, start thinking about it, but we're not quite there yet. A little bit more on this interdisciplinary perspective. I think the first point Tim's talk has covered perfectly, the gaps between algorithm output and forms of human explanation. Another part is also the plurality for people, the motivation for people to seek explanation. Diagnosis is only one of them, even though we tend to talk about model diagnosis when we think about explainable AI. But explanation is also sought for sense making, for predicting future, for justifying past, for reconcile cognitive dissonance. Explanatory power is recipient dependent, and some would also argue depend on the question being asked. A how question, a what question, why question, what if question, they will require different explanation. This is called explanatory relevance. Adding to the complexity, I think are talked a little bit less is one is the cognitive process. For example, system 1 and system 2 thinking, they also have implication for how explanation is consumed and how they impact people's attitude. For example, people's trust in AI. And also recently the recognition that AI systems are socio-technical systems, so explanation should also be socially situated. So now practitioners start having access to this toolbox. And whenever we have a toolbox, there are two questions need to be answered. One is how to select, right? In a particular domain for a particular user, how do we select the most suitable XAI technique? And second question is how do we translate? And by translation, I mean, how do we translate technical advance made by academic work into user experience that's usable, effective in a particular socio-technical system? So I think this kind of high-level points from social sciences are very useful. I also want to point out two additional areas of work that really kind of push us towards that direction. One is to produce taxonomies and guidelines to help us navigate this space. On the left-hand side, recent work start producing taxonomy to classify this large collection of algorithms with varying level of granularity. Based on our experience, practitioners really appreciate those things. They find it particularly informative, helpful. On the right-hand side, their work starts to categorize important user group or contexts that explainable AI is needed. For example, for decision maker, system builder, regulator, and end consumer, or people being impacted by AI. So this kind of taxonomy are a good start point to start consider this kind of guideline on how we select from this toolbox. But HCI perspective is also high-level guideline is not enough. We always need to empirically design and evaluate them to understand their effectiveness and also to understand how to make them usable. So I picked a few notable work. So the conference IUI and CHI are the premium venue if you're interested in HCI work on this topic. So we're really seeing this booming effort in the past 2 years, but the HCI community do have a longer history studying how to make computational system transparent, explainable, early days on recommender system, then context-aware system. So the recent work around explainable AI, one area work focused on evaluating explainable AI technique and understanding their limitation. For example, Akuraway's work, they use this simulatability task, basically predicting the AI's judgment in unseen cases after the user have seen some cases with explanation. They use that to evaluate saliency map and basically find that, yes, saliency map could maybe provide some local understanding on how the model makes this particular decision, but it provides very limited help for people to really understand how the model works and be able to predict this decision. Even if explainable AI technique can help user achieve better simulatability in this kind of proxy task, another study shows that they may not necessarily translate into better decision-making in actual usage. And another area of work focused on building explainable AI system in particular domain. For example, for model debugging tool, our work on model fairness, for medical decision support. A common theme of this work is that they often provide not one, but a collection of explanation and recognize that there's no one-fits-all solution, different usage point, people will want different kinds of explanation, and the system should be prepared to provide those explanations. So to summarize, I think the advances, the academic research really make it into practitioners' toolbox, and this interdisciplinary perspective starts to inform the selection and translation of how to use the toolbox. But it's not a solved problem yet, and I will discuss some of the open questions later. But I will stop here and open for discussion.
Thank you, Vera, very much. We have 2 questions here. Tobias, would you like to ask it yourself?
You mean, do I repeat the question and answer? Oh no, Rob.
Yeah, I can ask it myself. So thank you, first of all. And I really liked the TCAF paper, for example, but when reading it and also trying to apply it to our own work, one problem that we have is like finding the concepts that the model is using. And I'm always wondering if I'm not imposing some of my own knowledge into the model, which is something that we've seen users do a lot during user studies. And especially with those concepts, I'm asking like, what if the model is not even using our language? We're just imposing it on them. Like, what can we do here?
Mm-hmm. I like that question, and do for me the paper and user studies and interesting findings if you have it. But to answer your question, it's a great question. So we thought about this a lot. There are two ways. Neither of which were perfect, but one a starting step. So first, it's totally true. If you define and pick the concepts, then you are sort of fitting the model's framework into that shoe, right? And you ended up getting something similar to confirmation bias, which is a problem. So to mitigate that, the follow-up work that we did, ACE, which Freddie kind of touched on, actually lets model to decide which concept it learned, as opposed to humans telling model, okay, here are the modular language blocks that you're going to use. It works for image domains. We tested only with image domains. So if you're not image domain, then I think there's opportunity there to investigate a new discovery method. But that's basically discovering the concepts automatically. Now the second question: what if? But even then, like, what about TCAP alone? Like, how do we prevent that from happening? One way we do it is to do the statistical testing. So, you probably already know this, but one part of a TCAP, you give me concepts of dinosaur in my pizza classifier, and clearly it shouldn't be important, the dinosaurs. Then what TCAP would do is, okay, well, I'll take this in and test it out in my model space, whether this concept of dinosaurs is different enough from random concepts. And we do the t-testing of statistical significance, and only if the concept passes that test, then we're going to give the users the number TCAP score, how important that concept was. Otherwise, TCAP is going to say, well, sorry, you thought dinosaurs were going to be important, but it isn't. Go find some other concept.
Thank you, Bing. Next question is from Rao. Would you like to ask?
Hi, guys. Okay, I'm sorry. So I basically am asking like a more philosophical question, because all three of you, at least the first two of you, are doing this, which is let the machine learning system sort of say what features seem to have been relevant in its classification in coming up with its decision. But in general, some people worry about this whole idea of reconstructive explanations, because they're sort of, you could tell people what they want to hear as against what the system actually did, which I guess sort of Tobias was also bringing up a little bit. But at the same time, if you don't do that, they don't actually accept the explanation. In fact, I'm actually surprised, being that you said that the later part of your work, you have let the system come up with its own concepts, which again makes, which sort of removes the use of, the motivation that you gave for the human understandable concepts. Because if the system comes up with concepts, it's not at all clear to me why they should make any sense to the human. I mean, it could come up with concepts that all look like amoebas. They're all different amoebas, and they made sense to the machine. I mean, you used words like dinosaur. I would be extremely surprised that things like dinosaur would be the concepts that a system would come up with, in trying to kind of, if that was the case, then we wouldn't have this adversarial example problems, right? So I'm just sort of wondering, we're stuck with having to give explanations that people would accept, which also means that there is no real way of proving that this is sound with respect to your reasoning, because it's a learned system, a purely learned system. So to what extent is explanations that are those kinds of explanations ethical to even provide? except in the cases where the person receiving the explanation is an expert, and so they're using it to debug the system rather than to actually understand whether the system is doing something reasonable for them.
Thanks for that question, Rao. I saw you asking this question and I was like, oh, he already know the answer, and we just want to chat about it. I think what you're raising is a serious problem in interpretability. And actually, I'm going to talk in the next question about the evaluation aspect, whether we are echoing what humans want to hear, or are we giving them actually what the model actually thinks. And one way to do that is to jump the line. One way to do that is to use ground truth data set, which we have, and lots of folks suggested ground truth based data set. We just don't have one data set that everyone agrees on. And I'll touch on that, how one might be able to go about in doing that. I think it's extremely important. In fact, one of the goals of interpretability that I think is to tell humans what they don't want to hear. And I hope that gets to the core of what
the evaluation of those could be very hard, because if people don't like your explanations, you can just say you didn't like it because you didn't want to have the truth, like that, a few good men quote.
Which is why you need a quantitative explanation. Now that what you just said happens in saliency map, when people look at it and say, oh, here's some bright spots in pizza tomato and not the crust. And you can argue about that. Like, I think the tomato is brighter. Oh no, I think the wine is brighter. Whereas in the quantitative explanation, there's a less room for that subjective confirmation bias. Because if I tell you tomato is 60% and cheese is 30%, you can't really argue with the numbers. You still have a room for arguing the explanation might be incorrect, but you have less of the subjective playing in the role.
I'm not sure that I agree with that. Giving numbers somehow makes the explanations more palatable, right? That's not necessarily clear to me. I mean, maybe you have a point there, but I just don't see it, because I can always make it harder for people to question my explanation by giving all sorts of bells and whistles, such as these percentages, like, in fact, you can make it sound particularly precise, like 36.735% or something. And not clear to me that adds anything further. If I had problem with the explanation before, I probably could still have the problem. It's just that
I'm puzzled how you can question the percentages. Like, so the question that you're asking, and perhaps I'm answering the wrong question. The question that you raised is, if they don't like to hear if they didn't hear what they want to hear, will they not take it? And so just by giving them what they want to hear, that's a problem. And what I'm trying to say is, yes, it is a problem. In fact, I think it's important to tell them what they don't want to hear. And one way to convince them that they are hearing what they don't want to hear is giving them something that is less subjective, which an example of that is a number, as opposed to looking at brightness of the pixels.
Okay.
Any comments by Vera or Freddie about this?
I agree with Rao.
Vera, any comments?
I was thinking about Bean's comment on this novelty of explanation. I just have follow-up comments. I think that also depends on kind of the goal of explanation. I think in certain contexts, you do need a coherence. So whether it's novelty first or coherence, that depends on the context. And also the novelty part sometimes is also a way of, if it's a long causal chain, for example, when people explain, right, we tend to skip the part that can goes without saying. So that part can also be skipped. So maybe that's also a part to be considered.
Thank you. Freddie?
Thank you.
Do you want to?
Yeah. So I think the question was good, an interesting point, right? Because well, what's the role of an explanation? It's, well, usually as human, if you ask, if you're questioning a process or solutions or a concept that you didn't get, you ask for an explanations to get convinced that you're right or that you're wrong, but you need more arguments or more information. So basically you're starving for more information. And this is what the human is asking more, and when we're dealing with our operators as stakeholders, they don't really question the final solutions. They try to get information that will help them making a statement about what is this model trustable or not. And providing explanation is something that they should be used and they should be consumed. So I think what I've seen is that this explanation, you would have two angles. Either you get closer to the model and you basically try to get too close to the decision making, or you try to get too close to the human and try to help them making a final decision according to the whatever explanation has been provided. So I think it's important to be considered that sometimes you need to stretch and you need to and the explanation that you get out of the model, which is using the data and the statistics and maybe the confidence, or it's maybe one thing, but if you really want to convince the expert or the human which is really behind, you need to have a much more rational based explanation. And that's why when I mentioned the multimodal or the interactive way is usually a one shot won't be helpful enough for the human to make a decision. I mean, you can still do quantitative evaluations and have metrics and say, okay, that's the right explanation because of all of these quantitative results. But then at the end of the day, did you manage to convince the human or the user? It's questionable. So I think different techniques have their pros and cons, but I think somehow many are missing the connection with the human, and somehow what Tab just mentioned at the beginning about how you message the explanation for the human in the language or in his understanding or in its expertise. I think it's important. How you do it, well, I don't know, because it's a tricky question. You basically have the model and then you build a machine learning system on top, and you're expecting the explanation to come out of the box and being convincible for human. And how you do it, well, there's no magic. You need to bring the human in the processing and then try to, I don't know, provide some kind of tutoring or some kind of annotations, so then you can get the data and the model closer to the human. But I think it's something very important for explanation field is really for the human, right? To trust and to be aligned with whatever the model will be building. So you need to be convincible, and quantitative result is one thing, and the quantitative part too. But then how you message it in a human understandable way, it's something very important, I think, too.
Thank you, Freddie. What if we move to the next question now?
Oh, can I add one thing, Rosina? I'm sorry. I just saw Pat. Nice to see you. I think I see you in AAAI conferences last year as well. If you have questions and further want to discuss this, I'm happy to. I think one of the ways to make the field move forward in a positive and constructive direction is to have that conversation and why we disagree, and then that's where we learn things from. And same with Rao, of course.
Yeah, well, right. But my point is that I agree with Rao, and if you want to follow, you should follow. Maybe all three of us should do it. So I'm happy to have a joint meeting.
Happy to.
I think we have another question from Mudit. Mudit, do you want to ask a question?
Let's move to our next question because it's time. And then I think Bean is going to complement her thoughts, and then I think we'll be in a better position to complement this discussion.
Right. Okay, so the next question, so the panelists would share their perspectives and experiences about the opposite, the limitations of the current work, and maybe about the open questions they have recognized in the field of XAI. and how would these impact academia versus industry and research versus applications, about the same format with the last question, kind of the opposite. So would Bean like to go first?
Yeah, do you see my screen?
Yes.
Yeah.
No, this the right screen. All right, I don't see you anymore again. Right, I want to start with what is not a limitation. I don't think it's a limitation that interpretability cannot be defined using math. And you can ask psychologists who's been trying to do this for centuries, why humans simply can't be defined using math. In fact, and one might argue this makes some people uncomfortable because don't we have to define this first in math so that we can optimize and so on? Well, the real life problems, lots of real life problems aren't really definable using math, right? And this is probably resonated by the panelists who are in industry. When you meet with people and learn about their problems are largely different. What they want to hear is different. If the model is doing something that is undesirable, the way that you can raise that in a most effective way is different. It becomes very complex problem, just like kind of how Farah touched on it a little bit. But this being said, a lot of open questions still exist in this area. How to encode this human aspect, the interaction, their biases. And I read into this work recently from IBM to think about this cognitive biases in this in an AI framework and modeling that using Bayesian learner, which I find really interesting and promising direction to head. It is a limitation, and I promise to talk about this, the evaluation is still our limitation. And I find it interesting that Freddie's advances, part of the advance Freddie was talking about the evaluation. It's true, it's been better over the course of the last many years. The evaluation of folks start doing more human experiments, so folks started using ground truth data set. That's really great. I'm hoping that we will have at least a few standard ones that most of the papers can benchmark against at some point, and then perhaps my limitation slides would go to advanced slides. Finale and I wrote about this in 3 different levels of ways to rigorously evaluate interpretability methods. There has been many work after this to complement and compensate ideas from this paper. Now, on that, I want to go through pretty quickly about an example of what I mean by ground truth data set. I'm hoping that this example would inspire us to think about how we can do better. What are we lacking in this particular experiment? And maybe perhaps some different ideas that folks might think of. So this experiment is about if we have a ground truth of which part of an image model pays attention, can we measure that, and can we make sure that our new method matches that ground truth? So here's what we did. We have an image, and we programmatically wrote a caption. So if there's a cap in the image, we may write a CAB cap or something else. Why are we doing this? Well, we're trying to create an artificial 2 concepts, an image concept and a caption concept. And by doing this, we're allowing models to use either image or caption for classification. And we encourage different models to different things by changing that noisy level. So 0% noisy data set means whenever there's a cap, I'm going to write CAB cap. 100% noisy means that whenever there is a cap, doesn't matter what's in the image, I'm going to write whatever I want, tiger, soccer ball, and so on. And so we created 4 different data sets. And how do we figure out what model looked at? Well, we can test these models with no captions. And because these images have no caption, if model cared about the caption, it's not going to do very well, which means that the test accuracy using this data set can give you the ground truth of the importance of image concept. If image was important, you're going to do pretty well when there's only an image, not the caption. So we test TCAP method using this for a couple of different classes. For CAP data set or CAP class, we show that none of these 4 models looked at the caption. Everyone looked at the image, which we know because of the blue line, the testing score with no caption was pretty good for all models. And we also show the green line, the TCAF image importance for the image was pretty high, matching that. So that's a good news. Slightly different news for Cucumber class, where when we gave them a perfect caption, 0% noisy caption, then the model did look at the caption and caption only. So we see a accuracy of random. There are 3 classes, so 33% is random, which is why the blue line is in around the 40%, and the green line image concept matches that. So remember, the cap class never looked at the caption. Now we're going to do some human experiments. How? We're going to use the salient. Well, the question that we actually really started with here is, well, maybe this example was so simple that saliency map or other methods can trivially do this too. Maybe we have to make this a little harder. So we ran this data set and the model exactly the same thing for on saliency maps for 4 different methods and for 4 different models in each row. And remember, the models did not look at the image. Did not look at the caption. But as you can see, some saliency maps, my own work in the last column, looks like it's highlighting the caption, which is not true. We know that from the ground truth. So then we thought, well, maybe like what we are seeing things that we want to see, like confirmation bias. So we decided to do a Turker experiment. We hired Turkers and train them to tell us whether they think the image or the caption concept is important for classification. We did this and then we asked them how confident they are in their answers. We show them 3 classes and 2 types of saliency maps. And this is the fun part. And this is why I think everyone should do human experiments, because it can teach you something that you might have suspected or maybe you didn't know before. When we did this experiment, half of the Turkers said, oh, it's totally images. And half of Turkers said, oh, it's totally captions. Again, they're looking at the saliency maps. And this is what I was trying to get at answering Rao's question. When you give them an opportunity to be subjective, what humans end up doing is to picking the evidence that matches with their belief, and it's confirmation bias. And this is exactly what's happening here. Which is surprising, because when I look at those saliency maps, I thought, oh, it's totally caption. It's looking at caption. But half of Turkers said, no, it's totally images, which is, my own confirmation bias. More importantly, perhaps, and interestingly, humans are super confident when they're wrong. 40% of subjects said that they could never be more confident. They're as confident as they will ever be in their answers. And doesn't matter when they're correct or incorrect. They're just seeing what they want to see, and they couldn't see it any other way. I hope that this experiment, this example sort of highlight challenges in this field, that because we have this complexity around humans and their beliefs, what they want to hear, the evaluation and designing that evaluation rigorously is very, very important.
Thank you, Kim. Freddie, let's try to keep that to 7 minutes, please.
Sure, yeah. So, so 2 things I want to say in terms of limitations. Probably I'll start with on the evaluation part. So, well, as I mentioned earlier, one of the promising and the things which have been seen, which advanced quite a lot, is on the evaluations on the semantic part. There were the 2 main dimensions, and I think even if they have been progressing, I think those 2 still need quite a way to get adopted in industry. So evaluation is getting better, but I think there's still limitations. And limitations, it's because when you read papers, the application usually is not really tailored for a particular group of persons, and sometimes it's difficult to see, well, to really see what's the advantage or the usefulness or the utility of having the explanation for this particular group of persons. So when I see evaluations with in a mechanical Turks context, it's something it's nice to see because you see it at scale somehow. But what's worried me is when we think about the different profile that you're considering, and if you have particular applications, maybe for a particular application which is designed for the everybody's use case, that might work. But in the applications that my operators and my stakeholders are dealing with in critical systems, the knowledge that they have about the domain is very important for them to make the decision and to trust the system. And so I'll give you an example. We try to equip submarines with machine learning to detect and classify World War II underwater mines. And they try to detect them in the water. And you can apply saliency maps and all those techniques for identifying key features and key elements that make them in this particular class. But usually the human rely on much more information than what has been used and designed. So I think when Ben mentioned that it would be nice to have a ground truth about the explanation, it's true, because if you use the existing saliency map technique and say, based on the model, based on the data, this is what you need, the model need to rely on for the evaluation. It does work in some use case, but in some others, they completely missed information and they completely out of context, and the model just doesn't capture in the very first place. And if you compute all of those different saliency map using many different flavors of backpropagations and attribution techniques, none of them will be the one that you need to use for the explanations, because they're very important correlations that need to be captured, and the model sometimes is using it for making the prediction, but it does it in the wrong way. So that's why sometimes it's important to have a ground truth based evaluation, and that's what is missing. So I think Ben has been mentioning, and I definitely agree with that. And much more evaluations based on the applications, and try to understand what the human is trying to do and what is the expertise is bringing on to solve this particular problem. So I think that's important to be considered. So evaluation for me was advanced, an advancement, but still a way to go for much further adoptions in industry. I mean, in research field, it did progress to a quite steady pace, but for much further adoptions in critical domains, then there needs more to be done. And the second dimension is, I say that semantics is getting a bit more now in the explanation machine learning domain, in the sense that we try to make annotations, and by annotations, it's simply all those annotations that you have on, if you do object detections, you have the labels, and those labels, they are the semantics that they try to use for doing annotations of part of the neural network. And I think it's nice way. So again, that's again the paper here I show, which has been presented at NeurIPS, and that's nice directions. And then probably the next step, then they can add and statement and or statement and negative statements, and they try to compose those. But now, what if you add a bit more structure of your knowledge? So if you start organizing objects with their relationship, so they're very important domain in AI on knowledge graph and knowledge graph embeddings, link predictions, and all of those topics. And can you use this structured information, so this kind of structured facts, that can you use it for somehow guide the rationale, or try to understand the reasoning? Well, if there is a reasoning behind the learning, can we try to at least expose some kind of level of better or higher semantics? So there's been a way, there's been kind of good and steady progresses along those lines, but there probably need to be more to be done, and that's probably the field of neurosymbolic reasoning. It's also an interesting way that we're using work in this particular field for trying to interpret what's really in the neural architecture per se. So yeah. So for me, they're good, they're advancing, but there are still shortcomings. And is it the right way to solve the problem and bringing explanations closer to to human mind and human reasoning, I don't know, but that's an interesting way to go, and we're seeing interesting research papers, and I'm sure that there are probably more to come over the next couple of years. So so that will be my statements for the limitations.
Thank you, Freddie. Vera?
I think he needs to, yeah. Yeah, so open questions. Let me bring back this practitioner's toolbox and ask again with the toolbox how to select and how to translate. I talk about this top-down guideline approach, but it has limitation, right? The obvious one is the granularity, right? For example, decision makers are highly, sorry, I think I haven't started playing. Good. So for example, decision makers are a highly heterogeneous group. A doctor versus a seller versus someone browsing on Netflix, they may need very different kinds of explanation. And also the scalability, right? If the toolbox keeps growing, that will render this top-down approach intractable. I'm curious to hear your thoughts, but I think there could be two paths to solve the problem, not necessarily exclusive. One is to allow users to select directly from this toolbox. I think the field will inevitably move towards this interactive and intelligent explainable AI system that can provide different kinds of explanation. There are a lot of practical challenges, for example, how to develop sensing capability that can really understand what kind of explanation user wants. Our work kind of focus more on the second path, that is, instead of follow this top-down guideline, we encourage product team to engage in bottom-up, user-centered design process to really understand what their user wants in terms of explanation. To give an example without going into detail, this is a design process that we're practicing with some product teams. We call it question-driven XAI design. We're inspired by this social science perspective that explanatory relevance depends on the type of question being asked. So we encourage product team that through user research, first understand for a specific context, a specific interaction, what types of explanation the users want, by what kind of question they may ask. Then we map this question to potential technical solution as the starting point of design, then evaluate and iteratively improve the design by whether these questions are sufficiently answered. We provide something we call XAI Question Bank, which was developed in our previous work, where we quote unquote crowdsource common questions users have for understanding AI across 16 AI products. So they essentially represent this common space of different kinds of user needs for explainable AI, and we encourage practitioners can use it as a checklist to identify what kind of questions are applicable to their products. And these questions have clear mapping to the types of explain AI technique, where we also provide a mapping guidance focusing on XAI algorithms that are available in popular open source toolkits. An important function of this mapping is that they serve as a boundary object where the designers understand the user requirements behind asking the kind of question, and the data scientists understand the techniques and the technical detail to answer this question. And then they can work together to identify the right design solution, which is really important because at the current time for explainable AI, what kind of user experience can deliver often constrained by the technical feasibility. So by supporting this collaborative problem solving between designer and data scientists, guided by user requirements, is our attempt to tackle this how to translate question. To give you an example, this is one team that follow this process. They're trying to develop this AI system to predict adverse event of patients. So it can help doctor to identify high-risk patients and deliver intervention. So the team started by doing user research. They interview doctors trying to understand for this kind of AI system, what kind of question they have. Then we analyzed the question, did some mapping of technique, and you can see the design solution the team came up on the right have a clear mapping with the kind of question they had collected in the beginning, which included the feature importance explanation and contrastive explanation. So another question is, how do we expand this toolbox? What's missing? I know that's an extremely broad question, and I just want to provide one point of view. So we begin to take this view that explainability does not equal explanation. So AI explanation is about AI making itself clear, but explainability lies in the recipient. It's recipient dependent because the user has prior knowledge. They also has a goal to make sense of the AI and end goal, for example, to make a better decision. Being able to fill the gap is explainability. And currently, I think the toolbox focuses exclusively on explanation. What else? What other tool could help us to fill these gaps? So last summer, we worked with a summer intern, Upar Ehsan, who is currently a PhD student at Georgia Tech, to develop this concept of socially situated explainability. We recognize that AI systems are often embedded in socio-organizational contexts, meaning that a group of users are interacting with the AI system, and their interaction, their usage of AI are often governed by certain organizational or contextual factors. These factors are also very important to answer users' why question. Why the AI fail? Why should I trust this prediction? So we say,
Vera, just ask you to wrap up in the next minute or so, please.
Yes, yes. So we say the ability, that's why we're trying to emphasize, the ability in explainability does not lie exclusively in the guts of the AI system. And this is a design solution we came up with. We suggest to record and present past users' interaction with AI, as well as their reasoning for accepting or rejecting AI's recommendation. For example, someone say, I have to lower the price because there's a global pandemic going on, I have to make that compromise. So that helps make transparent this kind of socio-organizational context that also can answer the why question. So I also just want to plug that if you have answer to these questions or if you're interested in other people's answer, I encourage you to submit to our workshop that we're going to organize at CHI, focusing on this human-centered perspective in explainable AI. And then I will conclude my talk, and thanks for your attention.
Thank you, Vera.
Thank you.
So now interestingly, we end up, we try to focus more on industry concepts, and we end up talking about pretty much the same as we're going to be talking tomorrow, when the focus of the panel is going to be user-centered evaluation. So that's very interesting. May I have any other questions now from the audience?
I think Mudit had a question before, but I don't know if he's still here.
Who?
Mudit Berg. If Mudit is here, you can ask your question with me.
He was not able to unmute himself.
So the question was, I can ask a question for him. So the question was, if the explanations are not causal, I think they're useful only for debugging models. But how does image-based explanations help in debugging deep learning-based methods? And if explanations aren't actionable, should we pursue finding explanations of decisions by neural networks? Maybe it's a question for Bean or maybe Freddie.
Yeah, maybe for everyone. Oh, it's an interesting point that if it's not causal, it's only for debugging models. I think it's one of the causal work we did. We kind of defined the causal world to be in the model. So not the whole world that we're living in, but the causal world that model is living in which case you can kind of think about that as also debugging, but also understanding the model. So that point is a really interesting point I want to understand more. Image-based model to help. So is in terms of actionability, I think it's another really important point, and I think what Vera's question bank kind of points at is what directions we should head at in types of explanations that we can offer so that the practitioners can use the system and use them for their goal, not just debuggability and perhaps updating some models, change the data and so on. That's something that we're missing currently in the field, although there are lots of work going on. It is a very important direction. That's all I had to say.
Any other questions?
Any other comments by Freddie or Vera?
Yeah, agree on the causal part. So if you don't try to uncover anything really causal in the model, it's true that it's much more for debugging. I think but if you try to uncover some causal relationship, or whatever it could be, right, in the model, then as soon as you try to uncover that, then the human is more involved, and you probably need to message a bit the information for the person to capture, not only for debugging, but much more for understanding the rationale. So if there's any signals of causality in the model by whatever means, then it's important to go beyond the debugging part. And in terms of actionability, I think the debugging is important because it's help making your, if you're doing a machine learning models, it's helping your model being more robust. And if I do the parallel in the work we're doing in critical systems, it's important for tasks such as certifications. So we try in our case to deploy machine learning models that will be working in industry which have been certified and which have been highly monitored for years. And you don't change the habits just like that. So it's difficult, and then you need to add some kind of level of certification, and robustness is one of the challenge. So anything along the lines of out of the distributions and how those models do operate. Usually, what the people mean by explanation is they say they want something robust, and how you do make it much more robust. And usually the debugging part is part of the journey for making them more robust, and that kind of level of explanation, they are actionable.
Thank you.
Yeah, so I just want to agree with Bing and Freddie's point that actionability depends on users' end goal, and we also need to think beyond debugging. Another point is also, I think, a lot of explainability technique, they can be useful for some tasks. It's hardly that they're going to be effectively useful in all tasks. One way to think about it is some of the explainability criteria, they have certain inherent trade-off, right? For example, completeness versus conciseness, or before we say coherence versus novelty. So it's important to understand when we have a new technique, understand in what kind of context they work and in what context they don't. One of the current project we're working on is to developing this kind of prototypical context or prototypical scenario, and also link them to different criteria. For example, debugging context versus decision-making context. How should we prioritize different kinds of criteria that will also help us to consider this kind of trade-off? And then we have a new technique. We can evaluate them by this criteria, and that will also help us infer in what context they may work better.
Thank you. As unfortunately the time is approaching, I would like to ask the panelists to wrap up your thoughts in about 2 minutes, please.
I go first. All right. Thanks for having this workshop. It's been interesting. Gave me opportunity to kind of look back again to see, okay, where are we? If I had to pick two things, what are the advances? What are the limitations? That was a good exercise. I think despite all, well, not despite, but in addition to everything that we talked about, I think it's an exciting field. The ambiguity in the problem definition, I think, is actually an exciting one. It is challenging one because there's a human, there is, biases or definitions of them, like all this complexity, I think makes the problem really interesting. I am excited to see more ideas and papers that addresses these, and folks like the panelists here who bridge the gap between academia, advances in academia, and bring that to industry that eventually will help people to save more people or help people do better work or being more creative. I'm excited to see more of that. Thanks for having us.
Thank you. Freddie?
Yeah, so yeah, also, yeah, thank you for the invitation. I think it was nice discussions, and thank you for all the questions that you raised. So it's a very exciting field, and if you have been here from the very beginning of the journey, you see very a big enthusiasm and more and more application, much more evaluation, many different user studies, and many different techniques, and now it's getting much more multi-domains. So you have people from social science and the HEI, obviously. So it's nice to have Vera in this panel today, because that gave us the very user-centric perspective of the field, which is very important. And I think the more we do progress, the more we need to have joint efforts and end over on having teams from different domains. And that's probably what we have all seen. It's successful XAI application deployment. It's really depending on seeing the problem from many different angles. So that's something very interesting, and that's looking really forward to the next innovation in the field, and to more applications and deployment in critical systems and large scale systems.
Yeah, and will not repeat what Freddie and Bing has said. It's really also gave me a good opportunity to reflect on things and this needs and opportunity for this interdisciplinary perspective. I also want to say that I think another perspective is also, sometimes I say explainable AI may be a misleading term. Instead, we should use understandable AI. I think in human communication, explanation is just one device for us to reach understanding. There are many other kinds of opportunity, for example, simulation, theorizing, observing how other people do things. So taking this view of understanding AI, I think what the kind of devices, what the kind of technique the community come up with would be useful. And I'm also optimistic that as people living with AI for a long time, we'll also be able to better understand it and make sense of it. Thanks.
Thank you very much. If anyone has any other comments and final questions, Pat, please.
Right. So I just wanted to remind people that AI has been interested in issues of understandability and explainability for decades. Early work in machine learning talked a lot about interpretability and often the trade-off between how well understandable a model was and how accurate it was. And I just want everyone to remember that that's true, and to make sure that they go back to the older literature and not act as though machine learning is something that was invented 10 years ago, when in fact it's been a mature field with fielded applications since the late 1980s. And interpretability was a key issue in getting some of those systems actually into industry back in the late 80s. So just keep that in mind. A few other people in the group have been around that long and know this too, but it's easy to forget.
Thank you, Pat. Would like to thank you very, very much, our panelists. It was an honor to have you. Great insights. Lovely to hear your thoughts about the field. And I will bring back to our other next steps. Thank you very much.
Yes, thank you.
Everyone.
So Rosina, are we on to the wrap up now?
That is Prasha and Sylvia. They have the two last steps. Closing remarks.
Okay, so I think we had a very productive and informative session today with 2 invited talks and also a panel and many contributed talks and papers. So I want to kind of summarize what we have been doing in the workshop so far. So let me put something up. Does Sylvia want to say something until I put this up? Let me.
Yeah, I think
quickly.
like the last discussion we were having actually meets our intent, like because we wanted this cross-pollination between people that comes from different backgrounds and have different opinions on what explainable agency is and explainability, interpretability means. So I think like this last discussion was really like important for us as a workshop and meets our objectives. And yeah, if you want to summarize what came out like this morning with Ofra Amir, we talked about agent policy summarization, while in the afternoon with Timothy Miller, we discussed about explainability in artificial intelligence in general. So do you want to show something? I thought you wanted to show the slides again.
Oh no, I just want to summarize. Yeah, I'll summarize. Yeah. So so I want to see what were the audience's main takeaways were. So if maybe some people might like to talk and comment on today's activities or the main takeaways you got from today's sessions. Happy to give. Happy to feel free to unmute yourself and maybe say some words. And also we want to get some feedback on maybe there were some other topics we might have missed. So if you have, if you like to see other topics, please let us know. And also general observations about the workshops as well.
I have a comment, but I will happy to wait for someone else to talk first. No? Okay. Should I go ahead?
Yes, yes, please.
So I've of course been struggling with the issue of, I mean, this is a workshop about explainable agency. And when I think of agents that either do things in the world or at least think about doing things in the world, like a planning system. And I struggle when I hear people talking about deep neural networks for classifying objects and recognizing object images to view them as agents. Now, I think I think there is an argument for that, because they are going through a sequence of steps, right? I mean, it's not just like a linear classifier or something. It's actually going through a number of steps, and you could think of those as an agent doing sequential processing. So I finally got that through my head today, which is good for me. I don't know if other people see that connection, or if they would find it valuable. Is it useful to think about an image processing system as an agent that is going through some kind of sequential processing where each step could in principle be explained. Is that useful or
So
random?
Pat, yes, certainly useful. And, you know, I of course noticed this with the large percentage of submissions being on interpretable ML rather than on what you're characterizing as agent-based systems. And I likewise was striving to try to increase the interest of those who were interested in talking about agents. We still today see the XAI term being very much adopted by both communities, with one being much larger than the other. So I think we're at the point where it's reasonable to continue to provide forums like this that talk about both sides. And in particular, yes, it gives us an opportunity to think about how work on non-interactive tasks, such as the types that you described, you often characterize them as perceptual systems or something of that nature, can be used down the line by agents interacting in the environment.
Right, but David, I think there's more. The most of the talks I've heard about for image processing are not about explaining the learned model. They're about explaining how the learned model does something on a particular problem, and that makes them actually much closer to what a planning system is doing. It's on a particular problem, right? And explaining their behavior, their decision on that problem. That's very different from old style interpretable machine learning, where you would say, oh, look, my decision tree, you can understand it. That's not what most people are talking about. It actually is closer to what an explainable planner is doing.
Yes. So from my observations, I've seen more work on local than global explanations in the literature that I've been looking at.
Yeah,
certainly agree with you on that.
I do think that's a terrible term, but then I disagree with most terms that people invent these days.
Well, we're fortunate that we don't have to all agree upon your terminology, Pat.
You would call it 25 years ago, you would have called it lazy explanation.
I don't necessarily know that I would. I haven't thought about it that deeply. But yes, I do agree with your observation in that regard. As to whether or not it's more like planning, it's not completely clear to me. Be happy to have the planning people speak up to that. But yeah, that is an observation I agree with you on.
Okay, if you want, we can also introduce the program of tomorrow. So tomorrow we will have Margaret Barnett, Pat Langley as invited speaker. So we will have another session of oral presentations and another session of contributed talks. So I hope this will give us also, with the panel discussion on cognitive science research, give us other opportunities to discuss those topics that we introduced today.
And the workshop would start at the same time, 7 a.m. PST. Are there any other comments or anything else you would like to discuss?
Thank you of your help and your participation and for being awake, Prashant. Appreciate it.
Thanks, everyone. See you all tomorrow.
See you tomorrow.
We can wrap this up.
See you tomorrow. Good night.
Thank you.
Bye.
Bye.